Ladies and gentlemen, welcome to the 2024 Future Science Prize Week. The Science Symposium will begin shortly. Please be seated. Please turn your mobile phone to silent mode. Stay tuned and see you in a bit. Ladies and gentlemen, the Science Symposium is about to begin. Thanks to the support of many parties, the Future Science Prize Week has been a great success. Please give a big round of applause to show your appreciation. Organizer, the Future Science Prize, and co-organizer, the Hong Kong Academy of Sciences. Our strategic partners are Sino Group, Shangri-La Group, Tencent SSV Organization, the University of Hong Kong, the Hong Kong University of Science and Technology. Our partners include Qiming Venture Partners, 5Y Capital, Sanofi, Future Innovation Fund, Fully Supporter, Leisure and Cultural Services Department, and our supporters including Hong Kong Science Museum, Hong Kong Space Museum, the Hong Kong Young Academy of Sciences, Hong Kong Subsidized Secondary Schools Council, Hong Kong Direct Subsidy Scheme Schools Council, Association of Principals of Government Secondary Schools, Acknowledgement, including All Stars Investment, CTF Education Group, Nanovo, TrustStar Capital, We Light Capital, Alcoholic Capital, Carl Lake Consulting, Frencher Foundation, UBS, 1886 Holding Group, Tomakado, Computing Art Lab, and our media partner, Radio Television Hong Kong, RTHK, our funding organization, Innovation and Technology Commission. Without your support, the event would not be so successful. Thank you very much. Distinguished guests, ladies and gentlemen, parents and students, thank you for joining the 2024 Future Science Prize Week and the Science Symposium. It is my great pleasure to be the MC today. I'm Yo Lang. Hello everyone, good morning. Good morning. We are so thrilled to be here with many great minds of the year. The Future Science Prize Week aims to promote scientific spirit and pay tribute to scientists, leading the public to explore the forefront of world science with a forward-looking perspective. This year, our program committee sets the agenda and invites domestic and international keynote speakers to ensure the high level of academic content and extensive global perspective of the conference. The next session will be physics session, quantum information. To begin with, program committee co-chair and the convener of physics session, Professor Douglas Nelson Cho-Lin will deliver welcome remarks and introduction about the physics session. Let me introduce his profile. He is Professor, Astronomy and Astrophysics, University of California, Santa Cruz. Distinguished Visiting Professor, Institute for Advanced Studies, Tsinghua University. Member, American Academy of Arts and Science. Member, Science Committee of the Future Science Prize, co-chair, Program Committee of the Future Science Prize Week 2024. Let's welcome Professor Lin.
Thank you. Distinguished guests, ladies and gentlemen, good morning. It is my honor to be the conveyor of this morning's section on quantum information. This subject is one of the most fascinating and enigmatic areas of scientific endeavor. We are fortunate to have preeminent pioneers as well as rapidly rising stars from Europe, US, and China to share their contributions and perspectives in this rapidly advancing branch of physics. Let me introduce each of the speakers. First, let me introduce you, Professor Peter Zoler. Professor Zoler is an internationally renowned theoretical physicist whose main research area includes quantum optics, quantum computing, quantum information, and quantum simulations. Basically, quantum everything. Professor Zoler is well known for his pioneering work in the field of quantum computing, particularly for his theoretical proposal with Ignacio Cirac on using ion trap systems to implement quantum entanglement gates. This theory laid the foundation for quantum computing to transition to experiments and inspired the discovery and the development of other physical platforms with the potential to achieve large-scale universal quantum computing. Professor Zoler's research accomplishments are not only theoretically significant, but also have inspired a wide range of experimental physics programs. His work has built a bridge between quantum optics, quantum information, quantum metrology, and promoting the development of quantum communication and quantum computing technology. In addition, Professor Zoler has explored large-scale entanglements in quantum simulation, developed new measurement tools that can study physical phenomena previously unattainable, and helped better understanding of quantum materials. Professor Zoler has received several international awards, including the World Prize in Physics, in recognition of his outstanding contribution to the field of quantum computing and quantum information. The title of his lecture is Quantum Simulation with Atoms and Ions. Professor Zoler, thank you.
Okay, so let me first of all thank for the invitation to come here. I really feel honored to be part of this Future Prize Week here. And this is a session here on quantum information. Since I'm the first one, what I would like to do is first of all, give a very general introduction that's maybe more aimed to high school students or undergraduates, and then move on to the second part of my talk, which is what we're doing right now, which is quantum simulation of lattice gauge theories. We have some new results along these lines. At one point, this gets a little bit more technical, and we'll try to talk about it, of course, in very qualitative terms to give you the whole spectrum, what the idea is, then all the way, forward and to sort of new results. You might ask yourself, what this picture is. This is a painting in the entrance hall of our Quantum Institute, and this is Erwin Schrödinger, one of the founding fathers of quantum physics. He wrote down the Schrödinger equation, that explains atomic physics, quantum chemistry, nuclear physics, and so on. But he's also famous for the Schrödinger cat down here. These are these cats that are dead and alive at the same time, and probably you have not seen so many of them walking on the street. But you will see them today because they live in our quantum computers, of course, not as real cats, but they live in our quantum computers as superpositions of zeros and ones, what we call then entangled states of a quantum register. This is a title of my talk here. I will talk a little bit about quantum computing and then in particular about quantum simulation. My own background is atomic physics, and so we are going to speak about quantum processors and simulators mainly built with atoms and ions that we would like to control then with laser. This is a long story in the meantime, because we are celebrating actually this year the 30th birthday of quantum information. Peter Shor wrote down the Shor algorithm 30 years ago. This motivated a lot of this work and our ideas regarding ions and so on that I will explain now briefly, also now 30 years old. Let me start out by simply telling you this is sort of an old-fashioned ion trap. It's like, when you have an old car, you can still, raise the hood and look inside. There was the real engine inside. Very similar here. This is an ion trap, and you can see the individual ions. So very often people are impressed to say, you're storing information in single ions, in single atoms. That's quite impressive, but of course, this is not the point of the story. The point of the story is that this is single atoms that we prepare in vacuum in free space, and we trap them with electromagnetic fields, and they are charged particles. They repel each other. They form a little crystal that you can see over here. But they have also internal structure like spin. And this at the end will be our qubit that we are going to explain now later. And of course, this is basically what at the end will correspond to the Schrödinger cat that we just talked about. The point, of course, is that this quantum computing should not be seen as an extension of sort of the standard classical computing being fast or whatever in any way, but really as a new paradigm. A new paradigm that I guess will really shape our present century that we have in providing really new information technologies, and I think that we are really well on the way of actually achieving that. Of course, talking about these ions, there's a question of we have to scale up these quantum computers. And, just in the case of the ions, you can make 2D crystals, very long 1D chains. And, what used to be sort of labs like you saw over here, the big picture, on the right upper side over here, you can see that, this is sort of all of these things now put into a rack. So we are at the point where these things get condensed in racks and are sort of useful as computers that you can really install also in computer centers. But for those of you that are sort of maybe not so familiar with quantum information per se, talking now to the undergraduates and maybe also the few high school students that are here, let me explain a few of the basics. When we talk about classical bits, they can be either 0 or 1, and a quantum bit can be in what we call a superposition of 0 and 1. So it's sort of 0 and 1 at the same time. And we always have ways of representing it by something that we call the Bloch sphere. Classically, there's only the South Pole and then the North Pole over here. But quantum mechanically, it's like visualizing this thing that all points of the sphere are possible states if you're a quantum state, representing the superposition of zeros and one that we can store in our quantum register. And this is an attempt, sort of a classical attempt to represent these things. Depending how you look at this picture, it's either an old woman or a young woman. Of course, we can take our classical bits and our quantum bits and we can combine them to what we call either classical registers by having like over here 0, 1, and 0, but also then a quantum register where we have now superpositions of all of these numbers that are at the same time live in our quantum computer in this quantum memory that we have. And of course, at that point, what we have is exactly the Schrödinger cats that we talked about now before as the superpositions of zeros and ones that we are storing in our quantum computer and which at the end then give the whole thing the power of quantum computing. Of course, the space where all of these things is happening is actually huge. So when you take something like 300 of these qubits, you got 2 to the power 300 states, and they are represented simultaneously in your quantum machine. So in this sense, you can see that we have a huge space over here. This Hilbert space is really huge, and this is what made Feynman say, of course, that suppose that you would like to do computations on a classical computer of, say, quantum materials, it becomes at the end very hard, but this entanglement here gets very, very large. Let's now have a look inside what we have to do in order, to understand and at the end and also build a quantum processor. What is the task that we have to do? So we have here input states, down here that are the different qubits that are entangled. And of course, we have to operate on these qubits by what we call quantum gates. So these are operations on the qubits here that either can be so-called single qubit operations or then entangling operation down here. At the end, the question is, how do we do that in the real experiment? And, the single qubit operations basically correspond to a rotation on this sphere that we talked about before. We call it the Bloch sphere, or there can be something like a Hadamard gate over here. But we can also, and this is sort of the tough part in designing a quantum computer, think about how to make what you call 2-qubit quantum gates, where one is the control and the other one is the target. So depending if the control is on the South Pole or the North Pole, 0 or 1, you can either do nothing or you can maybe swap the 2 states on the other qubit that you have over there. Implementing, of course, these entanglement operations is the core and also the main difficulty in building a quantum computer, apart, of course, from the fact that you have to isolate your Schrödinger cats really well from an environment. You can see here that these kind of gates act on superposition states. So in this sense, we have in our quantum computer not only a single number, but a superposition of different numbers, and we act with these gates in parallel on all of them, and this is what we call here quantum parallel processing. Let me now go back to the ions, and as I said before, this is a string of single charged particles that we have laser cooled down to very low temperatures. We trap them in a vacuum in the chamber, and we want to convince now this object here to act as a quantum computer. And of course, for us as physicists that know a little bit of atomic physics, we know that these are atoms that have maybe, say, an outer shell electron. And this outer shell electron can have a spin, and this spin can act as our qubit. It can be spin up, can be spin down, but of course, any superposition state, and if you got the whole register over here, it can also be entangled. This is quantum memory, and it turns out that the quantum memory of these atoms in terms of quality is really, really high. This quantum memory has a lifetime of, well, depending how they do that, in some cases it can go up to maybe even minutes. The internal atomic physics that's going on is that you have here, for example, in these calcium ions, very long-lived states, that live, in this case, a second, and in particular realization over here. And then we have here other lasers that allow us to read out the qubit here in terms of measurements. But the central part, of course, is how to do gates. And the single qubit gates are very simple because we only have to shine lasers on the individual ions to rotate them. This is not very hard, but of course technically challenging, but conceptually quite obvious. The question is, how do we get the entanglement? And the entanglement, in the case, the ideas that we had together with Ignacio Cirac were that, these ions, they also have motion, they vibrate, as you could see over here. This is, of course, classical motion, but we can use this motion, if you cool it down to 0 temperature, also as a data bus to communicate, qubits from one internal state to another internal state of some other ion. And this, at the end, allows us to design quantum gates, and they have been implemented now in experiments, up to the point where we have sort of a whole library of different operations on these strings over here, acting with our lasers. We can read them out, and we can easily perform now, without doing any error corrections, for example, a few hundred of these quantum gates at the moment, until the whole thing falls apart. Of course, we would like to do that with an increasing number of particles here. And just to sort of tell you where one is at the moment, I've taken as an example here, that's H2 Quantinuum computer, that you can actually buy. And if you look at the gate fidelities over here, you can see at the very beginning, when people did the first experiments, they had gate fidelity, which is the quality of these quantum gates of about 85%, maybe 90%. In the meantime, there's a lot of 9 over here. This means that these gates that we are talking about can be implemented in the experiment with very, very high fidelity. And this, of course, is a good starting point. This means that error correction is something that, is either maybe not necessary in some cases, and in other cases, has to be done only very infrequently. So in this sense, we have gone a very long way from initial ideas, 30 years ago, first experiments on single ions, and now they talk about actually in some of these cases, even a few hundred ions where they do this kind of a quantum computing. But let's take a step back and simply say, of course, I've given you the example of the trapped ion quantum computing as, as a historical first example, but as an example that also survived. We have, of course, now several other examples out there, from, for example, in particular, here, superconducting qubits. We have then, for example, defects in solids and so on, various solid-state devices. This is trapped ions over here, and atoms and so on. I'll talk afterwards also about Rydberg arrays, which is now, I would say, one of the most promising systems in terms of scalability, but I'll come back to these things later. But if you want to summarize, we can really say here, the key features are, or the requirement is that in developing all of these things, first of all, controllability. You would like to be able to control down to the level of a single quantum, a many-body system with a growing number of qubits. So the scalability, this controllability is key. And at the same time, of course, you have to do that in a way that this controllability is preserved by scaling up the number of qubits to a very, very large number. And this is sort of the fundamental rivalry that we have in building these systems. And this is, a slide that I've copied here from actually Misha Lukin, who gave it to me. This is the guideline, I would say, for what's going on at present, that we have different platforms, but the controllability and scalability, of course, are the key features that we have to try to implement in these experiments. So the current frontier, if you want to read this, is that you would like to do here tasks, that they are beyond maybe the classical computing that we can do at the moment. And we want to do that, now with qubits that are approaching now, I would say 1,000. And I would say that some of these systems obviously scale to higher numbers. We want to test and implement useful algorithms and applications. And of course, at the end, we also want to do error correction. And I would say that many of these things have now been achieved. And just in the last year, in terms of error correction, I would say has been a highlight, in the development of all of this and the application of these quantum machines. Let me comment just, and then I move on to this quantum simulation part. Let me just comment on briefly, where the power of quantum computing actually comes from. We have talked before about, having a quantum register and superposition states over here. If you think about a classical interferometer over here, then you can see that an interferometer has two light beams that eventually interfere to constructive interference, or maybe destructive interference, giving rise to interference fringes. And in a quantum computer, something is happening, but on a sort of a much larger scale, because you got this huge Hilbert space over here, the huge Hilbert space that represents the Schrödinger cats over here, where you're doing sort of in parallel all these different computations, which at the end can interfere, giving rise to algorithms. And I just want to point out again that Peter Shor came up, of course, with the factoring algorithm now 30 years ago. Somehow this was the initial point and also the motivation to develop many of these things. But of course, in the meantime, we have many other examples also. But one that I find particularly interesting is the problem of solving quantum many-body problems, which is what we call the problem of quantum simulation. So I would like to switch over now to problems that I'm personally also very interested in, because they really are physics problems in nature where we are trying to solve from quantum computer, either digital or analog. I will give you analog examples now in the following, many-body problems. And this goes back, of course, to Feynman's original vision, who said that, classical computers have difficulty simulating this many-body problem because of entanglement, and now we learn how to control entanglement in a programmable quantum machine in order to do that. And we have, of course, many examples, and you should see this like constructing a special purpose quantum computer here, where we might design different kind of materials, maybe design also quantum chemistry, different drugs and molecules, but of course maybe also do very fundamental science, like for example, doing here, I don't know, high energy physics and being able to do simulations that are beyond what one is able to do right now. And they will afterwards show you sort of a little toy model that tries to go in this direction over here. Let me first remind you, however, briefly, why sort of in our condensed matter language, this simulation is sort of hard. Classically, if you think about, this is a magnetic drive that some of the older generation might still remember. Basically, think about it as having many spins that are in a certain configuration. It can be spin up, spin down, or many other configurations. Quantum mechanically, of course, we have all of these 2 to the power n configurations simultaneously. And this is sort of the power why we would like to do quantum simulation, that we're able to handle these large superpositions, in our quantum machine in a controlled way. And this, of course, is just, as I said, Feynman's original idea how to do all of that. Let me now switch over to a little bit more technical part, but I would like to make it nonetheless very qualitative by trying to explain to you some of the physics that we are trying to do over here with my hands rather than in writing big formulas. But at the end of this thing, there will be an experiment that will allow us or sort of show us in this context what one is able to do at the moment and where, in terms of science applications, some of these developments also go. So, lattice gauge theories, of course, appear. Quantum chromodynamics is one example in high energy physics. And I've taken here 2 examples. On the left-hand side, you can see that we have here some phase diagram where we have different states of quarks bound together, or maybe moving freely, like a quark and gluon plasma and so on. And on the fundamental level, this kind of interaction between these particles is described by gauge theories, or if you put them on the lattice for computational purpose, by what we call a lattice gauge theory. And these kind of different phenomena on the left-hand side, you can see over here these quarks bind together to nuclei. This is the nuclear physics over here. Over here we have something like color superconductors and all of that. Can we understand this phase diagram? And of course, on the high energy physics side, fantastic methods have been developed to describe and compute these phase diagrams, except of course that one has difficulty in going to the very high density limit over here, because then classical Monte Carlo simulations fail. And of course there's another range of experiments which are really collider experiments, where we have all of these jets that go out to describe or sort of model from a theoretical point of view these kind of processes is something that is really, I would say, on the large scale impossible. And one can do, of course, many approximations like semi-classical and so on. But this is where maybe quantum computing can find its own purpose and its own niche here. And so we have here the computational sign problem, either in real-time dynamics or at finite baryon density. And this is, of course, also something that we have in parallel, not only in high-energy physics, but there's, of course, counterparts also in condensed matter physics and more general, and also in the more global context, in this quantum information context. So let's think a little bit about, what these kind of things are, to what extent we can develop and program our quantum machines to handle these things. I have to tell you right away that, what you can see on this slide is something that really goes beyond what we are able to do at the moment. This is far too big for the machines that we have right in the lab. But what we can try to do is to identify certain phenomena that we identify as being important. And this will be string breaking now in the following as one example, that we have confinement, deconfinement, that we see confined phases and the corresponding properties and all of that. And to construct very simple toy models that illustrate certain phenomena, knowing, of course, that we are pretty far away from this ultimate goal that we would like to do over here. But it is amazing to see that the machines that we build at the moment are able to provide us with quantum simulations on the level of these toy models. And this is what I would like to talk about now in the following. So the phenomenon that I would like to speak about and to show you then experiments and afterwards is the phenomenon of what we call string breaking. And string breaking basically consists of, well, let me simply explain it like this. Imagine you got some rubber band and you pull it more and more and more. At one point it will break, you know. And very similar, if I take, for example, a classical charge, positive, and the other one negative, and I got now an electric field, you know, line connecting these things, an electric flux line connecting that. If I make it longer and longer, there will be more and more energy stored, electric energy stored in this string. And of course, at one point, it will be for the system easier or sort of simpler to produce pairs of particles created from the vacuum, electrons and positrons in the case of quantum electrodynamics, that will break the string. And this is what we try to indicate over here. This is a picture I've copied from the internet, that we have here these two charges. We pull them apart, and at one point you create here electron-positron pairs, or maybe quark, anti-quark pairs, and so on. And this is the phenomenon of confinement that we have, and is fundamental, of course, in all of this, quantum chromodynamics, but of course also in the context of electrodynamics, we have that. So if I get a little bit more quantitative, you can see that we have here two things in our context. On one hand, we have here the potential that corresponds to a certain length n with the string tension. So the longer the string is, the more energy you store in here. This is the line that goes up here. And you can see that we also have here a broken string, where, of course, this whole thing has collapsed to just here two, let's call it mesons. This is a meson, and this is a meson over here. So this is a quark and anti-quark over here, bound here to this charge that we have in our problem, where the energy has been now become independent of this distance d by forming now this, in the sense of pair production, two particles over here that are now bound. And now you can see this corresponds to the line up here. So the ground state of the system will be, well, the string gets more and more dense, then it breaks, and then it will be flat over here. We'll try to see these things in the following, then in an experiment where we design a lattice gauge theory. And if I, just in a very elementary way, try to represent this kind of physics and a lattice gauge theory, then we would have here, a lattice where each side carries matter, and we put here classical charges, the red one over here and the other one over here. And now you can see here the corresponding electric flux line, for example, connecting these two. And the broken string now corresponds to having created an electron-positron pair, quark, anti-quark, from the vacuum, that now form these bound mesons. So this is sort of on this toy level, a kind of dynamics, and that we would like to describe and now try to see and model in our experiments. Can we identify systems that do all of that? And we just put a paper on the archive, actually, now a week ago, which was an interesting collaboration for us between Innsbruck Theory and Quera. This is a startup, starting from Misha Lukin's group at Harvard. Misha Lukin is also here, where we use their machine in order, this machine is called Aquila, has 256 qubits, in order to simulate here, in a sense of creating synthetic quantum matter, that shows the string breaking, and where we have tunable parameters that show all of these phenomena that are sort of fundamental on this level over here. And quite interesting, in more or less within 2 weeks, two more papers appeared. One from Google, they did digital quantum simulation of the same problem. You can see a 2+1D lattice gauge theory, and then there was a 1D experiment coming from the Chris Monroe group at Duke University in collaboration with Maryland. So I talk about the experiment down there because this is the one that we were involved and tried to do now for 2 years and made a lot of progress then just during the last few months. And I would like to give you a qualitative idea what can be achieved and what can be done in these kind of toy model simulations of lattice gauge theories. But before I do that, let me tell you a little bit about Rydberg tweezer arrays, because this is the hardware which underlies all of that. And very similar to the ions, I worked on some of these things now more than 20 years ago, and now they are finding their realization in the lab. And of course, what the experimentalists do here is this. They would like to build quantum systems one by one, and I find this a very amazing story, and just show you a few beautiful pictures that I've collected from my experimental friends, in particular from actually Misha Lukin at Harvard. And this reminds you that when we talk about tweezers in biology, we have light, which allows us to trap and move, for example, small dielectric particles around. We now would like to do the same thing with single atoms. We can catch single atoms and trap them in a tweezer, which is a focused laser light, and we could do that for many. And we are trying to catch these atoms. Of course, we might not always be successful, but we can look if you see these atoms, if they are trapped or not, and you delete the ones which have no particle, but you can rearrange, because these are tweezers, they can be moved freely into any configuration that you want. And I always like to show this example down here. This is a 1D example. You tell them any pattern that you want, and at the end they even write your name, but this costs you a beer, I have to tell you, and so it doesn't come for free. At that point, you might ask, what's the distance between these tweezers? About, say, 10 micrometer, very similar to the ions. And the question is how to make interactions. And I would like to tell you now a little bit about how this is done, showing you a few beautiful pictures, but then we get serious and we go to the experiment and try to simulate the lattice gauge theory. Of course, what I show you, this free arrangement, is not only 1D, could also be done in 3D. This is from France. Antoine Brouet's group has done these things. And the question, of course, how to make the atom interact. And I have a few pictures here on this Rydberg electrons. I find them quite entertaining. So let me show you. So if you got an atom, of course, we have think about Bohr radii at the moment, or Bohr orbits. We have different Bohr orbits here. We can, of course, take one of the ground states of these atoms, and we can excite them with lasers to very high Rydberg states, with a quantum number n, which is really large. And there's, of course, this famous Rydberg formula, which was the starting point of our atomic physics. And if you look at the numbers here, these atoms, by bringing them to Rydberg states, you make them huge. They become roughly the size of a small virus, even. So you have an atom that is, a few Bohr radii, and then it becomes as huge as, micrometers. Now, it's also very clear that if you excite atoms, to these highly excited states, you also start to interact very strongly, and this is a resource of entanglement. And if you start to put in numbers and you come up with gates, these are papers that we wrote together with Misha Lukin now, you can see quite some time ago, but today these things are reality and also lead to very high fidelity gates. You can create interactions between these atoms and entangle them either as gates or by an interaction which is always on. And this is a way of engineering interactions between atoms, like, for example, the ones that we need for lattice gauge theory. Of course, at Harvard, this thing has been developed now. They're now really doing quantum computing with these things by having all of these arrays of atoms over here that can be moved around freely. And, we had these ideas of moving around a long time ago, but now to do it in an experiment, this is quite amazing. You can see all of these gate operations happening in parallel. This is now really quantum computation done in parallel on these qubits over here. And of course, a recent highlight from Harvard has been this error correction done in this way. And error correction at the end and doing fault-tolerant algorithms. Let me now go to the sort of a little bit more hardcore part, and then I will do this very quickly and just tell you what the basic ideas are. So we can create, using these tools, synthetic quantum matter. And they correspond to certain Hamiltonians, and they are really, really well controlled in the lab. That we have Rydberg interactions, we have a certain blockade radius, and by this we mean that we got atoms at a certain distance, and we would like to excite them. Only one can be excited, or the other can be excited. Exciting two of them would be too expensive, and we cannot actually do that. And this leads to a constraint, and it turns out that the Gauss law and lattice gauge theory can be sort of reformulated as a blockade constraint in this Rydberg tweezer arrays. And when we do now analog quantum simulation of what we call a quantum link model in this atom array, sort of the story goes like this, and I will be very brief here, that we have here 2D atom array, and there will be a certain blockade radius. So if one atom is over here, this is at the link of a honeycomb lattice, this is a Kagome lattice here, you can see other atoms like this one are out here, they cannot be excited. So this allows only certain configurations, and these configurations basically correspond to the Gauss law that we have to do in lattice gauge theories, and we can reformulate or reinterpret all of these different configurations of these atoms being on different lattice sites as charges and strings. And let me now try to explain this table over here, but show you what we expect from the theory by taking these Rydberg models and simulating that and translating the pictures into the language of lattice gauge theories. We can see over here that this would correspond to the case that we have a defect over here, defect over here. This is really punching holes in the synthetic quantum matter. And now this is theoretical calculation. The string develops, and over here you are in the regime by controlling your laser parameters where the string is broken. The potential for that is exactly what you expect. You can see the string tension and then the breaking of the string. This is reflected in this design of the model that we have over here. Then you go to Quera, to your friends, and there will be now different string configurations. You do theory, you get a certain phase diagram as a function of string tension and mass. There's a string, and there's a broken string over here. And then you can, go to the experiment. You indeed see that this blue regime goes roughly to that over here. This corresponds to this string. And then we have, of course, also here broken strings. The bottom line of the whole story, to sort of cut the whole story short, is this, that we see in the experiment as the ground state, the one, where we have here strings, or then we have broken strings. You can see here a broken string, only one configuration is over here, whereas over here you can see all of them somehow present. So this needs, of course, now more detailed discussion, but I think that the take-home message at this point is that, these quantum simulators that we have at the moment in the lab, they may be small, they may be toy models, but they already allow us right now to see phenomena that are highly non-trivial, and they will up to us in the coming years to develop all of these things. We can also do that for dynamics, what you can see over here. And if I want to conclude, I would simply say that, well, one of the big next steps will be, of course, that we really do fault-tolerant quantum computation, and of course, at the same time, then you have to develop things like high-fidelity gates, and finally reaching, of course, what our ultimate dream is, namely to go to the regime where for a useful or a relevant problem, we are able to do quantum computations that are at the end then, beyond what we can do classically. And of course, there have been examples in the past, but we really would like to push it at a point where we can compute something that hopefully will be a physical discovery. And I think we are maybe not too far away. With this, I would like to thank you for your attention.
Let me introduce the next speaker, Professor Wen. Professor Wen is a renowned condensed matter theorist and Cecil and Ida Green Professor of Physics at the Massachusetts Institute of Technology. He graduated from the University of Science and Technology in China and then received his PhD from Princeton. Professor Wen's research has led to a fundamental shift in our understanding of strongly correlated condensed matter systems. He introduced the notion of topological order and symmetry-protected topological orders to describe a new class of quantum matters beyond Landau symmetry breaking theory. He discovered C2 spin liquid, the simplest example of topological order, as well as non-abelian statistics in a class of 2+1D topological ordered wave functions. He developed the string net theory of topological order, which led to the emergence of gauge boson and fermion. The string net theory provided a way to understand and unify gauge interaction and Fermi statistics, and led to a new type of unified theory using quantum information to unify all elementary particles. Professor Wen received the Oliver Buckley Condensed Matter Physics Prize and the Dirac Medal. His work continues to to influence and inspire researchers in the field of quantum physics and condensed matter theory. The title of his lecture is The Origin of Light and Other Elementary Particles, Unification of Matter and Information. Professor Wen.
Yeah, it's really a great honor to speak here in the Future Science Prize week. And the Future Science Prize is really a celebration for the advance of science and its application. And today I'm going to talk about the origin of light and other elementary particle and the unification between information and the matter. So let's start from a bigger question. We know our world is very rich and very complex. And so there's a question is that where those rich and complex world come from and how to understand them. And the physics is a development of physics is via the cycle of discovery and the unification. So we have more and more powerful experiments, discover a lot more phenomena. When you have too many new phenomena, too many new discovery, we want to understand them better. Then we want to unify them under some simple unified framework. And so each unification, the big unification, actually represents a revolution in physics. So in this through this revolution, we may each revolution may bring us into a new world where there's some fundamental concept. Some fundamental concept is changed. And the mathematical formulation also changed. So the whole worldview is changed. So let me just give some example. So the first revolution in physics, we can call it a mechanical revolution. What they unified? They unified this the falling apple on the Earth and the planet motion in the sky. So these two seemingly very different phenomena actually have the same reason. That is Newton's law of physics. So after this Newton's mechanical revolution, and our worldview is that everything is made of particles. And Newton's law governs the motion of a particle, and the collection particle explain everything we see. Okay. And there we have also, in this Newton's mechanical revolution, we also need a new mathematics. Because Newton's new phenomena they encounter is a curved motion. So we have to describe curved motion to write down his theory. Newton has to do that. But unfortunately, at that time, we don't have a mathematics to describe curved motion. So facing this new phenomena, Newton had to invent a new mathematics, which is called the calculus. Then after he invented calculus, then he can write down his theory. So actually, the introduction of new mathematics is a sign that the physicists encounter a really new world. We are facing a new revolution, and so we need a fundamental change our understanding. The next revolution is, I will call this electromagnetic revolution. And in this revolution, Maxwell find a new type of matter, I will say that way. Remember, in Newton's worldview, everything is made by particles. But Maxwell said that, oh, that's not quite true. There's another kind of matter, is light. Light is a kind of a wave-like matter, not the particle-like. And they satisfy a very different law, the Maxwell equation. And here, the new mathematics is a fiber bundle. What they unified is this phenomenon of electricity. Yeah. Electricity, the magnetism, and the light. Again, on the face value, they are so different. The magnetism, electricity, light is totally unrelated. But actually, they are the same thing. They're reflection of the same thing. They're all reflection of this wave-like matter. Then we have this relativity or revolution. So Einstein basically pointed out that in addition to light wave, there's another kind of wave-like matter, which actually is a deformation of space. Even space itself can be deformed, can be dynamical, which gave rise to gravitational force. And here, the new mathematics for this space deformation or for this second kind of wave-like matter is a Riemann's geometry. The fourth revolution I would call the quantum revolution. In this revolution, we find that the spectrum of atoms and this diffraction of electron and the black body radiation, again, those are very, very different phenomena, are unified. They are really can be explained within the same framework. However, in this revolution, our worldview also changed. The Newton tells us everything is made by particles. The Maxwell and Einstein say, oh, there's another wave-like matter. But quantum theory tells us that actually particle-like matter and wave-like matter are the same thing. Those matter are particle, nor wave, and also both particle and the wave. So it's all mixed up. It's very hard to swallow. What do you mean by something is not particle, not wave, but also both particle, both wave. And this is really the magic of quantum superposition principle, which is Schrödinger cat, Professor Zoler talked about. That's what makes it possible. So actually, the new worldview under quantum physics is that everything is made by the so-called wave particle-like matter, something mysterious. Okay. And however, if you really brainwashed by quantum theory, actually you will say that matter and information have very fundamental connection. Traditionally we think information is some kind of property carried by matter. Your information matter are very different thing. It cannot be mixed. But however, quantum theory tells us that the frequency is energy. It's just like how do I say that? It's just like the pound and the kilogram. Is a pound and kilogram actually the same thing describing weight? The quantum theory tells us that the frequency and energy are really two quantities actually describe the same thing. They're really the same. And it's really by this fundamental relation that the energy is given by the Planck constant times frequency. So this is a very fundamental connection between frequency and energy. Again, it's very, very mysterious. But however, if you think deeper, you realize that the frequency actually is a property of information. Something changed, anything changed is a frequency. But energy is a property for matter, especially according to relativity. The energy and the mass, they all unified. They really just is a property of matter. So quantum theory of Planck constant connect the fundamental property of information to the fundamental property of matter. Basically tell us information is matter, matter is information. And so this really come to this belief that there should be a unification of matter and information, or maybe matter coming from information. But how this is possible? Okay. And the traditional view of matter is this reductionist. We view the space as empty stage. The matter are actor on the stage, and this actor can be divided to smaller and smaller pieces. But however, in the modern time, this emergence of approach this point of view became more popular. So in this approach, we view space itself is not an empty state. Space itself is active. Space is a dynamic medium. And this medium made by qubits. You know, qubits is the most fundamental, simplest building block in quantum mechanics. There's nothing simpler than qubits. So the space actually can be viewed as an ocean of qubits, like this picture. There can be 0 and 1s, and they interact, you know. And this is very much like the philosophy. There's a 太极 and a 两仪. You know, 太极 actually is a qubits. The 两仪 is a 2 value of qubits. And the 八卦 means 3 qubits, you know. But actually our universe is, I don't know, I can see they have 10 to the 120 qubits. So this is much more than 八卦, you know. But when you have so many qubits, some wonderful thing can happen. So actually, our universe is very, very complex and have a lot of many fundamental properties. And I list them as these 8 wonders of universe. And like this, like you have identical particle. There's a wave satisfy Maxwell equation. That's a Maxwell's contribution. And there's also a wave satisfy Yang-Mills equation describing the strong and the weak interaction. And then we have this mysterious particle called the electron quark, which have a Fermi statistics. Again, something very weird quantum effect. And they have a fractional angular momentum. And also we certainly have a wave satisfy the Einstein equation. That's just another wave. So there's a bigger question. Can we use a qubits to explain all those mysterious properties? You know? And the mainstream theory in physics tell us that no, those properties are so fundamental, and they are so fundamental, so mysterious, there's no explanation for them. So we should just accept them as something given to us, and then don't ask where they come from. But however, in the quantum information age, in particular, when we build these quantum simulators, maybe those kind of things can be simulated, can be understood via qubits. So that's this quantum simulator Professor Zoler talked about, may be able to simulate and explain those fundamental, even fundamental properties of a universe. And you know, after Maxwell wrote down his wave equation, and people have asked this kind of question. You know, if you think a light is a wave, then what is a wavy? You know, and then there's people search for such a media whose deformation, whose wave gave rise to the light wave, and failed. And actually, there's also standard theory. You know, this media was assumed to exist. It's even have a name called ether. And people looking for this very special media, ether, whose deformation gave rise to a light wave. And people couldn't find it. And even have an experiment to show ether cannot exist. So therefore, the standard theory that ether do not exist, and there's no media which can produce a light wave, a light really fundamental, you know. And so indeed, in condensed matter physics, we really study many, many materials and study all kinds of waves in those materials, and none of them such a Maxwell equation. So it's a very frustrating experience. We just couldn't find anything which produced a Maxwell equation. But however, the recent progress is that we realize that the material we're looking for are actually more classical. They describe by symmetry breaking of a Landau. Actually, as a quantum material, there's a new kind of organization that the qubits may have a lot of entanglement, may be highly entangled. So those highly entangled organizations are called a topology order. So this kind of organization is not studied before. So maybe we have a new hope. Maybe with this new kind of organization, this kind of material may be able to produce light wave. So, so one of this highly entangled material can be made by this string. We can imagine we have this media where the qubits with the empty dot is 0 and the black dot is 1. And this 1 may form a string. And the string may just dance around and form a string liquid. But that certainly is a simple way to say dancing around form a string liquid. A more precise way to say that, according to Professor Zoler's talk, is that there are superposition of all different string configuration, and that gives rise to the quantum liquid. And this kind of superposition of the dancing pattern of a string configuration is actually have a long-range entanglement. It's representing a topological ordered material. And this kind of material probably can give rise to light, give rise to Maxwell equation. And that's indeed the case. So let's consider a string liquid. So this animation just representing a string liquid. This kind of superposition of all kind of string configuration. So when you have this string liquid, remember string are formed by qubits. So those are really entangled pattern of qubits. Then you may ask, what is the deformation? What is the wave inside this string liquid? It's very simple, a density wave of a string. Some region you may have a more string, other region have a less string. Okay, and then because it's a string, so string have a direction. So therefore, to describe string density, we need a so-called a vector field. So here you have more string in this direction, there you have a more string, but in that direction. So there's a vector field to describe string density. And this vector field is also very special because the string density can only change in the direction perpendicular to the string. Along the string density cannot change because in order for string density to change along the string have to end, have to break. If string do not break, always form loops, then along the direction string, the density cannot change. But in the direction perpendicular to the string density can change, which is really this picture. You can, in the direction perpendicular to the string, density can change. Mathematically, it's really say that this vector field is divergenceless. Actually, that's one of Maxwell's equation. The electric field are divergenceless. So actually, electric field in Maxwell equation actually is a string density. And so this kind of density wave naturally satisfies the Maxwell equation. Okay. So therefore, this long-range entangled string liquid naturally explain the origin of Maxwell equation. We don't need to view light as a fundamental. It's just a property of entangled qubits. If a qubit is entangled in certain way, like in this string liquid way, then we will have a Maxwell equation. Okay. So that suggests that maybe our vacuum is indeed a qubits ocean which entangled as a string liquid, and that's why we see the Maxwell equation. That's why we have a light. The light coming from entangled qubits in our vacuum. Okay. Then we can actually make the story even richer. The light is just electromagnetic interaction. We also have a weak and a strong interaction. They are described by different equation called the Yang-Mills equation. And actually, we can also produce this kind of a wave, Yang-Mills wave, which we just allow the string to connect, to branch and form. This is called string net liquid. And the how string connect encode the information so-called the gauge group and etc. And actually, string net liquid can go beyond even Yang-Mills equation. It's the most general string net configuration actually are described by so-called the fusion category, a very abstract mathematics, which seems start to enter physics. This category theory start to enter physics to describe this entanglement. Okay, so therefore, this string net liquid can be used to produce the weak and strong interaction. Okay. Then you may say, should I really believe this? Or maybe it's just a story. Maybe our vacuum is really not a string liquid. Maybe not string-like liquid. Well, if you believe this, our vacuum is string-like liquid, we can even explain the origin of electron and quarks. And so we don't need to introduce any new concept. Just a string-like liquid which produces light and weak interaction, strong interaction, also automatically produce electron and quarks. They are end of a string. You may say string is something extended. The end string are extended. And the electron quark are point particles. So they are not like end of string. You can see the string. But actually, when you have an open string embedded in the background of a closed string liquid, we don't see the middle part of open string. They are kind of blend in with the background of string liquid. Only the end string shows up. So therefore, when you have an open string in the background of closed string liquid, it's just like a two particle given by the end of a string. And this kind of particle interact with a string density wave, just like a charge interact with an electric field. And also, this kind of end string can even carry a very mysterious property called Fermi statistics. So I won't explain what is Fermi statistics, but just as it's an extremely mysterious property in quantum theory. But actually, it can be explained very naturally using end of string. Okay. So therefore, if you're using this kind of a qubits ocean point of view, actually we can explain the 7 out of 8 wonder. All the 7 out of 8 wonder can be viewed as a property of a highly entangled qubits. And however, at the moment, we don't know how to get the Einstein equation. We couldn't find the entanglement pattern whose deformation gave rise to Einstein equation. So we tried, but so far without success. Maybe they exist. Maybe we need something more fundamental change. So that's an open question. So according to this quantum information unification of a matter, or this new point of view, I call this new point of view like a second quantum revolution. So in this, the world view will be the space is like an ocean with qubits, and the qubits may be highly entangled in the way of a string-net entanglement, and this fluctuation for a string-net can give rise to photon, gluon. There's an electromagnetic interaction, and there's a strong weak interaction, and end of string is electron or quark. So this represents unification. Remember, the grand unification unify all 3 fundamental interaction. Weak, strong, and electromagnetic interaction are unified. And this theory is called the grand unified theory. And however, this qubit ocean theory is even unified more. They not only unify all the 3 interactions, it's also unify the interaction with matter. Electron and quark are unified with the interaction. Okay, so it's a grand square unification. So it's just so almost everything is unified, but except gravity. Yeah, we do have trouble with gravity at the moment. So therefore, this so-called second revolution unify many different things. It also have a new mathematics. That is here similar to Newton's time. Newton are facing curved motion. That's a natural phenomena. He had to invent calculus to describe curved motion. Here, what we are facing is a many-body entanglement. We have many degree freedom. They have lots of entanglement. They are really entangled. So then we are facing the issue of how to use a mathematical language or mathematical theory, or which mathematical theory describing many-body entanglement. That is the challenge we are facing. And you know, in the, sorry. So there's unentangled states. So we have many body states, like many qubits. There's a particular organization, very simple, called unentangled organization. Like a spin all pointing up, or maybe spin is up and down, up and down. So those are unentangled organization. And this kind of like a classical organization. This kind of classical organization is described by the symmetry and the group. So the Wegener introducing the group to physics with a lot of resistance. You know, physicists say we don't need a group theory. You know, only mathematicians need a group theory. And but now physicists embrace group theory. And however, when you're facing the long-range entangled states, the symmetry and the group no longer enough. We need something new, something different. And this different thing has to be the braid fusion hierarchy category, some kind of category theory describing this many-body entanglement. So, you know, usually we talk about the 4 revolutions. Usually mathematicians are ahead of physicists. When physicists discover a new phenomenon, the mathematics describing that phenomenon usually have been invented like 100 years ago. Except Newton's time, where the mathematician is not ahead of physics. And this time, it's about the same. You know, the hierarchical theory is still developing. So, so therefore, at the moment, this physics and the mathematics can develop together to try to understand the phenomena of many-body entanglement. And there's another, so in addition to unentangled organization and highly entangled organization, there's so-called short-range entangled organization. And in this kind of short-range entangled organization of quantum information are really described by, again, some modern mathematics called the group cohomology theory. So really, this the quantum entanglement is really a new phenomenon. And a lot of very abstract modern mathematics enter physics to describe this new phenomena. Yeah. Yeah. Here I'd like to point out that actually the 3 of the pioneers developing those theories are really in this room. And Kong Liang is in developed the hierarchical theory for the many-body entanglement. And Zheng Chenggu and the Xie Chen really developed a theory about this long-range entanglement, and also developed a theory for this group cohomology theory. You know, Kong Liang is kind of local; he's from Shenzhen, and Zheng Chenggu is even more local. He's from this Chinese University of Hong Kong. Yeah. So, so to summarize, that the matter and the space is coming from quantum information, you know. It's almost like the movie Matrix. In the movie, they describe this, the virtual world can be as real as a real world. But actually, this matrix is not quite right. What happens is that this information world is a real world. Our material world is a virtual world, you know. So matrix get it flipped. And so if you're using this picture, all these interaction Fermi statistics, and they all really reflection of a many-body entanglement. So that's how powerful many-body entanglement can be. And that's how powerful quantum simulator can be. Actually, quantum simulator can simulate everything, maybe even gravity. So we don't know. Yeah. Thank you.
Thank you. Next, I would like to introduce Professor Robert Huang, Huang Xingyuan. And he's a bright young star in the quantum information, and he contributes his groundbreaking work in the field of quantum mechanics, in the quantum machine, machine learning, has earned him international recognition. He's currently a senior research scientist at Google Quantum AI and a visiting scientist at MIT. He will soon join the faculty at Caltech. Professor Huang's work is characterized by a rigorous theoretical approach combined with experimental feasibility, where he investigates how scientists, machine, and future quantum computers could learn models of our quantum universe. He leveraged quantum information theory, quantum many-body physics, learning theory, and complex theory to address the following question. When can quantum machines learn and predict better than classical machines? How to accelerate and automate the development of quantum and physical science? What physical phenomena can classical versus quantum machines learn and discover? Professor Huang's research has the potential to revolutionize our understanding of quantum systems and their interaction with classical counterparts, offering insights that could lead to significant advancements in quantum computing and information science. His ultimate goal is to build quantum machines capable to discovering new facets of our universe beyond the capability of humans and classical machines. The title of his lecture is Learning in the Quantum Universe. Professor Huang.
Yeah, thank you so much for the introduction and also the invitation to attend this Future Science Prize Week. I'm Huang Yuan, and today I'll be talking about learning in the quantum universe, an emerging field within quantum information science. So as scientists, we all know that a central goal of science is to learn how our universe operates. And as we have seen, our universe is inherently quantum mechanical, and hence the ability to efficiently learn in the quantum world could lead to many scientific and technological advances. For example, if we can efficiently predict how a collection of molecules will interact with one another, then it can help us design better catalysts and pharmaceutics. If we can efficiently learn the topological properties of quantum many-body systems, it can also help us gain new insights into exotic quantum matter. And finally, if we can efficiently learn the inner workings on how to control quantum devices, it can help us accelerate the development of quantum technology that will advance sensing, communication, as well as computation. And hence, to accelerate and to automate the development of quantum science, it is very critical to understand how we can design better algorithms to learn in the quantum universe, which is the main topic of my talk. Because learning is going to play a big role in my talk, I would like to first start out by defining what learning is. So learning is a combination of the following information processing capability. First, there's going to be an unknown aspect of our universe that we would like to learn about. It could be the state of the quantum system that we're creating in the lab. It could also be an unknown dynamics happening in nature. It can also be the phase diagram of a material, etc. We receive information about this unknown by doing measurements and experiments. We then process these information to form predictive models, which can be a theory, like electromagnetic theory. It could also be a complicated model, such as a neural network. We store these models such that subsequently we utilize these models to make accurate prediction about the unknown in new scenarios that we are interested in. The overarching question of this field is the following. How can we efficiently learn in the quantum universe? And in recent years, the development can be broadly categorized into two directions. One is learning with classical machines, where we try to understand how we can utilize current technology, classical computers, etc., in order to learn in the quantum world. And then the second direction, we try to envision having advanced quantum technology and understand how using quantum machines can help us better learn in the quantum world. So let me begin with learning using classical machines. Here, some of the central questions include, what can classical machines learn? And also, if we have a classical machine that can learn, can they outperform classical machines that cannot learn? So while it's a priori not clear how to answer this, I would like to first start out by asking an even more foundational question. How can classical machines see quantum many-body systems? So from the talks by Professor Wen and also Peter Zoler, we can see that quantum many-body system can, in this crazy superposition over exponentially different classical states. And when a classical machine tries to see the quantum many-body system, it will cause collapse. And it would just collapse into one of the classical state. And hence, a priori, a classical machine is unable to see these enormous superposition and entanglement inside quantum systems. However, there's still hope that perhaps using a more clever learning strategy, a classical machines will be able to see all of that. But to be more precise, what do we mean by seeing? One operational definition of seeing is the following. We try to convert the quantum system into some classical representation such that that representation accurately captures many properties of the quantum system. And hence, the classical machines, even though it cannot see the quantum system in its original form, it can just look at this classical representation in order to understand, reason, and manipulate the quantum system. The standard approach for learning or seeing quantum system is known as quantum state tomography. The idea is to learn the standard canonical representation of a many-qubit state. And for those of you who have taken quantum mechanics or know a little bit about it, this canonical representation is known as the density matrix, and it's an exponentially large matrix. It's of size 2 to the n by 2 to the n with certain constraint. And because we're inherently trying to learn and to see this exponentially large matrix, even the optimal protocol will require a resource that scales exponentially in system size for all of its different aspects. For example, sample complexity, also known as how many measurements do we need in order to learn the state, grows as 2 to the 2n. And the memory storage, the classical post-processing time, all of that grows exponential in system size. So while quantum state tomography, which has been around for many decades, have been very useful for the early stage of quantum technology, because at that stage, people are just trying to build and control a few qubit system. In the current era, the experimentalists have been able to create a few hundreds or even a few thousand qubit. And in those cases, if one plug in the number, if n equal to 1,000, then 2 to the 2,000 is already way beyond what we can capable of doing. And hence, we want to have something that's much better than quantum state tomography in learning and seeing quantum systems. So ideally, what we want is the following. We want to find a provably efficient procedure that allows us to do the following two steps. First, it will learn a classical representation of this state by performing a small number of measurements that do not scale exponentially in system size. And then our hope is that this classical representation accurately captures a huge number of properties of the original quantum state, and hence by looking at that representation, we can know and understand anything about the system. However, note that, as we have seen, if the goal is to learn the canonical representation or density metrics or wave function, one requires an exponential number of experiments. And hence, to achieve this, we have to move away from the standard description that we learned from quantum mechanics. We have to find a more succinct and more efficient classical representation that allows us to describe quantum system. A priori, it's not entirely clear how we will be able to do so. However, luckily, 4 years ago, together with Richard Kuhn and John Preskill, we stumbled across this surprisingly simple yet powerful formalism called the classical shadow formalism that allows us to achieve what we want. Particularly in this work, we proved that for any quantum system, a classical machine can learn a very efficient and succinct classical representation of the quantum state by performing only a few number of measurements. And furthermore, this classical representation accurately captures a wide range of properties of the quantum state. For example, if one plug in a number, we set m to be, say, an exponentially large number, and we can see that the number of measurements is still only linear instead of exponential. And hence, this classical shadow formalism allows classical machines to see and understand quantum systems. And furthermore, this is not just a theoretical concept, even though originally we proposed it to be, but can actually be done easily on a lot of experimental platforms, and there have been a lot of demonstration utilizing this new framework to describe quantum systems. And one of the reasons is because the procedure is actually very simple. All we have to do is the following steps. In each measurement, we sample a random quantum evolution, also known as unitary, that scrambles the quantum system. Now, after that, what we would do is we would measure the system, causing it to collapse into a classical state. So after scrambling, the quantum system will be in a superposition over exponentially many different things. Now, when we measure, we would just see one of the classical state. And then what we do is we store this classical shadow, which is given by applying the inverse of the quantum evolution to the classical state that we got. So for those of you who are kind of careful, this classical shadow is still a quantum state. However, we are going to restrict ourselves to quantum evolution that is easy to simulate on classical computer, and hence this representation Si can be stored efficiently on classical computer. Broadly speaking, one can understood this measurement procedure using the illustration shown to the right. We can think of a quantum system as this very high-dimensional object. It's an exponentially high-dimensional object from a classical perspective. Here, it's just shown as a three-dimensional object. Every time when we do a measurement, what we're doing is we're essentially looking at this quantum object from a random angle determined by this random quantum evolution, random unitary U. And we are going to project it into the classical space, casting a shadow in the classical space. So if we do it for once, it's not going to be very helpful. However, if we do it for a few times, then suddenly we can start getting a good sense of what this exponentially high-dimensional quantum system actually is. And by looking at these classical shadows, one will be able to see and understand quantum systems. And then, utilizing this intuition, one can combine it with theory of machine learning, as well as high-dimensional probability and quantum information theory to establish this theorem shown here. And over the past 4 years, our community has really found a lot of very exciting and creative application of this new classical representation for describing quantum systems. One of the more direct application is in benchmarking quantum systems. So note that quantum systems are extremely fragile. Even just a tiny bit of heating up or some photons coming in can just completely destroy the quantum system. And hence, in practice, in developing quantum technology, it is very important to be able to efficiently check how good our quantum system is. And that's known as benchmarking. So for example, on this plot shown to the right, the x-axis corresponds to the probability of error that is happening to our quantum system. And the y-axis is the fidelity. So a fidelity of 1 is the best, while a 0 is the lowest fidelity. And as we can see, as the probability of error increases, the fidelity would go down as estimated. So the correct behavior is given by this dotted line. And as we can see, using this classical shadow framework, one can accurately predict this property due to the rigorous guarantee. Here we also compare it with a very powerful heuristic known as neural network quantum state tomography, where one tried to utilize deep learning models to learn quantum systems. While this method works in many cases, in some cases, it can fail very miserably due to the neural network hallucinating, as one might have already seen a lot of times when playing with LLMs. But here, for example, we can see that the fidelity that the neural network reporting is much higher than the true one. And hence, it could give a false confidence to the experimentalists, causing them potentially to make incorrect scientific claims. However, by utilizing a rigorous protocol, one is able to avoid that. The community has also been using classical shadows for doing quantum simulation, such as the simulation of complex molecules. In a paper published by Google Quantum AI in Nature in 2022, Huggins et al. Were able to simulate some complicated molecules using an advanced hybrid quantum classical algorithm. And in their protocol, they require extracting a huge amount of properties from their quantum system in order to guide a classical algorithm running on the side. However, if one just do it naively, then it would take an extraordinarily long time. They were able to utilize this classical shadow formalism to first construct this classical representation and then predict all of its properties from that classical representation. More broadly speaking, classical shadow can be thought of as a new way of converting quantum information to classical information. So if there is some quantum system we would like to understand, we can apply this tool, do these randomized measurements, create these classical representation, and now we can apply our favorite classical computational techniques in order to address the quantum problem. For example, by combining classical ML and classical shadow, we were able to provide a provably efficient algorithm for classifying quantum phases of matter, as well as predicting ground states of quantum many-body systems, as I will briefly talk about soon. So now, after answering this question, showcasing how classical machines can actually see into quantum system by casting these classical shadows and by analyzing these classical shadows, we can now move on to a more ambitious question. Can classical machines utilize its ability to see quantum system to learn from quantum experiments in order to solve some very challenging problems arising in quantum physics and hopefully yield better solutions than any non-machine learning algorithm, establishing an advantage of ML versus non-ML algorithms in a physically relevant setting? So that's what we essentially looked at in this paper published in Science 2022, where we considered the problem of predicting ground state, which is one of the most ubiquitous problems in quantum physics, dating back to 100 years ago, when quantum mechanics was just emerging. So in this task, we're given some parameters that describe a physical system, and note that every physical system is a quantum many-body system. So the parameter describes a quantum many-body system, and our goal is to predict the ground state of that physical system, the lowest energy state, the most stable state. And this problem has been well studied for a very long time, and there are a lot of evidence showing and proofs showing that this problem is very hard for classical algorithms. And one of the reasons is because classical algorithms cannot really simulate and process quantum systems very well. However, one can still ask, is it possible that even though classical algorithm fails, classical ML algorithm can still do something useful for this task? In order to train classical ML algorithm, we have to feed it with some training data. One natural choice is the following. We just give him a bunch of existing physical system and the corresponding ground state. But then one could immediately ask, the ground states of a quantum many-body system is a quantum state. So how do we give a classical machine a quantum state? It cannot process that. And here's classical shadow can just be directly applied. In order to feed it into classical machine, we just first turn the quantum system into its classical shadow representation, and then the classical machine will be able to process that and learn from it. And the hope is that after learning from these training data, the classical machine learning algorithm would be able to predict the ground state for a new physical system that it have never seen, we have never created in the lab, and in a very accurate manner. So now let's go back to a more rigorous statement for classical algorithm. Using standard complexity theoretic techniques, one can prove that no randomized classical algorithm can achieve a good prediction error, a prediction error less than or equal to 1/4 within polynomial time. Meaning that if one has write down a classical algorithm that runs in polynomial time, which is efficient, then the prediction error must be greater than 1/4, which is pretty large. And this is true even when one restricts the classical algorithm to only apply to, say, 2D material or 3D material, etc., under various restrictions. However, what we found was a seemingly contradictory theorem, which states that even though classical algorithm cannot solve this problem, we can write down a classical ML algorithm trained with data that can achieve a prediction error that's much lower than 1/4, using just a small amount of training data and an almost linear computational time. And this classical ML algorithm works in any constant dimension, meaning that it can work in 2D material, 3D material, and work in regimes that's much broader than the classical algorithm fell on. And hence, together, the proposition and the theorem showcases this strange conclusion, where one can rigorously prove that a classical machine learning algorithm can predict ground states of new physical systems much better than any classical algorithm. So one might ask, how is that possible? How could this be? Aren't classical ML algorithms just a type of classical algorithm? How can they be more useful than these broader family of algorithms? And if one look closely at the inner working of classical ML algorithm, one will see the answer. The answer is that a classical ML algorithm can learn from data, and all it has to do to solve problem is to generalize from data, which can be much easier than computing everything from scratch. And in one of our previous paper, Power of Data in Quantum Machine Learning, we proved that data contains computational power. For example, nature is operating quantum mechanically, and hence if we learn from experiments, we will gather some quantum computational power from nature. And hence it can improve the computational power of those that learn from it, yielding a complexity theoretic diagram that looks like this. So here, each circle corresponds to the set of problems that can be solved by either classical algorithm or quantum algorithm, and classical ML algorithm trained with data. And essentially, if classical ML algorithm is able to obtain data that is not efficiently generatable on quantum computers, then it will be able to solve problems that's beyond both classical algorithm and quantum algorithms. Together, these results show that classical ML algorithm can indeed perform much better than any non-machine learning algorithm, and classical machines are actually quite powerful in seeing and learning in the quantum universe. Now we would like to move on to the next part, which is, what about learning using quantum machines? If in the future we have a very powerful quantum computer that can learn, can these quantum machines learn faster and or predict more accurately than classical machines? To answer this question, we have to first define what we mean by a classical and quantum learning machine. And that can be kind of abstractly captured by this notion called classical learning agent or classical agent and quantum agent. So the classical agent can learn about our world by receiving classical information through measurements, processing these information using classical computers, and storing the information after processing in classical memory, and utilize these capabilities to learn and make prediction about our universe. In the future, as quantum technologies start to mature, we can imagine giving rise to these powerful quantum learning agents, or one can intuitively think of them as a powerful quantum AI model, that can receive quantum information from our world using quantum sensors, process them using quantum computation, and storing them in quantum memory. And given this dichotomy, one can now ask the following question. Can quantum learning agents, or quantum machine, yield an exponential quantum advantage in learning about our world over classical agents? While this is a very important question for this field at the intersection of quantum physics and learning, I would also say this question is of much broader interest, because this question is equivalent to asking if in the future, whether quantum technology can fundamentally alter our ability to learn about our physical universe. Apparently, it's not clear that this should be the case, since we have seen that classical machines are even very powerful in learning to solve quantum many-body problems. However, throughout several recent works that combines ideas from theoretical physics, theoretical computer science, and random metric theory, etc., we were able to develop a new mathematical framework that allows us to establish and prove exponential quantum advantage in many learning problems, including predicting observables, uncovering hidden symmetry in the real world, learning approximate models of dynamics, etc. The one thing to note is that in quantum technology, a lot of times quantum advantage will die when there's noise in the quantum technology, in the quantum computer, for example. However, what we found was that these new quantum advantages actually can survive even in noisy quantum computers, supported by rigorous mathematical analysis in a work with Famiya and John Preskill, as well as demonstrated experimentally in collaboration with Google Quantum AI. So here I wanted to showcase some of the experimental demonstration on Google's Sycamore quantum computer, demonstrating the advantage in learning about states. So here on the plot shown to the right, the x-axis is the system size, how many constituents is in the physical system we would like to learn about. The y-axis is the number of experiments to achieve a good prediction accuracy. The gray crosses corresponds to the performance of the best known classical learning agent for learning physical systems. And as you can see, as system size grows, the number of experiments grows exponentially. The dashed line corresponds to a rigorous lower bound that can be proven utilizing this new mathematical framework that I described. That applies to any classical agents, meaning that even in the future, if we found some clever ways to learn physical system using classical learning agent, it will still be above this dashed line. On the other hand, the quantum learning agent that we implemented on Google's quantum computer provides a performance that looks like this, which at the largest system size that we looked at surpasses the rigorous lower bound by orders of magnitude, showcasing that quantum agents can learn much, much more efficiently than classical agents. Here's another demonstration on Sycamore quantum computer for the advantage in learning about dynamics. The goal here is to try to see if this learning agent is able to discover something on its own. And here the goal for the agents is to uncover some hidden symmetry in the physical dynamics. To both classical and quantum agents, they will be given access to a set of distinct unknown many-body dynamics. Half of a dynamic satisfy time reversal symmetry, also known as T-symmetry, while the other half are just some general random dynamics that's happening. And the hope and the goal is that the learning agents can just do experiments on its own, try to play with these dynamics, and at the end, in an unsupervised fashion, try to figure out and discover the hidden symmetry for these collection of dynamics. And as we can see from the plot to the right, the quantum learning agents is able to efficiently figure out in a purely unsupervised fashion that the collection of dynamics, half of which are time reversal symmetric, while the other half are just general dynamics. On the other hand, the classical learning agent fails to do so. And this is also supported by our mathematical theorems. And one can see that the classical learning agent is unable to uncover this hidden symmetry, and everything is just a big blob. So this provides a proof of principle experiment showcasing that quantum agent or quantum machine is able to discover things that are invisible to classical machines. And together, all of these results answer this question in the affirmative, showcasing and demonstrating that quantum machines can learn exponentially faster and predicting much more accurately than classical machines in learning about our universe. So together, all of these results paints the following picture. It shows that, first, utilizing clever techniques, classical machines can be surprisingly powerful at learning and making prediction in the quantum universe. Even though there are still problems that classical machines cannot solve, it can see a lot of things in quantum systems and solve some very hard problems after learning from experiments. However, we also see that quantum machines can be provably and exponentially more powerful in learning about our world. And finally, I would like to conclude my talk with the broad long-term ambitions that might not be achievable within 50 years. Maybe we need 100 years to do so. And these long-term ambitions are the following. First, we would like to build on what we have so far about learning, to continue developing our understanding of learning to accelerate and automate scientific discovery. And perhaps one day, we will be able to give rise to an algorithmic theory of science, meaning that we can write down a rigorous algorithm such that by running that algorithm, one will be able to discover everything that's left to be discovered in the scientific world. And if we can make some progress towards the first point, and then quantum technology continue to develop, in the future, maybe one day we will be able to build a quantum machine that is capable of learning and discovering new facets of our universe beyond what can be visible used by humans and classical machines combined. That's it for my talk. Thank you so much for listening.
Thank you. Now we are going to move on to classical world. Professor Li Kejia is a prominent professor of astrophysics in Peking University, who made significant contributions in pulsar research and gravitational wave detection. Professor Li completed his bachelor and PhD degree at the Peking University, and subsequently he was a postdoctoral research scientist at the Max Planck Institute for Radio Astronomy in Germany. As one of the founders of the Chinese Pulsar Timing Array, CPTA, Professor Li has played a critical role in advancing the field of pulsar timing and gravitational wave detection. His research focused on the detection of fundamental physical processes through pulsar timing, radiation mechanism, and relativistic plasma physics. Notably, his team published groundbreaking finding regarding the origin of repeated fast radio bursts, making several significant firsts in the field. Professor Li's dedication to understanding the universe through pulsar observations has positioned him as a leading figure in the quest to detect nanohertz gravitational waves, a challenging endeavor that has recently seen promising results. Professor Li received the 2022 Science Exploration Award, and the topic of Professor Li's lecture is Progress of the Chinese Pulsar Timing Array, which he will share his insight into the latest development in pulsar timing and their implication for gravitational wave astronomy. Thank you.
Hello, everyone. My name is KJ Li, and I'm now working at Peking University and Chinese Academy of Science National Astronomical Observatory. And although I'm the speaker today, actually behind me there is a big team working on pulsar timing array, Chinese pulsar timing array. So I will basically cover four major things today. First, why we want to detect nanohertz gravitational waves. For most of the time, gravity does not play any role, particular gravitational waves doesn't play any role in our normal life, right? Except that we fell off on the ground and break out the bones that relates to gravity. Besides that, we do not need the relativistic description of gravity or gravitational wave. But why we spend so much efforts to detect nanohertz gravitational wave? And the second thing is how we detect gravitational waves. It's a very long wavelength, low-frequency gravitational wave, how we make the instruments stabilize over a couple of years or probably 10 or 20 years. And the third, how is Chinese pulsar timing array is doing nowadays, and what will happen in the near future. Well, let's go from the first problem, why we want to detect nanohertz gravitational waves. If you look at the sky, in a dark place, you will see many, many stars over the sky in the night shining on the black patch of the sky. And people draw the picture about it, like this one. And all those stars you see in the nighttime are actually all close by stars, mostly. They are actually in our own Milky Way. Most of the stars, about 2,000 you can see in the night, if you have very good eyesight. That's all nearly in our own Milky Way. So that's the size of our universe? Probably not. Well, how large is our universe? Let me give you an example. You can hold a piece of paper, punch a small, tiny hole with your pencil with a diameter of half millimeter and pull the paper away from you for 1 meter away, and you look through that hole, what you will see, if you have very, very, very good eyesight. Well, what I expect, nothing is black, right? But actually, people do the experiment back to 2012 with Hubble telescope. This is what you will expect to see. All those bright little dots and fuzzy objects there are one galaxy, like our own Milky Way. So that's the size of the universe. If you continue to ask, beyond those things shining lights in the universe, where there are something else, the answer is yes. So suppose that this is our universe, the square box. Well, I do not know if the universe is a square box, but let's say that's our universe. And those material emitting lights or electric-magnetic waves are actually occupy that small, tiny portion of the whole universe. About 0.few% of the whole universe is those luminous materials. We know what they are, and we see them. There are a couple of percent of the material. We know the material. We know those are the material of daily life, like from the baryons, and those material is called the baryon contents of the universe. It occupies a couple of percent of the whole universe. And the next portion occupy about 30% of the whole universe, and we don't know what they are. We know it's probably material, and people doing experiment in the cave down in the earth to shed away the other particles, try to search for this particular kind of particles. People do astronomical experiment to verify the property of this particular type of material, and people call this dark matters. There are a couple of candidates people proposed to understand what they are, and so far we have no detection for the real particle of dark matter. But we know they must exist because the universe is what we see now, and if you want to get what you see now, you need to put this in your big model. How about the rest 70%? Huge amount of the universe. Well, we don't know what they are. It's probably just a parameter in the equation, or it could be something we call dark energy. We know the general equation of state for this material, but what they are, whether they are a field or constant or some type of particular particle, we don't know. So that's our understanding of the universe. Something we see, something we know, something we probably know, and something we're not sure if it's really something material or not. The key question is how those material or matters come from, and where they come from. How the universe forms the current structures. If you look at the universe, it forms some very linked network-like structures. How the universe forms this structure. How we can directly trace those material not emitting lights. Does our universe contain defects? Or it's just a smooth, continuous, four-dimensional something? Is our law of physics apply to the very early universe, at the time when the universe is very tiny and the temperature is very high, where the physics law we know today still apply there? That's a key question. And we try to answer those questions from observational side of views. Here is a general idea about how a universe are formed. At the beginning, you have a Big Bang, and after a very tiny period called inflation, it starts to cool down and the universe expand. On the way universe starts to expand, the particle appears and a material appears, and due to the gravity, material being attracted to each other to form structures, and stars and the galaxies are then formed. That's a general picture of our current universe. To explore the interesting physics, answering those questions I proposed one page before, you really need to look into the universe when it's at a very early stage. How can you do that? Well, for that particular area, you won't be able to see it because it's hide behind the dark age, we call. And how we can know the physics happens on that stage. There is one technique called gravitational waves. Gravitational waves are kind of a wave generated by the acceleration of mass or acceleration of energy. So there are many ways to detect gravitational wave from high frequency to very low frequency. At high frequency, on the ground, you can build laser interferometer, like ground-based interferometer called LIGO or Virgo, to detect the collision of stellar mass black holes. That generates a gravitational wave at a frequency about 100 Hertz. At lower frequency, when the period of the gravitational wave approach hours time scale, you cannot detect those gravitational waves on ground anymore. You have to go to space to have a much more stable environment. And in the space, if you have laser interferometry, you can detect gravitational wave down to a couple of hours. That time you will see the orbiting of the big black holes, and you can see a tail of cosmic string. What is cosmic string? I will explain later. At even lower frequency, the frequency of gravitational wave achieve a couple of years. The only known way to detect those gravitational waves is to utilize a celestial object called pulsars and use pulsar as a detector to search for gravitational waves. At this band, what you will see is you will see gravitational wave first astrophysically from those galaxies. And when the galaxy merge, there will be two big black holes in the center of the two galaxies. When they start to merge, you will see the orbiting and collision of the two black holes. That will emit gravitational waves. And those gravitational waves happens in the frequency band of post-timing array. You can also see something called cosmic string. It's a universe defect. Basically, when the universe is cooled down, you sometimes have the edges on the phase transition. You can either have dot-like structure, line-like structure, or a surface-like structure. For the line-like structure, we call cosmic string. And for post-timing array, it's right on the peak of the cosmic string spectrum. So we are able to see if they do exist, we were able to see the gravitational waves from the cosmic string. And if we are lucky, we will be able to see the residual gravitational wave from the quantum fluctuation at the very beginning of the universe. So as a short summary, nanohertz gravitational wave can directly probing the universe structure formation. It can provide a bridge to look into the early universe, and it's sensitive to the universe defects. And also it actually can do gravity theory test in the new parameter space to understand if our gravity theory works in different set of parameter space. Let me try to explain how we do that. So pulsars are discovered pretty new, actually. It was discovered in 1967 by Anthony Hewish and Jocelyn Bell. It's a star. We know it's a very small, we know the radius of the star is very small, it's about 10 kilometers, and the mass of the star is about 1 solar mass. It rotates, and it has magnetic field, so the radiation of the star is more like a lighthouse. So when the lighthouse sweep across your line of sight, you will see a bright pulse. That's exactly how the radio pulses are generated. And once on the Earth you have some telescope, you can measure the pulse and you can see those pulsars. Turns out that the pulsar rotation is very, very stable. Here I show you an example. Let's neglect the green and blue lines here, just focus on the yellow and red line here. The red line here is actually the stability of current international atomic clock standard. So the higher the value is, the more unstable the system is. So at a very long time scale, the stability of the clock ensemble gets worse. For pulsars, we can compare to the International Atomic Clock Standard and also figure out how stable those pulsar systems are. That follows the yellow lines. On short time scale, the yellow curve lies above the red curve, so you know that the pulsar is not stable compared to the clock. But on long term, it's very stable. It can go down like 10 to minus 15-ish compared to the 1 or 2 order of magnitude improve compared to the current atomic standard. Once you have so many pulsars spreading across the whole Milky Way, nearly all the pulsars we observe in this talk are all in the Milky Ways. And on Earth, you have some telescope to observe those pulsars. You equivalently have many, many very accurate clock on the sky, and you can measure those clocks. And by correlating the signal together, you will be able to differentiate the contribution of various of signal. Let me give you an example. Suppose you have 2 pulsars very nearby on the sky. You see them, and gravitational waves come by and perturb the space-time background. Then the 2 signals pass through nearly the same path, so the contribution would be similar. If you correlate the pulse signal you see for these 2 pulsars, right, you will expect to see the positive correlation here. Because of the symmetry of gravitational wave, it tends to squeeze the x direction at the same time stretch the y direction, and compress the y direction and stretch the x direction. Then at 180 degree, the 2 pulsars will do similar things, right? So if you correlate the signal from 2 pulsars 180 degree apart from each other, the correlation coefficient would be still positive. But for 2 pulsars 90 degree apart from each other, you compress the y direction, you stretch the x direction, and you compress the x direction, and you stretch the y direction. So the 90 degree correlation would be negative. So this very specific curve, like this shape, is called Hellingsand-Dance curve. If you find this correlation, you know that there is a gravitational wave like quadrupole correlation in your data sets, and you can use that technique to detect gravitational waves. Similarly, if your clock is not stable enough, you will see all the pulsar signals start to become late or earlier, and the correlation is angular independent and be of positive values. If your Earth position or telescope position is incorrect, then you have this blue curve. It's called dipole correlation. You have positive correlation at 0 degree and negative correlation 180 degree. So you can separate different systematics. And because of using the same argument, we get the Hellingsand-Dance curve from the symmetry of how gravitational wave perturbs the space-time. By extend the possible polarization or the way gravitational wave perturbs the space-time, you can actually have up to 6 different types of polarizations. And that's not in the general relativity. That's in the gravity theory besides general relativity. For those polarizations, you can have extra 3 types of correlation. By looking at those correlations, you can immediately test the gravity theory itself, and it's model-independent way to test the gravity theory. You can directly check what is the allowed gauge degree of freedom for gravity theory by just looking at the correlation curve of pulsar data. You can also measure the gravity speed or graviton mass by looking at this shape of correlation curve. You can measure clock signal. You can measure position error. That will actually also have profound astrophysical implications. You can measure the clock. You can measure how the international clock ensemble behaves, whether the international atomic clock is drifting towards particular values. And we checked, indeed, the international clock ensemble clock is not that stable at the early time, 1990s, not 1990s, and stabilized after 2000. And there is a post-correction called BIPM time, and that's stable. So by using the pulsar data, we can show that the post-correction of BIPM is actually more accurate than the everyday you use TAI. And you can measure the solar system properties, because measuring the pulsar signal depends on the Earth's position, so you can figure out how the dynamics of the solar system really behaves. You can check whether there is unknown mass in the solar system by looking at the pulsar data. Here is the upper bounds. That's 1, 2, 3 sigma upper bounds. And within, say, a couple of AU radii close to the sun, we know that there is no planets, a dwarf, rock, or small black hole, cosmic string loop, or alien spaceship heavier than 10 to the power of 20 kilogram. Otherwise, we will see the signal inside our pulse timing data. We can measure the acceleration of our galaxy inside the Milky Way. And that's the ultimate, that's the best thing we can do one day once we have good enough data. And that time we'll be able to see how the sun is being attracted by the nearest stars. In general, different gravitational wave detector cover different bands. And pulse timing array cover this low frequency band called nanohertz band. And the frequency, the period of the gravitational wave is roughly on time scale of years. And because of this, from about 2000, various of international pulse timing array collaboration are formed aiming at gravitational wave detection. The first formed pulse timing array is actually the PPTA about 2004. And then nanograph and the EPTA. EPTA have some historical data, so that's why their data trace back to 1996. Indian PTA and South African PTA are emerging PTAs. CPTA formed actually very late at 2019, once the FAST telescope is running. So how CPTA is doing? CPTA has actually some long history. Back in 2003, Dr. Wang Shouguan here, he proposed to build a 15-meter telescope in Miyun, close to Beijing, to initialize the Chinese pulse timing array experiments. The telescope is built, everything is found, goes smoothly, but later astronomer doesn't have a chance to use that telescope. The telescope is being used for other purpose. 2009, we tried to implement the pulse timing array proposal in the FAST project, and that became one of the key drive to build the FAST telescope. And 2010, we started to use a small dish in Kunming, 40-meter radio telescope, to understand how to do high-precision pulse timing. And that time, we tried a lot of things, and we get microseconds timing precision. It's good. We get all the experience and technology ready, but compared to the other data on the international market, the timing precision is still very bad. So April 2019, FAST started to experiments pulse timing observation, and the second day after we do the experiment and process the data, exactly the second day, we formed the second Chinese pulse timing array collaboration meeting, and we agreed to finally form the CPTA collaboration. We want to use FAST to do pulse timing experiments and to catch up the gravitational wave. We put this figure in the proposal that's basically tell you how much signal-to-noise ratio of gravitational wave detection you will have for how long observation you took. In 2020, the proposal gets granted, and we start observing. So how FAST helps here? Those telescopes, the size of the telescope here are drawing in scale. So that's FAST, that's Arecibo. Equivalently, the FAST collecting area is equivalent to the summation of the rest of the telescope observing pulsar of the planet. So with a better signal-to-noise ratio, you can do better calibration. And if you have any systematics, it's easy to spot and mitigate. And it's also easy to spot mistake and track down the problems. With this big telescope, things move really smooth. 2003, we performed the first release of CPTA, and that's a data coverage across, say, 3 years time scale. Those are the pulsars we see. Basically, those are the pulsars in the field of fast we can see, and we just observe them. And if you look at the timing precision of those pulsars, basically the timing precision is the fluctuation of these data sets. You can see for a significant fraction of pulsars, we achieved 100 nanoseconds timing precision. Some of the pulsars we can achieve tenths of nanoseconds precision. If you remember a couple of pages ago, the detection sensitivity, here the detectable regime would be 100 nanoseconds pulse timing precision for 20 pulsar observed for 5 years. And for fast data, we start to match that criterion. And even better, we have 56 pulsars are doing that instead of 20. So overall, the data quality compared to the international data sets, the data precision is improved by a factor of 4 to 50. And for each pulsar, I just plot the RMS error here on this plot. And after that, we do the parameter estimation. And 2023, 4 different teams, European pulse timing array, Parkes pulse timing array in Australia, and nanograph in North America. We publish a paper together at the same time. We get roughly the same amplitude of gravitational wave from different data sets. Different people using different telescope, analyzing different data sets, get roughly the same amplitude of gravitational wave. We didn't contact each other before we see the final results, so the agreement is astonishingly well. So for the CPT data sets, because the data length is still very short, we didn't catch up the spectral index of the stochastic background very well. And for longer data sets like EPTA or nanograph, they can actually measure the spectral index to some good precision. There is some indication that those gravitational waves are not purely generated from supermassive black hole binaries. There might be extra thing happens, like cosmic string or something else. The key thing is whether you can really confirm this is gravitational wave. To do that, you need to check the Helling-Sandans correlation. And the 4 different calibration actually see the correlation curve. That's from EPTA, that's from nanograph, that's from PPTA, that's from CPTA. Using different technique, slightly different technique, but we all see the Helling-Sandans correlation. Well, it's not vacant. We only get about 4 sigma-ish. But it's an indication that the Helling-Stans curve or Helling-Stans correlation is there, and the signal we see is really gravitational wave of nanohertz band. What will happen in the near future? So on the international view, we'll have a lot of new telescopes. VLA is starting observing pulsars. SKA is coming up. NGVLA is in the pipeline, and the DSA-20 in America is going to observe pulsar as well. The pilot program of the SKA called Meerkat is already observing pulsar, and their result will be published very soon. In China, we are also building something new. We are going to build 200-meter radio telescope, one in Xinjiang province called QTT 110 meter. And another is called JRT in Yunnan province. It's 120 meter radio telescope. We are building something called fast array. The first phase, we are going to build a 40-meter telescope, 24 of them. And we are trying to upgrade a low-frequency array called 21CMA to observe pulsars. This will help us to not only increase the sensitivity, but also increase the frequency coverage to help us to mitigate the interstellar medium systematics, and also increase the view of sky to have more pulsar being observed in the pole. So that's a 110 meter in Xinjiang. It's now in the construction phase. The foundation is already built, and the next year they will start to build up the frame and put the dish on. And for 120 meter telescope, that's an imagination plot. It's not been there yet. The construction green light is already granted. The real construction will start December this year. We will upgrade this low frequency array. It will have about 9,000 dipoles observing at low frequency. And the faster core array, the 40 meter dish for 24 of them, is already start constructing. All those things will happen in the next couple of years. So by different time, you have different frequency coverage to different sensitivity. That's a future of CPTA. What we expect, we will expect that the pulsar number is nearly doubled, so the sensitivity will have a boost somewhere around 2030. Well, sensitivity is not something very interesting, right? But then we will be able to measure the parameters of the stochastic background of gravitational wave to very high accuracy and start to learn the physics. And we will be able to see the single source. If we upgrade the system, we'll be able to see a bunch of single source probably, and we'll be able to see the localized individual supermassive black hole binary system. And if one of those belongs to the cosmic string, then we have the first evidence for the defects of our universe. Well, the conclusion is very simple. The pulse-time array is important for fundamental physics, particularly for nanohertz gravitational wave. The international efforts will systematically further increase the capability of several different pulse-time arrays. CPT is upgrading the observing system and get ready to meet the dawn of nanohertz gravitational wave astronomy. Thanks.
Thank you so much, Professor Lee. Please remain on the stage, and could you please proceed to the other side of the stage, Professor Lee? Thank you. Yeah, because we're going to have another exciting sharing section will be panel discussion. Could you please proceed to another side of the stage? The keynote speeches cover groundbreaking topics in quantum physics and cosmology. Themes include quantum simulations of atoms and ions, the unification of matter and information linking light and particles, exploration of learning within the quantum universe, and also recent progress in Chinese pulsar timing array research highlighting significant astrophysical advancements. So now we are going to have a panel discussion. May I invite our moderator, Professor Douglas Nelson Lin Chao. Let's invite our moderator. And our panelists including Professor Huang Yuan, Professor Li Kejia, Professor Wen Xiaogang, Professor Peter Zoler. So I may pass the stage to our moderator. Thank you.
Wow, what an incredible series of lectures, ranging from the smallest aspect of nature to the grandest design of the universe. And there is a connection. Would you like to, Peter, would you like to share your thoughts about the connection of this complexity and how can we make sense of it?
Okay, so we are building quantum computers on one hand, trying to get control of the microscopic, and the way that I sort of see that quantum computers are to some extent quantum sensors. And I see the connection with a big scale, just as what we heard in the last talk. Also that, we are building quantum sensing network, where we might be able to distribute entanglement we might be able, for example, to have not only satellites flying, but even on a bigger scale, some gravitational wave detectors. We could have atomic clocks that sense, for example, different aspects of general relativity. And so I would say that the microscopic becomes a tool when we distribute it, when we distribute entanglement in the long range sense, to discover something that happens then on these microscopic scales.
Thank you, Peter. Xiaogang, would you like to share your thoughts as well? How it connects to condense, well, all the different aspects of the 8 wonders, plus your question mark with regard to gravity.
Yeah. We usually think of those some interaction, Fermi statistics, like fundamental properties. Now in the quantum age, looks like they could be the emergent phenomena. And this point of view actually may have experimental predictions. For example, one prediction is that our universe may have additional cosmic string if the fermion coming from qubits. If you assume fermion is fundamental, then maybe there's no actual cosmic string. If a fermion is emergent from qubits, there must exist additional cosmic string. And then this pulsar timing measurement probably can detect the gravitational wave from the cosmic string. So all this microscopic quantum point of view and this very macroscopic astrophysics point of view actually somehow have this amazing connections. So I'm very happy to learn that. Yeah.
Professor Robert Huang, could you share some thoughts on how AI may enable us to make further advancements on both the quantum world and as well as the global physical world?
Yeah, so in a way, when I talk about the things, learning in the quantum universe, of course, a lot of the talks that I covered was about learning microscopic objects, but we do believe that in the coming future, quantum technology can also play an important role in, say, gravitational wave detection. For example, in the experimental, which is different from this pulsar timing array, but these LIGO experiments, they were already now trying to utilize, say, quantum sensing strategy to enhance their sensitivity in order to better understand these fluctuation in space-time. And in the future, I don't know what the timeline would be like, because I think there's still yet to be explored. It does seem like if we can place, say, a small quantum computer next to these experiments for detecting gravitational wave, there is a possibility that one would be able to hopefully detect fundamental physics that would be invisible to us if we don't put the quantum computer next to it. So many of my collaborators have been exploring that possibilities, and so far we only have proof of principle results, but it does seem like that is there is a potential future in having quantum machines that try to learn from these gravitational wave signals in order to better understand about our universe.
Thank you. One thing that I walked away with an impression from Xiaogang's discussion, that information is reality and particles are, perhaps more virtual. How could gravitational waves from the earliest epoch of the universe, Professor Lee, give us a sense of reality from the information that you have obtained?
So this is a good question. Today, when I listened to the talks before my talk, I'm surprised, actually, because Professor Wen asked nearly the same question as we ask at a very large scale. But the basic question is the same, how the matters come from, and how the universe evolved to the current structure. This question, in terms of condensed matters physics, seems to be the emergent phenomenon. And for us, we are observers. We merely see this phenomenon and try to figure out what the process happens inside. We are trying to search for the universe topological defects called cosmic string. That's exactly what Professor Wen has just talked about. And also, surprisingly, I realized that since the universe is a big quantum computer, right? And we are actually just building the readout circuits.
Before I continue further with regard to the panel discussion, perhaps the audience may like to raise some questions that these world-leading experts could provide you with some thoughts. Are there any questions? Yes, please. Back there. Further back. Yes, please.
Good morning, professors. You all are so amazing and wonderful. So I'm not from the science background, but I would like to ask something more emotional or intuitive. So, because I have been reading a lot of those synchronicity, quantum physics, quantum entanglements in the past years. Because something happens with the synchronicities, which drive me to this search for the answers. Why something happens on the same day, and because it's about life and death. Because someone is happy, but someone died at the same date. So simply with these questions is drive me to this journey, and I found a lot of inspirations and answers today. So my question is, do you think that the collective consciousness of human, plants, and animals is part of the quantum computing? Can quantum computing, because it's from artificial intelligence. The value of artificial intelligence is to find out the human intelligence. And also, on top of human intelligence, there's the natural intelligence. So I think the true value for me on quantum computing, all these huge efforts that every scientist is building on, is to elevate the human intelligence. That's the ultimate goal. So how to use these tools to study more about the collective consciousness of human, plants, and animals, everything, even bacteria. So this is my questions. Thank you.
Thank you so much. Would you, Peter, would you like to share some thoughts first, maybe?
I can try to. So, thank you for this very interesting and to some extent deep and also challenging question. I have colleagues, that study, for example, the relation to what extent, the function of the brain or maybe bioscience in general is related to entanglement. And there's some very concrete thoughts about, say, the bird compass, that we have, to what extent quantum effects might, for example, enhance the possibilities in, biological systems or in animals or us, to achieve something better, like being more precise, like this quantum compass that we have in birds to sense, for example, magnetic fields. To what extent we can talk about notion of consciousness and so on. This is something much more challenging, and maybe Robert wants to say something along these lines.
Before that, I just want to note that Professor Zoler's home country is Austria. This is the wonderful country that actually contained two great minds, both Schrödinger and I assume Schrödinger, and Boltzmann and Sigmund Freud. And so maybe the question is combining Sigmund Freud and the concept of quantum information. Huang, would you like to share some thoughts?
Yeah, there are two aspects. One is whether two well-separated human beings can sense each other's emotion states, which probably not. But on the other hand, there's a very interesting question about whether human brain is a classical computer or quantum computer. This is a very, very important question. And one thing I like to say that I think we feel we have free wills. You know, if we want to do something, we'll do it. But this thing is very strange from a physics point of view, because physics, all the phenomena follow equation motion, so they're all determined by your past. So that seems against the free will. So I personally, I always a puzzle whether free will is something beyond the classical physics or not. But on the other hand, as a condensed matter physics, it's harder to imagine the human brain have a quantum entanglement effect, because the temperature is high and there's a lot of decoherence. But on the other hand, I think there's a serious consideration whether the human brain actually can have some quantum entanglement effect. In a sense, maybe some nuclear spin may have maybe really quantum. And so there's a serious research to see whether some nuclear spin entanglement nuclear spin can modify the chemical reaction, and then that may have some effect. But this is really a kind of open question. So we're also wondering what's going on.
Okay, Professor Huang, you have thoughts about interface between human learning, machine learning, and artificial learning, and quantum information.
Yeah, I mean, that's basically what I work on, but I would say that right now I don't think there's an operational way to test consciousness. Like, I've been reading several interesting articles about how one can experimentally test if a human is unconscious or conscious by looking at their brain waves. But I would say right now I don't think there's still a very solid scientific foundation for that. And hence, oftentimes it's quite challenging to combine these subjective experience of consciousness to scientific experiments such as quantum experiments, etc. I do wanted to say that actually, so I'm currently part of Google Quantum AI, who the leader is Hartmut Neven, and Hartmut he's very excited about this possibility that maybe quantum physics and consciousness can really be related to each other, and we can really answer some of the big open question in consciousness using ideas from quantum physics. In a way, I think that's how he decided to start this Google team that tried to build quantum computers, so we can now simulate, say, these learning agents within quantum computers and maybe try to test if they're being conscious, how can they learn, and all of these things. But so far, I would say that's still at a very, very early stage. Because especially the subjectiveness, like there's this famous philosophical thought experiment which says, I'm conscious, like I can feel I'm conscious, I can see all of you, but how do I know if you guys are all conscious? Maybe you are all unconscious. So how can I tell that apart? So we need to somehow find a way to answer that. But interestingly, there's these also a very famous experiment in quantum information science called Wigner's Franz paradox, which has this notion of subjectiveness. Like you can have an experimentalist or a person that is looking at another person, and then that person is doing some experiments, and now the person measures certain things, but now I look at that whole system, and they would still just be in a big superposition. And if I try to measure them, I would get entangled in it. And if there's another person that tried to look at this, it would not see that I have this subjective experience of looking at certain experimental outcome. And they were able to formulate a very fascinating paradox that I would say in the quantum foundation, which is a subfield within quantum information science, try to better understand. So there's these recent works by people in ETH Zurich. I know Renato Renner was a very big proponent or like a big scientist exploring that frontier. I don't personally know that much, but it does seem like quantum physics provides these notion of subjective experiences that might be related to consciousness. But I would say right now it's still very unclear.
Thank you. Perhaps a couple more questions. You have a very eager hand. Please. Turn on.
Yeah. All right. Thank you so much. Thank you all for these amazing presentations, and I really learned a lot from by taking notes and watching the slides and hearing your speeches. So I don't have a science background. I'm now working for a Chinese entrepreneur organization. So I'll ask all of these speakers like a few the questions about how the science will affect the business. Which industries do you believe will be deeply affected by the advancement of the quantum technology and science in the future? So, how would this technology influence the fate of humanity in the future? Thank you so much.
What about quantum communication? And Peter, would you like to share some thoughts?
Yes, I would say that one of the most, sort of close applications that we're already kind of in the middle, I would say at the moment, of all of these quantum physics and technology is, of course, quantum communication. I just want to remind you of the great experiments that are being done, even involving satellites, in China. Where we talk about, teleporting quantum states, where we talk about quantum cryptography. And these are things that we're able to do right now. And just, when you apply these things to the security on whatever level, I mean, this has immediate consequences. And I would say that, sort of extending these kind of ideas then, the possibility of quantum communication to network and also quantum computers that can start to talk to each other in some non-local way. I think all of them, I mean, they offer really completely new possibilities that we're just at the moment starting to explore.
Okay, thank you. Maybe we can ask some more questions. Back there, on the third row, please.
Thank you, Professor, for all wonderful presentations. I have a specific academic question. That is, how can we calculate the amount of information loss in the learning process of quantum systems? And after that, is it possible for the information to increase during the learning process? Thank you.
Okay, maybe that's a question for me. Yeah, so there are many different ways of talking about complexity in learning. There are many different notions. One of the most common one is known as sample complexity, which means how many samples, how many measurements, how many experiments do one need in order to learn. And in various cases, quite surprisingly, we can get a very good handle on that complexity. But in addition to sample complexity, there's also this notion of computational complexity, which try to characterize, if you wanted to learn certain things, how much computational time do you need? And that is oftentimes a much more challenging thing to characterize because computation is just a much more elusive object. But more recently, by utilizing ideas from quantum cryptography, we were also able to make progress in characterizing computational complexity. So there's sample complexity, there's computational complexity. One could also ask a lot of other things, like how much memory do I need in order to learn certain object, in order to learn to solve certain problems? And all of that have a lot of very fascinating different properties, and they all have different connection to one another. sometimes one can be very different from the other. For example, the sample complexity might be very small, but actually the computational complexity would be extraordinarily large. So understanding that, I would say also is a very important aspect of this intersection between learning theory and quantum information.
Okay, maybe the last two questions, okay? And maybe someone from the back there. Yeah, you. Don't turn around, right, you. Yeah.
Yeah, actually, I just have a technical question for Xinyuan. So you mentioned that classical algorithm can efficiently simulate quantum systems. So this classical machine learning algorithm, you mean based on the current developed algorithm, or maybe some new algorithm we should develop in the future? And of course, the second related question is that there's also notion of quantum machine learning. So do you think quantum machine learning can also be approximated by certain classical algorithm? Thanks.
Yeah, that's a great question. So the first, classical algorithm cannot simulate quantum system very well. That's also one of the results that I mentioned. What I was talking about was more like these classical machine learning algorithms that can learn from quantum experiments. And the reason that it can suddenly solve problems, quantum problems that classical algorithm cannot, is because in a way it's like inheriting computational power from quantum experiments. And that was one of the reasons why they can solve that. And I would say, in a way, like I guess the first question was, is it something that we can already do now, or we still need to develop it further? I would say a lot of things can already be done now. Like the algorithm that I was talking about, when I say there exists a classical machine learning algorithm, we actually write down the algorithm and we also tested it numerically, seeing that it can do a lot of wonderful things. So a lot of those I would say, can already applied using current technology. But I do believe that there's going to be further development that would really enhance the power of classical learning algorithm to solve quantum problems. And can quantum machine learning algorithms also be simulated by these classical machine learning algorithms? Some of them, yes. Some of them, actually, that was one of the key message in this Power of Data in Quantum Machine Learning paper that I very briefly mentioned. But one of the results there is that certain quantum machine learning algorithm, even though it's hard to simulate by classical algorithm, when we now use classical machine learning algorithm, it can actually simulate them. So some of them, yes. And that also builds a stage for why we then start to think, are there cases where we can just prove that this quantum machine learning algorithm would just not be simulatable by any classical machine learning algorithm? And that leads to some of the results that I talked about towards the end of the talk. So that's right.
Thank you. One last question. Okay. I'm trying to spot maybe a lady somewhere, but that's okay. Maybe you raise your hand several times, right? So I could just give you that last chance. My apologies that the time is limited because there's a short lunch break. So,
thank you so much. Thank you, our guests, to give us wonderful talks. My question is about, I'm in physics and math background, so my question is to Dr. Wen Xiaogang. The question is about the cubic oceans to describe the universe. So I saw from your PowerPoint that the model, we have the string, we have the open string and closed string, and we have the string to net interactions to model for the fundamental principles. So my question is that how about boson? Because in your presentation you have the Fermi statistics. My question is about whether how can we do boson statistics so that it will related to the collection of mass and then the long-range mass effect and then the gravity. So my wonder is how about to create the boson statistics from your hypothesis? Thank you.
Yeah, the boson statistic is kind of easy in a sense, like in the qubits ocean, you can say if a qubits O equal to 0, that's a background, there's nothing. The qubits 1 represent a particle. And this qubits 1 can move around. So this qubit is equal to 1, or that qubit is equal to 1. So that representing this, the 1 representing particle representing, actually that represents the boson. So this is 1 moving around actually corresponds to boson moving around. So actually without quantum entanglement, we already have a boson, and those bosons are already identical particle. So that's quite impressive, because the notion of identical particle is pretty strange from classical point of view. But from the qubits ocean point of view, it's very natural. We can only have identical particle. But however, at the beginning, physicists thought we can only have identical boson. So the qubits ocean cannot simulate a fermion, and also cannot simulate a photon. Photon is a very special boson, you know. And so people struggled that for 100 years, you know. After Maxwell already tried to imagine something which is either produce a light wave, but it's not quite working. And so only recent years, when we study quantum system, quantum entanglement, we find that, yeah, not only qubits not only can simulate, this quantum simulator of a qubits not only can simulate the boson, but can also simulate the fermion, and also simulate the photon, which is gauge boson. You know, Professor Zoler talked about simulate the gauge, lattice gauge theory. It's really simulating the photon. And so more generally, if we can go further, we can even simulate the so-called SU2 gauge theory, the Yang-Mills gauge theory, or some other things. And I also want to say that the qubits not only can simulate Fermi statistics in 2 dimensions, they can also simulate so-called fractional statistics, or non-abelian statistics, something not existing in nature, but possible allowed by mathematics. So this more weird thing can also be simulated. So actually, this will be the one of frontier research, either using quantum simulator to simulate or discover something more exotic effect, not in the nature, or maybe you can build synthesize some quantum material, which gave rise to this fractional statistics, non-abelian statistics, and etc. Yeah. So this so entanglement really have a lot of to offer. Thank you.
Thank you so much. I just want to thank our wonderful, inspirational speakers for this morning. And there's a lot of thought-provoking ideas to take home with, and maybe you can chew on it over lunch. And I will hand it over back to our presenter.
Once again, big hands to our panelists and moderator. Really stunning and exciting sharing. Thank you so much. And now may invite all the guests, please rise. We have video together. Let's stand closer to each other, then we can have the best photo. Okay, now please, let's stand in one line and then have a look to the center, please. Yeah, I know time is limited, and thank you so much for actively asking questions. I believe you all learned so much. Okay, thank you very much. Thank you so much. So this is the finale of this session. We are about to have lunch. So those who register for luncheon, please follow the instruction from our helpers to the venue. We will see you again at 1:30 with different keynote speakers with different insightful topics. See you at 1:30. Thank you. Distinguished guests, ladies and gentlemen, welcome back to our Science Symposium. I hope you enjoyed the lunch. And their upcoming session is Mathematics Sessions, Insights into Mathematics. For this session, I would like to introduce with you Professor He Shuwa as this session's convener. He is Chair Professor and the new Cornerstone Investigator, Department of Mathematics, the University of Hong Kong. Member, Program Committee of the Future Science Prize Week 2024. Let's put your hands together to welcome Professor He.
Good afternoon, distinguished guests, ladies and gentlemen. So glad to see you in Hong Kong. It's my pleasure to be the convener today. First, I would like to extend a welcome to all of you and my gratitude to all speakers accepting our invitation. The topics of today's section is Insights into Mathematics. I hope that today's speech and the panel discussions will offer you profound understanding and stimulate thoughtful conversation about mathematics. First, allow me to introduce our first speaker, Professor Jen Ding from Peking University. Professor Ding has made significant contributions to the field of probability theory, emphasizing its interaction with statistical physics, theoretic computer science, and statistical learning theory. He is the laureate of the 2023 Nobel Prize in Probability. He's going to deliver his speech titled A Glimpse at Statistical Physics from Population. Through examples, he will describe various population models in statistical physics, with emphasis on phase transition, critical phenomenon, as well as disorder efforts. Let's welcome.
Thanks for coming, and thanks for the invitation and a very nice introduction. It is a great pleasure and honor to speak on this occasion. Today I'm going to tell you something about statistical physics from the perspective of population. So what is statistical physics? Well, to put it in a simple way, basically the goal is to understand complex, macroscopic, and deterministic laws in physics via simple, microscopic, and stochastic mechanism. This subject, you see joint efforts from physicists and mathematicians. Usually, the physicists would provide very insightful predictions via non-rigorous derivations and numerical studies. So what do we mathematicians do? Most of the times, we regularize and clarify physicists' predictions so that we can give them a consolidated ground for further predictions. And occasionally, we can actually correct what physicists predicted. And in some occasions, mathematicians did discover phenomenon that has been elusive to physicists. This is a subject in its prime time. There are many interesting problems, and many of them have seen substantial progresses recently, which lead to major prizes in both mathematics and physics. So I'm only going to choose one facet of statistical physics to talk about today. It's an important facet, and the perspective is from population models. So what is population? The history of population is rooted from the coal industry. People are interested in the permeability of porous medium, i.e. Whether water can pass through some porous material. And experiments in 40s discovered that the permeability of this porous material, it depends on the temperature and also the type of liquid you are considering. In fact, population models are very commonly seen in the nature from the natural sinking of water into the soil, or whether fire forest is controllable or not, or the clustering structure of cells in the tissue. In fact, in everyday life, whenever you boil a cup of coffee, you are doing a small experiment of percolation. Now let's move to the mathematical side of percolation models. Canonically, when we talk about percolation, it refers to the Bernoulli percolation model introduced in 50s. It is perhaps the simplest model. It just says, say, on a lattice, every edge or every vertex is chosen to be open or closed with the same probability independently. So here, if an edge is open, it means water can pass through that edge. Then you can see, mathematically, the permeability of water corresponds to the macroscopic open clustering structures in the percolation model. Here are some illustrations for either bond or site percolation models on a few different lattices. Two of them are in 2 dimensions, one of them is in 3D. As I said, we care about whether water can pass through the material or not, and this corresponds to whether we have an infinite open cluster in the percolation model or not. And this is, as a result, this is the major goal in the study of percolation. Let's look at the Bernoulli percolation on Z2, because Z1 is the simplest, but it's kind of trivial. Z2 is the first interesting and non-trivial example, and actually has quite rich phenomena. So the fundamental question is whether there exists an infinite or macroscopic open cluster, or we can just ask whether there is a positive probability that the origin can be connected to infinite via an open path. An open path is a path so that every edges along the path are open. Then we can define this critical threshold. Clearly, this should depend on P, right? If you increase P, you should increase your probability of finding an open path. So we can define the critical threshold, PC, to be the infimum of the P so that this event happens with positive probability. Note that this event cannot happen with probability 1 because we're looking at the origin. There's always some probability that the origin is just broken already, or the neighboring edges are broken. Now we can wonder, what can we say about PC? We know it should be between 0 and 1, but is it strictly between 0 and 1? A moment of thinking leads to, okay, there should be some non-trivial lower bound. For instance, here's what we can do. Suppose we want an open path from the origin to the infinite. That means for every n, we should be able to find a self-avoiding open path of length n, starting from the origin. And for each such path, the probability of being open is just the p to the power of n, because we want all edges being open, and these openness are independent of each other. Then naturally you would wonder, how many paths of this kind you have in total, right? There should be some bound you can get easily, like 4 to the n is the simplest bound, because the degree is 4 for each vertex in Z2. But you can do a little bit better and get a 3 to the power of n, because a self-avoiding path naturally cannot be backtracking. That only gives you 3 possibilities for where you go next, for the next step. So you get 3 to the power of n is an upper bound. Then you put this probability calculation and the enumeration together. You get that, okay, PC has to be greater equal to 1/3, because otherwise a simple union bound or simple counting argument like this tells you that there's no way you can find the infinite open path. Now you would wonder, can we do better? Is 1/3 of the sharp threshold or not? There are 2 types of questions here, right? First, when we count the number of self-avoiding paths, is 3 to the power of n good enough? Is that sharp? 2, provided with a sharp estimate on the enumeration of self-avoiding path, can we get the sharp critical threshold via this method? Well, the answers to both questions are negative. Our bound on the enumeration of self-avoiding path is certainly not sharp, because we only consider that in one step you don't want to go back, right? But you certainly have to also avoid, say, small cycles. And every 4 steps you want to avoid a small cycle that should also further limit the number of choices for your path. this means that we didn't get a sharp answer for the enumeration of self-avoiding path. In fact, self-avoiding path itself is a very important and challenging model in statistical physics. It was proposed to model the polymers, I think by a Nobel Prize winner in chemistry. Its enumeration is also a very difficult problem, and only in a lattice, in two-dimensional lattice, like not Z2, but honeycomb lattice, this was solved by Dominic Kopan and Smirnov, both are Fields medalists. So that's the first comment. The second comment is, suppose somehow you can actually compute the exact enumeration for the number of self-avoiding paths. Can you use this method to get the exact critical threshold? The answer is also no. So basically, this type of counting method is a little too simple to tell you something about near-critical behavior. In all these statistical physics models in lower dimensions, if you want to understand what happens near criticality, you would have to find some more sophisticated methods than just the counting method I described here. Okay, and in a similar manner, you can also get an upper bound on PC. This basically by some sort of duality consideration. Just imagine now you want to grow your open set. And you want to say, if you want to confine this open set into a finite zone, at some point, all the boundary edges in your open set have to be closed, right? So you have to be able to find some sort of closed contour to surround your origin. If you just do some duality consideration, this would say, okay, you should be able to find some closed self-avoiding open loop in the dual model, and a very similar calculation to what we did above give you that if P is if P is larger than 2/3, then this would fail. So this says that PC has to be between 1/3 and 2/3. Now a natural wonder is, can we actually calculate the value of PC via some other methods, right? This is actually a quite difficult problem, and we can only calculate it in very special cases, basically in 2 dimensions. And I can tell you that on Z2, we know the answer. By we, I mean the community, not I. The answer is PC equal to 1/2. Here is a very rough heuristic, and we can see what is the flavor here. The first ingredient is some rotation invariance. This is not very hard. This basically says if you have a square box, the probability that you find the left-right crossing and the probability you find a top-down crossing, those are the same because the model is invariant if you rotate it by 90 degrees. The more sophisticated ingredient is again the use of duality. So here we basically used, implicitly we used the theorem from topology. In 2 dimensions, so suppose you have a rectangle, and suppose you draw one continuous path from left to right, and you draw another path from top to bottom. These 2 paths have to cross each other. This is a theorem from topology that we have used to justify the duality here. But there's a little bit thinking which is required to get what I'm going to tell you next. You may just choose to trust me during the talk. So basically, what is the special role of 1/2? Why 1/2 is so important, it's so special, and serves as the critical threshold? That's because 1/2 is exactly the point that the probability of being closed and the probability of being open are the same, so that you can couple the original model and the dual model together so that when 2 edges are dual to each other, one is closed if and only if the other one is open. And through this coupling, and also using the sort of topology theorem I just told you, and using a little bit trust on me, we see that if you can find a green crossing from left to the right, if and only if there is no red crossing from the bottom to the top. Those are the if only if. And then combining these things together, we see that the crossing probability is 1/2. Still, this does not quite prove 1/2 is the exact threshold, but this gives a strong hint. because this is exactly the point that the probability to cross through a square box is away from 1 and also away from 0. And finally, this was proved by casting in 80s using some more ingredients, which I'm not going to talk about. Now you see there is this simulation, which shows that as the P increases, how the open clusters in the percolation model evolves. If you have good eyes, you'll see that near the criticality, near P equal to half, there is emergence of a macroscopic cluster. If you don't have good eyes, I have the 3 screenshots to show you here. The first picture shows what happens at P equal to 0.4. You see there's only a very small open cluster. You can barely see if you sit at the back. Now, the second picture, when P is equal to 0.51, already there is a very obvious macroscopic cluster. And when P is 0.55, the macroscopic open cluster is basically dominating everything. So this says there is a phase transition. What do I mean by phase transition? We have a physical system, and in this case, there's one parameter, P here, we can adjust. Phase transition basically means, well, when you adjust the parameter just a little bit from below criticality to above criticality, then the macroscopic property of the system changes dramatically. Like here, you would change from no infinite open cluster to there is infinite open cluster. In fact, not only we have a phase transition here, the phase transition here is also sharp. What do we mean by sharp phase transition? It basically means that in the entire subcritical regime, that is, as long as P is strictly less than a half, not only you do not have infinite open cluster, but if you look at the open cluster of the origin, it tends to be very small. The probability for this to grow to into a large cluster decays very quickly. Actually, it decays exponentially. So we have a sharp transition for Bernoulli percolation. After describing the phase transition, now let's move to critical phenomenon. So a natural question is, at criticality, what happens? At criticality, do we have an infinite open cluster? This turns out to be a challenging problem. We know the answer for 2 dimensions and also for high dimensions. For high dimensions, that's because, according to physicists, if the dimension is high, then we are sort of in the mean field, so-called mean field regime, where 2 particles basically interact with each other in the same manner. The geometry does not play an important role, which is why we have the sort of mean field behavior, which is easier to analyze. Although to rigorize this is not easy at all, mathematicians have developed powerful methods like Lattice expansion to deal with the high dimensional behavior. But the most interesting behavior in lower dimensions, especially for d equal to 3, remains a major open problem in this field. Now, suppose we know the water can actually pass through the material. What are the other questions we would care from a physics point of view? I guess one natural question is, how much time does it take, right? How long does it take for the water to flow through the coal, for instance? Mathematically, this would correspond to the random metric generated by the shortest open path. In this simulation, we see the evolution of the metric ball. This is in the supercritical regime when P is like 0.51. Basically, I think we can more or less see from the animation that in this case, the random metric is linear in the Euclidean metric. The challenge here is to understand something like the limiting shape of the metric ball and also the fluctuation, that is the second order term, what is the order of variability for the distance, and also how much would the geodesic fluctuates from the geodesic when you are just in the original lattice. Those are also very hard problems. We can also ask what happens at criticality. Here is another simulation, again describing the evolution of the metric ball. You see that in the critical case, very vaguely, there is some fractal structure. although we don't have much mathematical progress on this front, we do have some results that can justify the fractality here. For instance, in high dimensions, we know the distance grows as the square of the Euclidean distance. And in 2 dimensions, we know that if you look at the geodesic in this metric, its Euclidean dimension is strictly larger than 1. This is due to Eisenman-Burchard and as well as the sort of ISW estimate. Okay. In these models, we assumed that particles only have nearest neighbor interaction, or basically only nearest neighbor edges can occur. This is probably true in some physical systems, but certainly will not be correct in some other physical systems. It would be more natural to think, even though when 2 particles are sort of away from each other, they would still have interaction. It's just the strength of the interaction should decay in terms of their distance. So to incorporate this, people proposed long-range models, and in particular, long-range population models, where you could have a long edge joining 2 vertices that are far away from each other. It's just the probability is very small. I don't want to tell you too much about this model. I would just say there is also a very interesting and intriguing phase diagram for this model. And at criticality, we have obtained some scaling limits results for the random metric. Another type of question that you would be possibly interested in is random walk on the open clusters of population. It is probably one of the few most fundamental results in probability that random walk on regular lattices, they scale to the Brownian motion, which is the random movement, the random dancing of a pollen observed by Brown. If you observe the pollen particles in the water, they have all sorts of collisions from the water, and which results in this very highly irregular motion, and people call it the Brownian motion. And then it is very natural to wonder, in this population clusters, do you still have scaling limits of Brownian motion for the random walk? Especially at criticality, this is a major challenge. We obtained some preliminary results along this direction for long-range population, but we wouldn't be able to solve the question at this point. Okay. Now, I mean, up to now, I'm talking about the Bernoulli population where edges are independent of each other. But you could imagine there were other scenarios where there should be some correlation, right? So that's what I'm going to talk about now. You would think if things are correlated, you have to put some nice structures. On the one hand, it corresponds to some nice physics models. And on the other hand, this nice structure allows you to do some interesting mathematics. If the structure is too arbitrary, I don't believe anything interesting can be said. So one model that we can choose to talk about, and which is also a very canonical model in statistical physics, is the Ising model. In this video, it shows a small experiment on when you hit the magnet using a march, then the magnetization will be weakened and eventually lost, and then this hanging nail will drop off. Wait for 10 seconds, it will drop off. This says there's a phase transition in terms of temperature for the magnetization of the magnet. The 2 simulated pictures also echoed this point. On the top, this is a picture simulated for high temperatures. You see that there's all these chaotic colors. This basically corresponds to no magnetization. And on the bottom picture, things are pretty organized. It's one color on the top and the other color on the bottom. There's some fluctuations. This is very ordered, and this corresponds to magnetization. Now, how do this organized and not organized corresponds to magnetization exactly? Basically, we can imagine at every lattice point, there is a dipole. The dipole can have 2 directions. It can point to the north or point to the south. If the directions are chaotic, then they are basically the combined effect is canceled with each other, and you do not see macroscopic magnetization. On the other hand, if things are pointed to the roughly to the same direction, you see there is a macroscopic effect. In order to understand the important role of temperature in this phase transition, we need a little bit more definition for. My time is almost up? Not yet, okay. The clock says otherwise, but the chair asked me to continue, so I will continue. Sorry. Let's look at the math definition of the Ising model. So let's say each vertex has two spins, either plus or minus, it's like red or blue, and we just need to understand what is the probability to have assignment of colors, right? For each configuration, the probability is proportional to exponential of the number of agreeing pairs divided by t. So from the definition, you'll see that the model prefers to have the same color for nearest neighbor spins. And if t is smaller, this sort of preference is stronger. And this hence, there is a phase transition in terms of t, in terms of the temperature. But to prove this rigorously still requires more work. And this was done by Payas in 30s in his very classical work that shows that in 2 dimensions and above, there is a phase transition for the Ising model. After understanding the phase transition, we can also ask, what about the critical phenomenon? At the critical temperature Tc, what do we expect? Is there supposed to be mechanization? And in the most important case for d equal to 3, this is a result obtained about a decade ago. Now I will take the chance of Ising model to explain what would happen if we have noise or disorder in our physical system. Because when we pose a physics model, we have made various idealized assumptions. However, usually the environment cannot be as idealized as we think. There will be all sorts of noise in the system. So it would be important to understand, if you have some noise in the environment, would this drastically change the property that you are interested in? So there are a few ways to introduce noise to Ising models. One way is to say, okay, let's have a random external field. That is, at every lattice, we have a random preference to plus or minus independently. We want this preference to be weak. Otherwise, you can imagine that the property of the original model will be completely destroyed. So here's some simulation. The simulation goes as follows. We simulated a very natural evolution of the Ising model. It's called Galoa dynamics. Not only this is a very natural way to sample a Ising model, but also this corresponds to the natural process for the Ising model to relax to the equilibrium. In all the 3 simulations, we started from O+, and the noise is increasing from left to the right. Basically, if after a long time of this simulation, plus is still the dominating direction, then you imagine there should be mechanization. Otherwise, the mechanization will be destroyed. Then we can see clearly that in the 3rd simulation, it becomes chaotic very soon. That probably means, okay, large disorder would destroy the mechanization as we expected. The more subtle question is, what if we have weak noise? From the simulation, it seems to suggest the mechanization will be preserved, even if we have very weak noise. But, here is a but. The simulations can be misleading for 2 reasons. One is that the time is too short. 2 is that the scale is too small. So this is where the physicists have debates and where mathematicians have clarified the debates and even found a phenomenon that elusive to physicists using rigorous methods. I see the chair is about to stand, and I think that's just my time is up. I would just say there are many other things I didn't have time to tell you. There are other ways to introduce noise to the Ising model, which one of them is supposed to model the avalanche, and also there is yet another important population model coming from level sets of coming from a certain Gaussian process. There are some beautiful simulations. At least you got the impression that this subject has a lot of interesting and rich questions that I hope some of the youngsters in the audience can be attracted to. My time is up, so I'm just finished here. Thank you so much.
Thank you, Professor Dean, for your wonderful speech. Actually, I would hope that you would actually continue to talk, but we have a very tight schedule. And first, I would like to say that actually I really enjoy your talk, and your insight into population and static physics is truly enlightening and highlighting the intricate interplays between probability and physical phenomena. Please allow me to introduce our second speaker, Professor Yifeng Liu, from the Institute for Advanced Study in Mathematics, Zhejiang University. Professor Liu, Ramanujan Prize laureate, is renowned for his work in algebraic number theory, algebraic geometry, and automorphic forms. His talk, titled From Natural Numbers to Infinite Categories, we explore how the phenomenon of abstracting has led mathematicians from simple concepts like the natural number to the complex one like the infinite categories, emphasizing the necessity of such abstraction. Let's welcome.
Okay, thank you very much. So first, I would like to thank the committee to give me this wonderful chance to share some mathematical thoughts from old to new to the audience. Okay, I will, sorry, how to turn up and down? Okay, how to go back? I'll go back to it. Okay, thank you very much. Okay, so I will start from some mathematics that everybody knows from childhood. They are so-called natural numbers. Okay. So this is also the order where human beings started to, how mathematics started from. Okay, so about 50,000 years ago, mathematics started from the so-called counting. And there are many ways we count. Today we use numbers, but numbers are some artificial things, right? We write 1, 2, 3, but those are invented from later. And at the very beginning, people use objects to count. For example, use sheep, stones, and knots, and even ceramics and ceramic objects. And today we don't use sheep, stone. We eat sheep, right? We play with, but we don't count in sheep unless you feel hard to sleep. So today we use this so-called Arabic numbers, 0, 1, 2, blah blah. Okay, those are called natural numbers because they came from the nature, like sheep, stones, and knots. Okay. And actually, the generation of this concept of numbers, those abstract numbers, is one of the earliest mathematical thoughts people discovered. In today's language, it's called one-to-one correspondence. Also, today we use like a 10-digit enumeration. Like we count to 10, then we use 11 and 1, 10 plus 1, 10 plus 2. And also, if you know French, you know that they don't count in this way. But anyway, this is called a system of numeration. Today, we commonly use the 10-base one. And in computer science, people use the 2-base one. Okay, these are some pictures I found from internet. I apologize if there's some copyright issue. So the first one is the counting by knots. As you can see, there are characters, right? So you can imagine this was from ancient China. And the second and the third are from Asian Mesopotamian. They're counting from, they use ceramic objects to count. And you can see on the third picture, there's symbols, and they look very like from the second picture. So that's one source of this abstract notion come from. They came from actual objects. And the last picture, I think it's from ancient Egypt, right? They use different objects to represent a certain amount of number. And you can already see there's an idea of 10 10 base sort there. There's 1, 2, or the 9. Then 10 is, it just changes to another symbol. Then 100, it's even bizarre. And then 1,000, there's something there, right? And until 1 million, there's a human being. Okay. So these are all early sorts, mathematical sorts from all Asian civilizations. Today, we know that there is actually a hierarchy of numbers. We start from natural number, and then we want to present their ratio, represent their ratio. For example, the ratio of female audience to male audience in this room, like some to something. And you know that in many cases, this number is not a natural number anymore. It could be like 2 to 3. Okay, 2 to 3 is not any natural number. The ratio of natural numbers are called rational numbers because they are ratios. Okay, they are ration. Okay, and then there's an important discovery that at about 2,000 years ago, the ancient Greeks thought that every quantity in nature can be represented by a rational number, and certainly that's not true. The first example is that if you consider a right angle triangle, like a two right sides are 1, 1, then the other side should be square root of 2, and that number is not rational. So that's called irrational number. And that discovery was thought as the first crisis in mathematical history. And later, people even found a way to classify those irrational numbers. And some irrational numbers can be represented as a root of a polynomial equation with integer coefficients. That are called algebraic numbers, and some are not. And irrational numbers have also other type of, for example, today we know that there are something called the real numbers. There is a real line, and the rational numbers are dense there, but they don't fit all the holes there. So there's this real number, and real numbers basically, all numbers we see from our daily life can be represented by a real number, but they don't really give all the interesting numbers. Okay, and for example, if you want to solve the equation x squared plus 1 equals 0, there won't be any real number satisfying this equation. So you need to extend the number system to something called complex numbers. Okay, as of course these numbers are more complicated than the real numbers, so that's called complex numbers. That's how I understand this terminology. And in modern physics, people have in some sense proved that complex numbers are actually necessary in describing our universe. Okay, now I will continue to introduce a second main origin of mathematics. Okay, so mathematics also starts from geography. Okay? So what does that mean? Okay, for example, from long time ago, when there's a human being, there's an animal, they travel, right? They need to move from one spot to another spot. When you do this, there are many choices. You can go from this way or that way. There are even change of ways. But this is called from points, and there are past linking points. So there's a very famous problem in mathematics from 18th century that's called the Königsberger 7 bridges. So you see in the picture, there are 4 pieces of lands, right? Two are lands and 2 are islands. And there are 7 bridges linking these pieces. And how many ways you can travel through all these 7 bridges, and what are the shortest ways? And those are basically the question you can consider. And this is also a very important origin of mathematical study from this geographical question. And from all this consideration, there's a new branch of mathematics studied. It's called topology. And the official terminology was actually invented by Leibniz in his book called Geometria Situs in 17th century. Okay? And in topology, there's a very important concept called homotopy. This word probably non-mathematician didn't hear about this. What does this mean? This essentially means deformation of path. So what does deformation of path mean? Let's think about this. We're now in Kowloon, right? I mean, if we want to travel from here to the island, if we drive, how many ways can we do? There are 3 ways, because there are only 3 tunnels under the Victoria Harbor, right? But if you want to swim from if you want to swim from Kowloon to island, how many ways? There are infinitely many, right? You can choose any starting point, go any route. If you want to challenge yourself, you can go S, right? Or you don't need to go straight, right? And you can land at any point on the island. So there are infinitely many passes from point Kowloon to point island, okay? And I can swim this route today, and tomorrow I just shift a little bit to the east of the previous route. That's the second route. And the day after tomorrow, I can choose a little bit even easter to the previous one. So this deformation, this is an infinite many choices, right? There are infinite many choices. There's no way that you can drive like this. There's only three tunnels. There's no way I can shift or deform my way of driving. So this is an important concept from topology called homotopy. And at this point, probably you won't see any relation between natural numbers and this homotopy. But I think in late 19th century, there's a new subject somehow relating these 2 very different sources of origin of mathematics together. That's called homological algebra. So later I will introduce a little bit, and I will also mention this, the modern, the very recent development in this subject, the so-called infinity category theory. Okay, here's a picture. You can view X as Kowloon and Y as the island. And so gamma naught is the way you swim on your day 0, and the gamma 1 is the way you swim on day 1000, for example. And in the middle, you can just deform gradually day by day, as you wish, okay? Okay, so here are even more bizarre words, right? What J comes as homomorphisms, homotopies. Okay, so here comes a very important branch of mathematics, or you can even call this a philosophy of mathematics, but algebra. Okay, we know algebra, right? We study algebra even from elementary school. But the term algebra in modern mathematics is a little bit more abstract than the algebra the general audience know. Okay, so this is a key. This is a subject where you can really feel the abstractness of mathematics. So I will take one example of the objects we study in algebra called an abelian group. So what is an abelian group? So first, it is a set. A set is just a collection of objects, okay? And there is an algebraic operation on this set, which is a binary one, okay? I denote this by a plus. Okay? It is, of course, related to the plus we are all familiar with, but this is an abstract version. So what is plus? Plus is an assignment from A times A to A. This means that given me 2 elements in A, I will give you 1 element in A. Just like what usual addition does, right? Usual addition, you give me 2 numbers, I give you 1 number, which is the sum of the 2. And this addition should satisfy what an addition should satisfy. So first, it should satisfy the associativity law. If you add x plus y first, then add z, it is same as you add y plus z first, then add x. Okay? The second is the commutativity, which means that the order doesn't matter. If you add x plus y, same as y add x. The third one is that there is something called a 0 element. There is a necessarily unique element 0, such that 0 plus x is x. So here's a very good exercise. Even you never heard of this, you can still do this exercise from pure logic. Why 0 is unique from this definition. Okay, you only need the logic. There's nothing you really need to. And there's also something called inverse element. So for any element x, there exists also a necessarily unique element called the negative x, such that when you add x and the negative x, you get 0. Again, this is a pure logic exercise to see why inverse element must be unique. So what is a homomorphism? Homomorphism, okay, what does this word come from? Maybe from Latin? I'm not sure. Okay, a homomorphism is a relation. It is something between two abelian groups it is a map F from A to B that respects the addition, which means that if you add them first, then you map to B. It's same as you first map to B, then you add them together in B. So you see two plus signs here, right? They actually have different meanings. The plus sign on the left-hand side is the addition on A, and the plus sign on the right-hand side is the addition on B. Okay, that's a homomorphism. And again, that's a pure logic exercise to prove that a homomorphism must send 0 element to 0 element, and then must send inverse element to inverse element. Okay, examples. The numbers, so we have introduced in the first slide, they all form abelian groups. And what's the addition? They are just the usual addition of numbers. Like giving me two complex numbers, 1 pi, 1 I, then the sum is just pi plus I, right? And that's just a complex number. And the next example is a little bit more interesting. Actually, you can use multiplication to form the addition in a group. I know it sounds weird, but that's how algebra works. So in fact, if you remove 0 element from Q, or you remove 0 from R, or you remove 0 from C, they also form abelian groups. But now I take multiplication instead of addition to be the addition of this group. You may feel strange because, okay, you just said there should be an element called 0. Then you remove 0. What is that about, okay? Because under multiplication, the role which the abstract 0 play is now played by the number 1. Because 1 multiplied by anything is that thing itself, right? Okay, so that's how algebra works. They borrow some familiar notation and they make it abstract. And after some day, you don't recognize this anymore. That's how, especially a feature of modern algebra. Okay. Now, okay, let's continue with this notion. So we have abelian groups. Let's make an example. Okay, so some examples of abelian groups, which are not just from numbers. So remember, in the previous Königsberg 7-bridge problem, I want to define some algebraic notion from this geographical problem. So I define something called A naught. That is an abelian group. This abelian group is freely generated by 4 pieces of land, in which 2 are islands. So what does this mean? What does freely generated mean? This means that A0 is just 4 copies of Z. Each Z represents one land. So elements in A0 is like a weighted sum of 4 lands. Like I put the north land a number 1, and I put the south land a number -1, and the left island a number -3, the right island a number like 2. That's an element in A0. That's called a abelian group freely generated by 4 pieces of land. And I also have 7 bridges, right? But each bridge have two directions, right? In ancient time, there's no one-way road, okay? So you can travel from this way or the other way. So if we count the directions, there are 14 bridges with directions, okay? So you have 14 bridges, and I let A1 to be the abelian groups freely generated by these 14 bridges. And more importantly, I have a homomorphism from A1 to A0. So how does this work? So you see, if I take the upper rightmost bridge, and there's a direction, let's suppose the direction is from the land to the island, okay? Then the homomorphism D will send a disoriented bridge to the element A0 that is its destination minus its origin. So this is 1 times the right island plus -1 times the north land. Okay, so that's the homomorphism that's given. It's called a D. And this homomorphism actually will play an important role in solving this, the original, the underlying topological problem of this seven bridge. So there's an even more abstract notion of this example called a chain complex. And this chain complex, we even consider an infinite chain of homomorphisms like in this example. So rigorously speaking, a chain complex of abelian groups is a sequence of homomorphisms of abelian groups like this. From A, you can have infinite many indexed by integers, rather all the way remote from then to A2, A1, A0, A negative 1. Okay, so the previous example is just one instance of this chain complex where you only have 2 non-zero terms, A1 and A0. All others are just the zero group. And we require this homomorphism to satisfy the following condition. So if you compose, so if you go from A2 to A1, then you go from A1 to A0. If you pick up an element in A2, you first go to A1, then you go to A0, that element must be 0. Okay, that means the composition is the 0 homomorphism for every n. So this chain is called a chain complex in algebra. Okay, so we already have this analog of points like the chain complex. And what is the analog of road or path for this chain complex? Of course, there's a homomorphism of chain complex. This is relatively natural to define. The homomorphism of two chain complex is just a homomorphism at every stage. Okay, at every stage. At every stage n, you have a homomorphism Fn from the group An to Bn. And the whole diagram should commute, which means if you pick up some element in A2, you go to A1 first, then you go to B1, should be same as you go to B2 first, then you go to B1. Okay, that's a homomorphism. So what's the analogy of homotopy? That is a very sophisticated, and that is one of the most important definitions in algebra. So a homotopy from between two homomorphisms, or from one homomorphism F to G, is a diagram like this. Okay? So it is a system of homomorphism from A0, but not to B0, as to B1. Okay, you like shift one thing to the left. So why is there? Okay, so what does homotopy mean? Homotopy, in the previous example, we know that homotopy are deformation of paths. Okay, so path is one-dimensional, right? So deformation is somehow two-dimensional thing, because it's you swipe through or the Victoria Harbor, you get some two-dimensional thing. So in some sense, this homotopy will raise the dimension by 1. So that's how you do get something that is shifted degree by 1. Okay, that's the thing called a homotopy. And so there is a unifying concept called a category, which put all these different sorts from algebra and topology together. So I will not give a definition of category. That's way too abstract. So I will give an analogy instead. So recall that, a path in mathematical language can be regarded as a map from a particular space, which is a closed interval of 0, 1 to a space. So from this remark, you can see that in topology, we have spaces, right? Okay. And maps and homotopies, higher homotopies. And in algebra, we have the corresponding concepts as well. And there is something unifying them called a category. We have objects, morphisms, two morphisms, and so-called n-morphisms. And, okay, so since I don't have much time, I will say that this categories where non-trivial higher morphisms are some objects just recently developed in the recent 10 or 20 years and become very, very important in many mathematical, so it has lots of growing influence in mathematical research. I will give some examples. The first, it has played big role in its origin called algebraic topology. For example, computation of homotopy groups by Wang Guozhen and Fu Dan and Xu Zhouli, two Chinese mathematicians, very young, both younger than me. And also in algebraic geometry, for example, the development of the modern six-operation formalism by myself and Zheng Weizhe, and Gatesbury Rosenbrim and Lucas Mann. And also in arithmetic geometry by Bart Schalter in this PID geometry. And also in representation theory, the so-called geometric long lines, which will be mentioned in the next talk by Professor Nakajima. And also in number theory. And it also generates some new mathematical areas like derived algebraic geometry and a motivic homotopy theory. Okay, I will stop here. Thank you.
Thank you, for Professor Liu, for your wonderful speech. Your exploration of the journey from the natural numbers to infinity category were both profound and engaging, shedding light on the beauty of mathematical abstraction. Please allow me to introduce our third speaker, Professor Hiroaki Nakajima from the Kavli Institute for Physics and Mathematics of the Universe, the University of Tokyo. He's also the president of the International Mathematical Union. His research focuses on geometric representation theory and the interdisciplinary field between geometry and algebra. And he has received numerous awards, including the American Mathematical Society Co-Prize in Algebra in 2003 and the Japan Academy Prize in 2014. His speech will focus on the 3D quantum field theory and the long-length duality. Let's welcome.
So how to use? So I'd like to talk about the 3D quantum field theory and the Lagrange duality. Okay, thank you. So Lagrange duality is one of the central problem in mathematics, and recently there's some big achievement still announced, so the proof must be checked. But anyway, so this is one of the very important problem in mathematics. And on the other hand, 3D quantum field theories, this is more precisely, I will talk about the three-dimensional supersymmetric quantum field theory. This is a subject in theoretical physics. And the theoretical, as Professor Ding mentioned, that theoretical physics has no mathematical rigorous foundation, but nevertheless, they have some give some insight to the to new phenomena. In particular, I'd like to talk about this insight to give some new hint about the some aspects of Lagrange duality, which I really want to mention. And I'm working on the mathematical rigorous justification of 3D quantum field theories, and of course I know because Lagrange duality is a central problem, so I have some basic knowledge, but I never imagined that my research is something to do with Lagrange duality. So this is the reason why I'm so excited recently, so I'd like to want to share with you this excitement. So anyway, so this Lagrange duality and the 3D quantum field theory are very different subjects. So finding new relations between the two seemingly unrelated subjects are very exciting, and that I want to emphasize. Okay, I must say a little bit technical jargons, but I hope that already you heard about the categories, so I hope most of you accept them. So anyway, so you have input for the Lagrange duality. So this is C and G and G check written there. So this is Riemann surface and complex reductive group and Lagrange diagram. So anyway, so you have this is the input, C, G, and G check. Then from them, you can construct two categories. So there's one category is called automorphic site, and the other category is called Galoa site. I will not go into the detail of this definition. Anyways, this is technical. So you have, if from the input C and G check, you can assign two categories. So they are very different. So there's absolutely no relation between them, but nevertheless, they are given from the same input from C, namely C and G check. Then Lagrange duality predicts the relation between those two categories. So as I said, these two are seemingly very different. If you have some relation between them, then it is very exciting. And because this is so exciting and this is so powerful, for example, the famous proof of the Feldman conjecture by wires is used this kind of idea. Okay? And I mentioned the categories, but in the number theory, which for the application to the number theory, so people use the slightly different version of the Lagrange duality. So in that case, you replace categories by more concrete object. So Professor you mentioned that the category is the most abstract notion in mathematics, but you have lower level abstract object called vector spaces. And so you, from input C and G check, more precisely, you need to replace C by some more number theoretic object. This use the so-called Bayes Rosette stone. But anyway, so from the same input data, you produce two vector spaces which seemingly very different, but nevertheless, Lagrange duality, arithmetic Lagrange duality predicts some relation between them. So because of this seemingly unrelated objects are related, if this is established, this is very exciting and this is very powerful. Okay. So this is Lagrange duality. And you consider this 3D quantum field theory is related to the so-called relative Lagrange duality, which is, in fact, proposed very, very recently, Ben Zibisake and Ben Katish. So this is more than 200 pages. I don't remember the number of pages, but it is posted in the archive as a preprint. So in this case, instead, so you put C is the same. Maybe I come back. So the input data is C and G check. Now I put instead of G, I take G1 and G2. So then, because we have two different inputs, I can assign four categories. For G1 and G2, for G1, you have two categories, as I mentioned. And for G2, I also have the category. So you have, in total, I have four categories, right? Four seemingly different objects. But those categories have some interaction between them. So this interaction is given by the so-called, this is the space M. So this is the so-called Hamiltonian G1 times G2 space. I will not go into the detail, but so those four categories are related, first of all, so maybe go to the next one. So I have four categories, and horizontal arrows is a prediction from the geometric Lagrange conjecture. But there's interaction which goes in vertical directions. So this M, so this gives an interaction between two categories. And so because the Lagrange duality predicts equivalence in the horizontal direction, so if you have the interaction in the vertical direction in the left side, you also predict the similar interaction in the right side. So this is a red interaction and light interactions. And because of the duality, so this interface, interaction are given by different sources. So this is one side, for the red, you use this space M, but for blue interaction, you need to use different different space M check. And Lagrange duality, relative Lagrange duality predicts two interactions which commute with the Lagrange duality. So this is the message of relative Lagrange duality. So as I said, the input data is C and G, and here I replace G by pairs, G1, G2, but I still keep the C to be the same, and this relative Lagrange duality should hold for any choice of C. So if you replace C, then you still have the similar. And in this case, the M and M check is independent of C. So that is the relative Lagrange duality predict. And so by this way, you can explain various known examples. So I started with trivial examples, which is some standard space M and M check. And there's the so-called Whittaker model, which has been studied in this Lagrange. And also there's some known example which cannot be explained in this way. But so there are lots of interesting examples. Maybe I should also say that this kind of relation between the four categories is called functoriality in Lagrange program. So this functoriality is one of the most important theme in geometry in Lagrange program, Lagrange duality. Okay. Then, in fact, this relative Lagrange relative duality has an origin in theoretical physics. So it is started from the work of Kapustin and Witten in 2007, and also its subsequent work by Galoa and Witten 2009. So they propose a way to understand geometric Lagrange conjecture by theoretical physics. As I said, this is, in fact, this is a four-dimensional quantum field theory instead of three-dimensional quantum field theory, which I mentioned. But it takes I mean, as I said, the quantum field theory has no mathematical rigorous foundation. And at the same time, for mathematicians, it is not so easy to understand what physicists say, because they usually use very different languages. And as I said, they are usually not rigorous. So it takes many years, so about more than 15 years, maybe no less than 15 years, certainly more than 10 years to understand mathematician to understand what those physicists say. So anyway, we now understand that those M and M check are coming from the so-called three-dimensional quantum field theory. So three-dimensional, because, as I said, Kapustin and Witten used four-dimensional quantum field theory to explain Lagrange duality. I don't explain why four is four-dimensional quantum field theory. There's some trick there, but anyway, so three is, if you have four-dimensional object, and if you have some boundary in the four-dimensional object, then it is a three-dimensional object. And the three-dimensional quantum field theory appears as a boundary of four-dimensional quantum field theory, which Kapustin and Witten use to explain the geometric Lagrange. So anyway, so you have definition of M check from M in three-dimensional quantum field theory. But as I said, this three-dimensional quantum field theory has no mathematical rigorous foundation. So this requires some justification, mathematical justification. Unfortunately, for this three-dimensional quantum field theory, I have been working on for several years. And in particular, so this is the Lagrange duality, and this aspect of duality understood in my work with Breiberman and Finkelberg. So we can somehow use our understanding to understand, to attack mathematical rigorous foundation of what this Galoa and Witten answers for how to define M check from M. And at least in some cases, we can we have a proposal for M check starting from M. I should not go into detail, but we have some concrete examples, which is rather striking because, so we maybe, yeah, I should not go so much into detail, but so I have some concrete example of M, and I compute M check, and I have another example of M, and I compute maybe I said M1, from M1 I compute M1 dual, and from M2 I compute M2 dual. And in fact, by our method, we computed the dual, and we found that M1 check and M2 check are the same. So starting from different spaces, and we apply our method to compute the M check, then we find the same space. This is in fact contradictory to what we can expect, because this Lagrange duality predict duality means that if you can go from one side to another side, then starting from another side, you should return back to the original space. So if you consider M starting from M and compute M check, and if you start from M check, then you return back to original space M. But our examples somehow contradicts this expectation. And the Benzibi and others formulate the relative Lagrange conjecture as a duality. So M check of, if you start with M check, then you should return back to M. So this is contradictory, but in fact, it's not the mathematical contradiction. In fact, they impose some condition on the starting space M, starting interface. So our example doesn't satisfy this assumption. So this is, I think this is a exciting sign, which means that somehow the relative Lagrange proposed by Benzibi and others are not sufficient to understand all the examples which we do have. And in our case, maybe we should more seriously consider our proposal so that we can recover this duality. So anyway, so I finish with my, oh, let me go. No, so still I hope it. So this is the most exciting part of myself, because I propose many questions, and this I hope that I will see some advance in future, and that's the reason why I'm so excited. And this is, I mean, of course, you want to finish earlier, but. So anyway, so the question first is, I said I have some assumption to define the dual space, and so we need to drop those assumptions. And the three is, as I said, this is still we don't understand. So starting from M, we should get M check, but then from M check, I should return back to M. So this is somehow very, very non-trivial if I under our recipe to define M check. So this is one of the most mysterious part. And finally, as I said, this should connect the Lagrange duality. And so far, we just understand the superficial level interaction between M and M check. We still don't know why this is compatible with Lagrange duality. This is the most deep question, which I hope to understand in near future. So thank you very much for attention.
Thank you, Professor Nakajima, for your wonderful speech and your explorations of the really fascinating, unexpected relations among the different areas of the mathematics, the automorphic side and the Galoa side, and between the mathematics and the physics, and also the quite unexpected connection to the first two talks. That's really exciting. Please allow me to introduce our last speaker, Professor Efim Zamalov from the International Center for Mathematics at the Southern University of Science and Technology. A Fields Medal laureate, Professor Zamalov is a distinguished member of various academics around the world. So he will present his talk on Galoa and communication technology, offering a unique perspective on the historical impact of Galoa's work on the modern communication technology. Let's welcome.
Well, I won't talk about the most recent work. Let us go back about 200 years ago. Now, how do I? Okay, this one. Okay, this is supposed to be the portrait of Évariste Galois. This is an amazing story. The guy was a French teenager who did not have any formal mathematical education except high school. He failed entrance exams to the university twice. People who knew him later wrote that it happened because he understood mathematics much better than his examiners and was not smart enough to hide it. He was killed at the age of 20 on a duel. Before that, he wrote a mathematical paper and sent it to French Academy. You know, he was a great mathematician. He had no idea how to write papers. Okay. And since he did not have any illusions about his ability to shoot, and he could predict the outcome of the duel, the night before the duel, he wrote a very detailed mathematical letter to his friend. And one of the top mathematicians of the 20th century, Hermann Weyl, called this letter the most influential mathematical paper ever. This letter and the paper that he sent to French Academy, nobody would be able to read them. And here a lot of credit goes to Liouville, who was mentioned in Professor Ding's talk. Liouville was able to decode Galois' works. Okay, and by the way, this portrait hangs in all mathematics departments, but this is artist's imagination. Nobody knows how Galois looked. Who would make a portrait of that strange teenager who is not interesting to anybody? At that time, there were no selfies. Okay, so what did Galois do? I'm pressing, nothing happens. Please help. Oh, I'm pressing the wrong button. Okay. Depending on when you finished middle school, you may still remember the formula for roots of a quadratic equation. There exist similar formulas for equations of degree 3 and 4. Nobody remembers them, nobody uses them, but they exist. And for many years, people tried to find similar formulas for equations of degree 5, 6, and so on, unsuccessfully. And then they started to suspect that maybe these formulas do not exist. The first credible attempt to prove it was done by Paolo Ruffini. But his proof contained a gap. And we know that a proof with a gap is not a proof. All his life, he tried to patch this gap unsuccessfully. The first correct proof that similar formulas for equations of degree 5, 6, and so on do not exist is due to another young genius who died young. Oh, well, I don't know if you can see. What is that? Niels Henrik Abel. So what did Galoa do? Galoa explained what was going on, building on ideas of Lagrange. And now Lagrange wrote a very influential paper. He analyzed all existing formulas, and he showed how these formulas depend on symmetries of roots. Symmetry is a very basic notion. Everything has a symmetry. Whether, this wooden thing or ornament in Alhambra, and symmetries can be performed one after another. It's like a multiplication. Symmetry is some transformation of the system that kind of takes it to itself. Symmetries can be reversed. The concept of symmetry is codified in the mathematical area which is known as group theory. You already had a crash course in abstract algebra in Professor Liu's talk. So I will assume that you know what is a group. If you go to a deserted island and you are allowed to take only 3 mathematical concepts with you, give a consideration to the concept of a group. So Galois showed how the question whether a root can be expressed by radicals depends on the groups of symmetries of this equation. He asked the right question, what is a group of symmetries? So when in the 20th century physicists started to study elementary particles, they knew which question to ask. I heard the following phrase from Sheldon Glashow. He's a Nobel Prize winner in physics, one of the fathers of the universal model. He said, I don't know if God exists, but if he exists, then he knows group theory. Okay, but Galois did 2 things. He worked on solution of equations in radicals, and there was a second theory that he developed. He introduced finite fields. I must say, well, I understand why Galois was interested in solution of equations and radicals. At that time, everybody worked on that problem. But why finite fields? I have no idea. You know, Schopenhauer, a German philosopher, said that a talent hits a target that nobody can hit. A genius hits a target that nobody sees. I will give you an example of a finite field. Let P be a prime number. You know, I'm addressing most not professional mathematicians. I was told that there are high school students here, so you are my excuse. Let P be a prime number. Every integer can be divided by that prime number with a remainder. And the remainder runs from 0 to P minus 1. Now I will show you how to add and multiply these remainders. Let P, well, be equal to 5, for example. So there are 5 remainders, 0, 1, 2, 3, 4. Take 2 of them. We want to add them. If the sum is smaller than P, okay, be happy. Then that is a remainder. But if the sum is bigger than p, it cannot be a remainder. Okay, divide that sum again, and the remainder of this division is declared to be the true sum of these two remainders. Similarly, you define multiplication. For example, if p is equal to 5, then 2 plus 4 is equal to 1. Why? Because 2 plus 4 is 6. Divide 6 by 5, the remainder is 1. Similarly, 2 times 4 is equal to 3. Now, this is the first example of a finite field of Galoa. Why did he do it? We know real numbers and complex numbers. We were told even that complex numbers are appreciated by physicists. These real numbers and complex numbers can be added and multiplied, and these operations are subject to certain rules. You can even divide by non-zero numbers. And the addition and multiplication of remainders that I described above satisfy all the same properties. They are also subject to the same rules. When I was a student, unfortunately many years ago, we were told that real world are real numbers and complex numbers. Only strange algebraists and number theorists can be interested in Galois finite fields. Okay. No, since then there were some changes in the world. The first application of finite Galois fields. Suppose that we send a satellite to another planet or whatever. That satellite sends a signal to the Earth. The signal is a sequence of zeros and ones. 0 and 1 are remainders modular 2. So they are elements of the finite field of Galois of two elements. Those of you who had a course of linear algebra know that n tuples of elements form a vector space. You can add them. So a signal is an element of a vector space. But unfortunately, while it goes to the Earth, there are noises. So what you get is not what was sent. What should we do? The following scheme was invented in late 50s, early 60s in Bell laboratories by Shannon, Hamming, and so on. It's coding theory. We decide on the Earth that we will send signals only from a certain subspace, which is called the code. If we got a signal that does not lie in that subspace, okay, it means that there was a mistake. So what do? You choose the closest element from that subspace and say maybe that was the intention. Closest, in which sense? It means that you need to define some distance. We define the so-called Hamming distance. Given two n tuples, the distance between them is the number of positions where they don't disagree. One has 0, another one has 1. And this distance satisfies triangle inequality, all the property of the distance between points on a plane. So mathematicians studied it many years before. It's metric space. And a good code is a code where all points are far from each other. Otherwise, you may end up with two closest elements, and you won't know which one. So, the minimal distance between two different elements is called Hamming weight of a code. A good code is a code with a large Hamming weight. Now, the best code in the world, it's amazing that it exists. One of the miracles of the world is Zoler code. The length of the n tuple is 24. The dimension of the subspace is 12. And Hamming weight is 8. this Galoa code is involved in a lot of mathematics, classification of finite simple groups, sphere packing, etc., etc. It's even involved in theoretical physics. And don't tell me that it doesn't have applications. When NASA sent satellite to Jupiter and Saturn, Galoa code was used to decode signals. And in the United States, it is a standard for high-frequency radio. So this is the first example, coding theory. Another example, public cryptography. In old times, if one general wanted to send a secret message to another general, they selected some page in a very thick book, War and Peace, and it was used to encode the message. It was very difficult to encode. It was equally difficult to decode it. But now, each time when you log in to your email account, you exchange secret message with your internet provider. When you use credit card or WeChat to pay, you exchange secret messages with your bank. Billions of people do it. Obviously, old methods did not work. And mathematicians came up with a new method that was entirely based on Galois fields. Suppose that, I will explain it. Suppose that Alice and Bob want to exchange some secret. And Catherine is a hacker. Don't read too much in names, it's just ABC. The following scheme is due to Diffie and Hellman. There are some other common schemes, all based on Galois fields. Let us choose a very large prime number p. I will explain why it has to be very large. Okay, so there are p remainders, 0, 1, 2, up to p minus 1. This is a finite field, as I explained before. Throw away 0. Then you are left with p minus 1 non-zero remainders. And now our operation is multiplication. In fact, in Professor Liu's talk, there were such examples. And this is a group. Galois even proved that this group is cyclic. So there exists some element G, more than one maybe, such that every element of this group is a power of that element that we call generator, G. Everybody knows these generators. Alice and Bob choose some secret numbers that they don't show to anybody, A and B. Then Alice takes the generator G and takes it to the power A and sends it to Bob. Bob got this G to the power A to the power of his secret number. So he knows G to the power AB. Bob does the same. He takes the generator G to the power of his secret number, G to the power AB, sends it to Alice. Alice takes it to the power of her secret number, so they both know G to the power AB. That is a secret that they share. What about evil Catherine? Evil Catherine knows P because, well, everybody knows P. She knows G because everybody knows G. She knows G to the power A because Alice sent it to Bob. She knows G to the power B because Bob sent it to Alice. But in order to know G to the power AB, she needs to know A and B. And we are coming to the problem of discrete logarithm. Take logarithms in the Galois field. If they were real numbers, she would just press a button and take logarithm, and that's it. But this is not a finite field. It is a finite field. It's not a field of real numbers. There are expectations or fears that when and if quantum computer is built, it may be more efficient in taking logarithms, but we have to wait. When and if it is built. Okay, the last. Well, I should say also that in the technology of blockchain and Bitcoin, the same methods are used. More often, instead of this group of non-zero remainders, they take some version of it, group relate encoded by elliptic curve, but ideally, it's very close. In blockchain technology, sometimes you need authentication from your neighbors. And how do you do it? In the same way. All financial transactions in the world, all, are done on the basis of this scheme. Now I will explain how all smartphones work. iPhones and Huawei, they all use this method. A bit is 0 or 1. A byte is a sequence of 8 bits. So how many bytes do we have? 2 to the power 8, 256. Galoa proved, among other things, he developed the whole theory of finite fields from scratch. So Galoa proved that every finite field has order p to the power n, where p is a prime number. And for every p to the power n, there exists a unique finite field of that order. We could discuss what does unique mean in this sense, but let's not do it. So, I should tell you the story. In 2001, National Security Agency of the United States announced an open competition for the best encryption system. The winners were 2 Dutch mathematicians, Damen and Rijman. And so this method that I am explaining now, it's called either Advanced Encryption System or Rheindal. First parts of their names. Okay. So the message is a 4x4 matrix over the Galois field of order 256. Well, to make it more difficult to read, we add some rows to another rows, add columns to another columns, we add key. But if it were only that, they wouldn't have won the competition. At some point, we do the so-called S-box. All elements in the matrix are inverted. It was A, now it is 1 divided by A. You may ask, what if it is 0? The inverse of 0 is 0. If you had tomatoes, you would throw them to me at this point, but I will explain why. It's a good question. How do you find inverse? Inverse is such an element that A times that inverse is equal to 1. How do you find it? Will you examine all elements? Too much. In fact, we find it via Lagrange theorem about finite groups. In a finite group of order n, the inverse of the element A is A to the power n minus 1. So, in fact, we are not talking about inverses. We are talking about powers. And power of 0 is 0. You need to do some 11 multiplications to find the inverse. Okay. In both Diffie-Hellman and Rheindal, a very strong player can break it with supercomputers just by exhaustion. Like there was a terrorist act in San Bernardino, California. FBI wanted to read the iPhone of the terrorist. Apple refused to provide password. They broke it. But if you are an ordinary person, who would do it to you? If you are not an ordinary person. Every half a year, I read that somebody broke Rheindal. I'm used to that. The recent was a week ago by South China Monitor. Okay, thank you very much.
Thank you so much, Professor. Please stay with us. Professor, may I invite you, could you please come to another side of the stage? The keynote speeches explore diverse topics in mathematics and physics. The discussion ranged from statistical physics and percolation theory to the evolution from natural numbers to infinity categories. Additionally, topics include 3D quantum field theories and line-length duality, concluding with insights on Evarista Galoa's impact on communication technology. So now we're going to have a panel discussion. May I invite our moderator, Professor Huang, and our panelists, Professor Ding Jian, Professor Liu Yifeng, Professor Hidaku Nakajima, and also Professor Anfim Selnomov. So I may pass the stage to our moderator. Thank you.
So first, I would like to thank all the speakers for the wonderful talks. Now we actually move on to the panel discussion, and so the questions from the audience are very welcome. But to start with, maybe let me first raise the topic. So and then we actually move on to see if the audience has questions. Actually, please raise your hand if you have. Well, first question I would like to ask you is that actually related to the mathematics and mathematicians and the careers. And so I know that actually there are many young students and also even the teenagers who want to be mathematicians. And so actually to ask you, what do you think are the important personality traits to be a good mathematician?
Okay. Well, first of all, I believe that there is such a thing as mathematical ability. You know, it's like musical ability. Just for some people it is easier than for other people. Second, stubbornness. Because when you work on a problem, you may work for many years, and in 99.999% of time, you don't achieve the result, and you have to do it again and again and again. Probably there are more traits.
Okay. I think that mathematics. I'm sure that this Japan and China has similar flavor, but so this is based on the Asian culture. So we have the hard competition in entrance exam. So people may think that mathematics is used for competition, but it might be true for the educational level, but it's not so for the research level. I think that it's really important to emphasize that. So research level mathematics is not competitive, and people do very different things, and this is just more cooperative effort of the community. So I believe that if anybody who likes mathematics could be a mathematician.
Okay, if I would like to mention one particular trait for mathematician, I think that would be patience. Okay, just as mentioned by Professor Zemanov. So most projects, especially in pure mathematics, they require a long period of working. Some may be several months. That already short, right? I mean, some long ones like Wiles proof from my last year, the whole length is like 8 years. Okay, so imagine that if one without patience could never finish a project lasting for those many years. So, but more precisely, so what does this patience play? Like, so first you have to stay there, like even after rounds of frustration, you still need to like keep the focus on the problem. And also there are many details, lots of like things you need to work it out. lots of difficulties. One by one, you need to finish them. And all these things, no one else will tell you. Like no professors will give you homework. Like today, so which lemma, tomorrow, which one? No, you don't need to figure them out by yourself. And in some cases, like unlike the problems you face in high school, the logic behind all this research is not linear. So it's not like one by one, then finally. Usually like this block, that block, then everything will patch together. The whole organization process and the whole solving process requires lots of patience. And that patience, well, maybe, I don't know if it can be developed, but I think it's a very important feature. If you think you have such patience, maybe it's a good idea to try to be a mathematician. Thank you.
First of all, I agree that you need certain mathematical ability to become a professional mathematician. There is some bar. Below that, I really don't think this is the track, at least for a career for someone. I think the second important thing is that you should enjoy it. If you don't find a pleasure in doing mathematics, there are really many other ways that can make a living in a much better and a much more efficient way. Then both Professor Zaminov and Liu talked about patience. You have to be persistent, spend years and years of efforts to trying to solve a puzzle. I agree with that, but I also would like to chip in the other side of the coin. You also need to have some sense on when to give up and switch to a new problem. Sometimes it's just maybe this problem is not right for you, or maybe it's not the right time to solve the problem, the right tools are not there yet. You can't just bump your head against the wall and hope something will happen. You know, you only have, your life is only once time. You don't have that many years that you can spend, you can waste in luxury and still secure a job. But the very cruel thing is, before we flip until the end of the book, we don't know whether your patience or persistence is for good or not for good. And this is a bit luck. I don't think anyone can tell you something definite. Okay, now it's the time that you should persist. Now it's the time you should give up. Nobody can tell you that. You have to build your own sense to make a choice when that kind of crossing road is present to you. I guess that's pretty much what I have to say, and I would like to pass it to the chair.
I'm curious. I mean, for that, actually, you just only depends on your own sense, or you actually also rely on the theory of probability.
Okay. Thank you very much. You actually reminded me of something that I was about to say, but I forgot, which is just answering the question. If you want to make a judgment on whether should it be basically come from yourself or should be, you said luck or probability. But I think more importantly, you probably should talk a lot to other professional mathematicians to build a sense on what is the right thing to do. Usually the sort of right thing to do are connected to some other things. If what you're working on is purely isolated at this point, perhaps that's not the best thing to chase at the moment. Speaking of communication skills, you also have to develop certain skills to balance your life, to find pleasure outside of mathematics. Because as much as we hope that we enjoy doing math, frustrations is just there, very frequently. So for someone who wants to be a professional mathematician, try to develop some harmless hobby. Whatever it is, it doesn't have to be meaningful. As long as it can calm you down and bring some smile to your face. That's very important, I think, for mental health and for a long-term pursuit of mathematics. Thank you for your reminder.
Yeah, thank you very much. And I'd like to thank all the speakers actually for the valuable input, how to be a good mathematician. And I would say that actually probably this is not only applies to the mathematics, but also, I mean, some actually also actually apply actually to be, I mean, if you actually choose other career paths, I mean, to have a successful career or you have a happy life. And okay, I would like to say yes.
Hi, everyone. My name is Joseph. I'm in investment business. I am looking at opportunities in quantum computing, which is your area. So my question is, in your view, how likely is quantum computing, if likely, or you think it's unlikely? Because it's a game changer, so it's very important for investment, for crypto. So I'd like to hear your view about quantum computing. Thank you.
On computing. The question is about quantum computing.
Game change? Which game? The whole game. Huh? Didn't understand the question.
Okay, I think he asks whether quantum computing can be real, and if so, how much longer should we wait, or something like that. How much longer you think quantum computing can actually be applied in reality? I think that's the question. Quantum computing, yes.
It's like cold fusion.
It's like what?
Like, there is a thing as cold fusion.
Or is it real?
It may be, you know, both quantum computing and cold fusion can be, you know, it could be next year, or could be in 30 years, or never.
So it's not feasible. It's not really feasible yet, right?
No, at this point so far, no.
I appreciate it. Your honesty is very important. If you don't think it's feasible, then it's not feasible.
I think you should take the answer with caution. I don't believe any of us is a real expert in quantum computing. You will hear different things, different ways of talking from different people. Those who would like to push the area, and those different. Yeah, this is the time that I should echo what I said earlier. You should use your own judgment after talking to people. One single person said it's not impossible. It's not possible. Does not mean it's not possible. Another day you met another person who said, "Oh, it's very promising. In 5 years we're going to have it." It may not be the case either. So, yeah, I would just tell you I don't know.
I should actually probably say in the beginning of the panel discussion that actually all the discussion here will not be regarded as investment advice. Let's see if there are other questions from the general audience that like over there. Please.
Hello, speakers. I'm very bad at mathematics. What makes me interested, because my son, 8 years old son, loves mathematics. So how he fall in love with maths, as simple as watching a video called Building Blocks at YouTube. Building Blocks is very visual-driven things, teaching you what is add, 加減乘除, so the basic 4 things. And then he suddenly he has the curiosity, and then last year I go to Cambridge to learn about sustainability and innovations. And I don't know where he knows that there's a bridge in Cambridge without any nails, but it's called Mathematics Bridge. So, and then he sent me, "Oh, you must go there, because that bridge is called Mathematics Bridge. It doesn't come with a nail, but they hold together the bridge." So, so I feel really fascinated by how a simple video in YouTube, starting from visualizations, because kids, they are not good at language at start, but they are good at seeing, because they learn faster seeing. So, and then makes this how he fall in love with mathematics. And then when I'm in Cambridge, and then there's a guy echo to these questions about algorithm trading. So he is a graduate from Cambridge 10 years ago, and he's now doing the on Cambridge mathematics, and he's now doing the algorithm trading on investment. And the way he speaks is blah, 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 so fast. It's like his brainwave working this speed. So, so recently I just back from Dubai for a business trip. And you know, Dubai is a very unique space because
excuse me. So
the question is,
yeah.
I do believe in crypto because it's a digital world, but the problem is how you use these tools to change the world for a better humanity and a safer planet. I mean, in terms of environmental, because in crypto world, everything is traced. Even in blockchain, everything is traced. So it's a force of energy. It's a force of energy, so everything is traced. So it's a force of energy and power on how people are tracing or changing the economy or something in terms of community. So I think and even on the quantum computing, it should be the session in the morning. So I think there's a lot of interdiscipline sections to close the dots.
Yeah, excuse me, because our time is short. Would you please briefly raise your question?
Oh, so my question is how to make my 9-year-old son fall in love in this area of mathematics. Thank you. To solve the complicated problem of this planet and humanity in general. Thank you.
So let me try to repeat if I understand your question. So your question is that how to have this is a young kids to like or fall in love, with mathematics, right?
Okay, I think for most people who really like mathematics, they don't care about how useful is mathematics. So, well, mathematics, of course, help a lot in real world. But I mean, as mentioned already by many talks, there's no way to live mathematics in today's life. But mostly they are carried out by non-mathematicians. They are experts in other fields who use mathematicians. So I guess for kids, maybe it's way too early to think about. Maybe you can show some examples, like we know this. For example, all this general relativity or all this internet security, all heavily reliant on modern mathematics. But I guess that usually won't be the driving force, for someone to fall in love with mathematics, right? I mean, I still think, in most cases, math is really pure. I just found it interesting, challenging, and I feel very happy by solving some puzzles in math. That's how most people fell in love in math. And of course, there are struggles, there are pains, but that's part of the life, right? We all have that, but we still love our daily life. So that's, I guess, it will become natural at some point that somebody uses developments in mathematics to benefit our world or to influence no matter in which direction. At least there's a huge influence. That's for sure. That's what I want to say. Thank you.
Thank you. Yep. One more question.
I'm quite interested in Ding Jian's talk about the percolation. So I'm curious that I searched that there is a model called the random cluster model. And I have several questions. And one is that how can you make sure that is only one transition point on between the unpercolated and percolated phase? And others are...
So since we are actually running out of time, maybe just only one question.
These are related. So if the random cluster model has a multiple dimension, how you can make sure before prove that the transition point is sharp? That's my question.
Thank you. So we have only 1 minute, and
I guess I will have to answer this one. For many models, when there is a monotonicity, then it's clear there should be only one transition. You transit from no percolation to there is a percolation. So when there is monotonicity, this is natural, and this actually happens in many models, including Bernoulli percolation, an easy model, and the Gaussian field I didn't have a chance to talk about. But there are also other cases when monotonicity is unknown. Then in this case, yeah, you could have very weird behavior potentially, but at least we have the faith that things should still behave nicely. For instance, when there is disorder, we don't really know things are monotone, but we still believe it would behave nicely. So answering your question, when we don't know what to show, when we don't know what is the actual truth, we have to have faith and try to prove it. It's like standing here still without doing anything is not as useful as making a guess of a direction and trying to jump to that. Because if you make a decision on that's the truth you want to pursue, you have at least a 50% chance of success. And if you choose the wrong direction, along the way, you probably will find, okay, something is probably incorrect in my intuitive picture, and you can switch back. I think this is how basically all science develops, not just mathematics. You need to make a decision on which direction to try. Okay, time is over. Sorry.
Yeah, I'm pretty sure that the audience actually has many more questions. Actually, feel free actually to ask the speakers afterwards. I mean, since we're actually running out of time, so our session has to end here. So let's join me actually to thank all the speakers for their valuable insights and inputs.
Thank you so much. Thank you. So we now invite all the guests, please rise to have a photo together. Let's have a photo together. Please have a look to the center, please. Okay, maybe we can have one step to the left, please. One step to the left. Yes, perfect. Yeah, one step is enough. Thank you. So please have a look to the center. 1, 2, 3. 1, 2, 3. Okay, a few more to go. 1, 2, 3. Okay, thank you very much for the insightful sharing. Thank you so much. Thank you. And now we are going to start the next session immediately. Meanwhile, light refreshments are served in the lobby. Please feel free to enjoy. For those who have registered for the Hong Kong Science Museum Guide Tour, please gather outside at 3:45. Meanwhile, I would like to introduce with you, this is me. Have anyone tried this robotic arm to draw yourself? Actually, this is for creating the Chinese traditional ink-style portrait through the AI technology. The project is to broaden the boundaries of the fusion between science and arts. Please feel free to try at the lobby area. And now we will move to the next session. The next session is computer science. We'll be focusing on AI and chips. Next, we are going to have Professor Xie Yun as this session's convener. He is Chair Professor, Hong Kong University of Science and Technology, Fellow, Association for Computing Machinery, Fellow, Institute of Electrical and Electronics Engineers, Fellow, American Association for the Advancement of Science, Member, Program Committee of the Future Science Prize Week 2024. And before Professor Xie introduces the upcoming keynote speakers, I would like to invite Professor Xie to take the photo together with our keynote speakers. May I also invite Professor Ono Mustu, Gabriel Lo, Professor Wang Yu, and Professor Ma Yi. Please come to the stage. Thank you very much. Is it better to step forward? Yeah. Okay. And one step to the left, please. Yeah, one is enough. Thank you. We can stand closer. Okay, let's have a look to the center, please. Let's have a look to our official photographer first. 1, 2, 3. 1, 2, 3. 1, 2, 3. Thank you. Thank you so much. May I invite Professor Che, please proceed to the podium. For the keynote speakers, please be seated. Meanwhile, we can see there are some newcomers. Please feel free to have a seat. And then we are going to have amazing sharing by Professor Che. Thank you.
Good afternoon, everyone. It's my honor to moderate this section in this beautiful day. And today we have a great list of the speakers for the AI and chip design sections. These two topics right now probably is the hottest topic these days. I would like to extend my welcome to all of you and my gratitude to all the speakers to accept the invitation of the organizers to give the speech over here. Please allow me to introduce the first speaker, Professor Wen from ETH, Zurich, who is also a member of Academia of Europe, will deliver his speech on memory-centric computing. Let's welcome Professor Wen.
Okay, thank you very much for the introduction, and thank you for inviting me to give this talk. It's always good to be here in Hong Kong. I'm going to talk about memory-centric computing. I'm going to take a critical view of how we design computers today, and hopefully sow the seeds for designing better, much more efficient, much more higher performance, and robust computers for the future. Today, computing is bottlenecked by data. Data is really key for many applications. Machine learning is one example. Genomics is another example. And these applications are growing. These applications require rapid and efficient processing of large amounts of data. And data is increasing. We can generate more data than we can process today, and we need to perform much more sophisticated analysis on more data. And as people dream about new applications will come, and these applications will continue to constrain the power and the capabilities of our devices. This is an example from neural networks. You may have seen this picture. Essentially, memory requirements and compute requirements are growing so that we can make these models better and better. And you can see the numbers. In just 2 years, you have orders of magnitude increases that are needed for both compute and memory requirements. And people are experimenting with interesting things. The person who delivered this talk, Sean Lee, is leading a company where you build wafer-scale chips that are of this size, so that they can put compute and memory together. Genomics is another area where we have technologies that can generate a lot of data, a lot more data than we can process. In fact, this is actually a fascinating area. We do a lot of work in this area. There was actually a talk on life sciences session yesterday where people are talking about genomics. I think we need to bridge the gap more between those life sciences and computing so that we can actually process the genomic data in ways that are actually much more useful to humanity going into the future. But this is an area that needs both high compute power and high memory demand. In my opinion, we have actually another responsibility for the future. We're building infrastructure as computer scientists, computer engineers, electrical engineers. We're really building the computing infrastructure for the future. If you think about it, this infrastructure is bigger than any other infrastructure humans have built. Humans have built a lot of infrastructure, but computing actually in scale overcomes all of them. We'll have billions of devices. In fact, we already have a lot. The question is, how do we treat the world? Do we want a world that looks like this, nice, or do we want a world that we cannot even breathe in? This brings us to sustainability issues, energy efficiency issues. I believe, as humans, we're greedy. We want high performance to solve all kinds of problems. We want clearly energy efficiency, and we have to do something about sustainability, all at the same time. So to be able to get all of these at the same time, then the question is, are we doing the right thing in the design of computers today? Okay, so basically, today we have a huge problem. We have a data access that in order to process the data, a computing system needs to access the data first. This data is generated somewhere. You take it with sensors, and then you store it in the storage system, and then you move it to the memory system, and then you move it to the caches, and then you move it to the processor so that you can process it. This is actually a very long latency process that requires high bandwidth if you're accessing many pieces of data, and it's also very energy inefficient. So basically, the fact that we're moving data between the processing and data generation and data storage units over and over so that we can actually get something done on that data is causing great energy waste. So we're basically very processor-centric, and as a result, we're causing a lot of energy waste. This also causes great performance loss because this process of moving the data takes time. Unfortunately, maybe fortunately, we recognize that a lot. We actually try to design our systems so that we tolerate that performance loss. We design huge hierarchies for caching, buffering. We design very sophisticated out-of-order execution engines. We design many different levels of prefetchers. We design heavy levels of multi-threading. And all of this is really there to tolerate the latency and performance impact of data movement. And sometimes it works. Many times it doesn't work. Oftentimes it doesn't work perfectly. If you look at some of the caches that we have, their efficiency is around 10 to 20%. If you're lucky, 30 to 40%, meaning most of the data that you cache is useless. You're not going to touch it again. Yet we're building these complex systems. I put this in parentheses because this is kind of the hidden cost of data movement, meaning we're used to designing these complicated systems and we take it as a given. But this is really bad for sustainability if you think about it, because you actually produce these huge chips that may not be very efficient. Okay, and this is a vicious cycle, basically. If you want to tolerate the performance loss due to data access, you keep making your systems more complex, and that wastes energy. So we're in this vicious cycle where we keep wasting energy today. And the fundamental problem is we're very processor-centric. All data gets processed in the processor at great system cost, and we kind of ignore memory and communication in the grand scheme of things. Now, let's take a look at what a processor looks like. It kind of looks like this today. This is a picture from 2008 when I wrote my first proposal to National Science Foundation in the United States. I used this picture. This picture is kind of similar today also. Essentially, what you see here is computation units in the red part. Those are called cores. They could be accelerators also. Everything else, more than 90% of the system, is really dedicated to storing and moving data. Now, if you show this picture to a 10-year-old child, maybe that child asks the question, I should not have any problem with data movement. Right? Maybe that child will tell you, yes, you're dedicating almost all of your resources to storing and moving data. You should not have any problem. Unfortunately, the system is still bottlenecked by memory today. Maybe it's because we're doing something wrong fundamentally in our systems. Okay, if you don't like my picture, this is AMD's picture. Gabe can talk to you about that. He's from AMD. Essentially, that green box is processor. That green box is really caches. But there's a lot over there that's not caches, like this is the memory interface. And there's a lot of other stuff for communication with the outside. And we're adding more and more cache. This is beautiful technology, 3D stacking technology. In fact, Gabe's an expert on that topic. 3D stacking technology where you actually put other processors, other things on top of the processor, and you do caching. The question is, are we utilizing our resource in the best way? Okay, if you don't like that picture, this is IBM. If you don't like that, and these are caches. If you don't like that picture, this is something that you maybe in your mobile phone. And this chip is really an SRAM-dominated chip. The rest is really DRAM. And then there's the darkness that many people don't think about, storage. But most of the data is really there. Okay, so we know that actually memory is a bottleneck. So I'm going to go through this relatively quickly. People have known that memory is a bottleneck. For example, this is a paper that was written by Dick Seitz in 1996. After his team designed the fastest alpha processor of its time, he wrote this one-page paper I would recommend everyone to read. He basically says that we designed this beautiful processor. It's capable of finishing one instruction, one alpha instruction, or 4 alpha instructions every clock cycle, which was a very fast clock cycle at the time. Unfortunately, on this important database workload, which we think we designed this processor for, it's finishing one instruction every 4.7 clock cycles. Basically, it's operating at about 5% of its peak efficiency. That's not a good number if it's good engineering, right? And he basically finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Okay, this is data from my own PhD thesis. Together with Intel, we show that most of the time the processor is waiting for memory. So that was his conclusion also. The processor is waiting for memory most of the time. Recently, Google has repeated this sort of study, and they basically shown that most of the time the processor, a cutting-edge processor, is waiting for memory. It's really finishing instructions only 10 to 20% of the time. Again, it's good to ask the question. We're designing these computers to actually finish instructions, yet they're doing what they're supposed to do only 10 to 20% of the time. Is this a good design? Certainly, it's not a very efficient design. Okay, that was performance. Energy is much worse. This is data that I borrowed from Bill Daly, who was the chief scientist of NVIDIA. The numbers have changed over years, but the orders of magnitude did not change. Essentially, a complicated arithmetic operation, 64-bit double precision floating point operation, is only 20 picojoules according to these numbers. A DRAM, a memory read or write access is 16 nanojoules. That's 800x difference. Between 2 to 3 orders of magnitude difference. Basically, does it make sense to move the data, expending a lot of energy, to the processor so that you can do one arithmetic operation and then write back the data over here? Now, this is an optimization problem. You can actually figure out when does it make sense and when it doesn't make sense. The conditions under which it makes sense requires a lot of locality to be present in your workload such that your caching is very effective. In many workloads, this is not the case today. Okay, so that was a complicated arithmetic operation. Let's talk about a little bit simpler arithmetic operation. This is an add 32-bit integer arithmetic operation. The disparity between a memory access and addition is 6400x. That number is huge. Now, to overcome the energy lost, to amortize the energy cost of accessing data, a piece of data, requires a lot more locality exploitation, which is much harder. Now, we're not even talking about storage. Think about storage. This is memory, main memory. If you think about storage, that's add another 10x over there. We're at 64,000x. We're also not talking about something that's really a big trend today, which is important, I think, making the computation more efficient, like smaller data types. People don't want 32-bit arithmetic. People want 4-bit arithmetic, 3-bit arithmetic, 2-bit arithmetic, 1-bit arithmetic. If you can get away with 1-bit arithmetic, that's much better. Now, the problem is this actually increased the disparity also. So increasingly, the data movement cost is much worse than computation cost. And we have done a lot of studies with Google, for example. On average use cases in mobile workloads, we have found out that more than 60% of the total system energy is spent on data movement. When you're doing web browsing, for example, when you're doing accessing YouTube, when you're doing machine learning inference on your mobile phone. And more recently, we've also repeated the study on machine learning accelerators. Clearly, machine learning accelerators have been used in industry so that you can accelerate many models today, and they have actually enabled us to scale artificial intelligence to larger models. In this case, we're looking at edge machine learning accelerators, and we found out that more than 90% of the total system energy is spent on memory in large machine learning models. Just to give you an example idea, we've studied proprietary machine learning models used at Google, and on large models at the time, LSTMs and transducers, you can see this picture over here. The yellow part and the blue part, they're off-chip interconnects and DRAM. Most of the energy is really spent on off-chip interconnect and DRAM. So actually doing the computation somewhere else, like in memory, reduces that energy, as we will discuss, and can get you much lower energies as shown in this bar, and we will talk about that. Okay, so basically the fundamental problem we have, in my opinion today, is processing of data is performed far away from the data. We need a paradigm shift to enable computation to minimize data movement, compute where it makes sense, as opposed to restricting ourselves to compute where the compute units are currently located. We want to push computation to everywhere where the data resides and where the data may be generated. Essentially, we want to make computing architectures fundamentally more data-centric as opposed to processor-centric, which is what we've been doing so far. And if you look at a computation unit, even an SoC that looks like this, there are a lot of places where we could do computation. We could do computation in the sensors, storage, DRAM. Even within this chip, we're not utilizing the entire chip for computation. Most of that is really memory that's just serving part of the processor. Okay, so we're going to treat memory as an accelerator in the rest of this talk, and we're going to accelerate certain functions on the memory side. We're going to add some specialized computation capability inside the memory. But basically, the broader idea is we could do this anywhere in the system. So we're going to talk about processing inside memory and storage. The processor is going to talk to memory as a somewhat equal partner, accelerator, if you consider that an equal partner. The processor will ask the question, memory, can you execute this function for me? And the memory will say yes or no, and when it's executed, it will return the results. And this is very useful, especially in main memory, because we have huge main memory sizes today. This is very useful inside storage, because we have even huger storage sizes today. Of course, this is not easy, because this requires thinking across the stack. Basically, there are many questions over here. How do you design the compute-capable memory and the controllers? Processors and communication units. How do you design the software and hardware interfaces to enable this? How do you design the system software, compilers, and languages so that you can actually take advantage of it and enable it to the masses, let's say? And then how do you rethink the algorithm so that it can match your computation capabilities in the memory? And also, how do you rethink the theoretical foundations of computing? So it's really an across-the-stack problem over here. And I'll pick on theory over here a little bit, because if you think about computing theory has been developed to be extremely processor-centric. What we do when we quantify the complexity of algorithms is counting operations. But everything I've shown you so far says that maybe that's not that important, today at least. The operation cost is not that much, but data movement cost is much higher. So maybe we need to really develop a new theory of computation that enables us to deal better with data movement costs and data access costs. And I think that's part of the data-centric computing paradigm. Okay, so that said, you may say, okay, this is an old idea. Why are we thinking about it today? And this is an old idea. People have actually thought about a lot of ideas when they were designing computing systems in 1950s, 40s, 60s. And they've written papers that look like this. This is the earliest that I could find in processing in memory. If you find something else, please let me know. 1960s. This is another beautiful paper by Harold Stone, who has a beautiful textbook on high-performance computer architecture. Essentially, these people have proposed these ideas for different reasons at the time. What is different today? Essentially, I think today we have nowhere to escape. We're having huge problems with memory technology, and we're having a huge demand from application systems. I've talked about this huge demand, so I'm not going to talk a lot about that again, but designs are squeezed in the middle today. So unfortunately, memory technology scaling is not going well. Even though we have huge memories today, they're becoming less and less robust, meaning we're having errors inside the memory. Rowhammer is another example that I'm not going to talk about today, but we have shown that you could actually induce bit flips in memory by just accessing memory. This should not be happening. This happens because the sizes of the cell that stores data are very small, and the cells are very close to each other. So there's a lot of electrical interference when you access one cell, and another cell gets affected. So you get a bit flip. So essentially, you can get a silent data corruption. You don't want that. We don't want to build robust systems. We don't want silent data corruption. So how do you solve the problem? Solving the problem is not easy at the device and circuit level. So we actually add a lot more intelligence on the memory side. So we require a lot more intelligence. I'm not going to talk about that in detail, but this is computation in memory, essentially, a form of computation in memory. I've already talked about essentially huge demand from application systems. We have huge bottlenecks due to data movement, and we want to improve all metrics at the same time. You don't want to trade off between different metrics. And this means that we need to do something completely different. So I believe we have nowhere to escape. Application systems are pushing us to do something different because data movement is a bottleneck. Memory technology is pushing us to do something different because we're hitting the technology scaling limits. So that, and if you want to scale further, we want more intelligence in the memory. And I think we're kind of squeezed in the middle. Now, that's why I believe industry is also moving toward this direction a little bit. But before I go into that, I should mention there are two different types of processing in memory. These are two fundamentally different types, in my opinion. One is processing near memory. The other is processing using memory. Now, if you think about processor or logic and then memory, processing near memory says, put the processor or logic closer and closer and closer, and integrate it nicely with memory as close as possible. This reduces the cost of data movement clearly. This is not that different from what we're doing today. What we're doing today is actually one end of the spectrum, process far away from memory, but you could get it closer. Industry is adopting this, I think, hopefully, over time. There's still adoption challenges, but there are prototypes that people have been building. Processing using memory is fundamentally different, and I think it's a very good research area going into the future. This is fundamentally harder also. The idea is, you have the processor and then you have memory. Forget about the processor. Just think about the memory, but think about the memory as a computational device. Every memory has some analog operational characteristics that can enable you to do computation. And this analog computation capability is very efficient because you're inside the memory array. You don't move data that much. And then the question is, how do you actually exploit that capability? In the end, I think we need to combine both of these two so that we can get the highest benefits. So this is the landscape today that, from my perspective. So we have 3D stacking technologies where you can put logic underneath memory layers at high performance and high efficiency. And then more recently, people have started developing DRAM chips where near each bank you have a processor. And more recently, large companies like Samsung, SK Hynix, and Alibaba, in fact, Huang is part of that, have developed DRAM chips that put near-bank processors, more like machine learning accelerators on the DRAM chip. So the good news is there's a lot going on in the industry as well, and there are many experimental chips and startups as well. And we have also interfaces that in the industry, like Compute Express Link, that can enable offloading more easily from the processor to somewhere else, including storage. So let me give you some examples of this near memory and using memory computation, and then we're going to conclude. Essentially, 3D stacking technology is an enabler for computation near memory because you can have a logic layer manufactured underneath memory layers with different type of integration technologies. In the ideal case, they're actually integrated very nicely with lots of connections between the logic layer and memory. Now, if you have this logic layer, you can actually do computation in the logic layer. I'll go through very quickly what we have done in the area, at least just one example. If you have this sort of chip, now inside this chip, you can add processors. You can have a lot of parallel processors that are connected to each other. And what we did over here was actually add a partitioned graph, have graph processing, and we use it as a graph processing accelerator. A graph is partitioned, and if you want to do the computation on a graph node, you actually send the function to the processor that contains the data, as opposed to moving the data between the processors. That's the idea over here. And if you want to scale the system, you need to connect these things, etc. I'm not going to go through this in detail. You can read the paper clearly, but if you do something like this, you get huge performance improvements across many graph processing algorithms.
13x was what we found. Later work actually improved it to closer to 100x. At the same time, you can reduce energy by 8x. That was what we showed in 2015. Later work improved it to also 100x. Imagine we can get 100x improvement in performance as well as efficiency at the same time without even completely specializing. Okay, so that's one example. Now let's talk about processing using memory. There's a lot of interesting work that's going on in the area. I'm going to focus on processing using DRAM. DRAM is a dominant memory technology today, and if we can do something with it, if we can change it so that it can also do computation, we can do a lot. Just a very quick summary. We can do a lot with DRAM. We can do a lot of operations, functionally complete operations and or not majority. We can do data copying. We can do true random number generation, physical unclonable functions. And if you want to do more complex computation, you can use lookup tables. You can do this mostly at low cost using analog computation capability. I'm going to give you a couple of quick examples of that. But the basic idea in some of these is really to activate multiple rows. If you activate multiple rows, you can perform computation. And it turns out you can do this even in commodity off-the-shelf DRAM chips that are not designed for this purpose. Okay, and you get significant performance and energy improvements. We're going to look at that. Let me start very simple, with a very simple idea. This is in-memory copy. Today, if you want to copy one page or one piece of data to another piece of data, you have to go through the processor, at least to the memory controller. Basically, you need to bring the data byte by byte to the processor caches, and then you need to write the data byte by byte back over here. Initialization is a special case of copy. Now, if you take this picture and show it to a 10-year-old, maybe the 10-year-old will say, why are you doing this? Why do you have to go through the processor? Why not just do this inside the memory? That's the idea, basically. The idea is very simple. Just do things inside memory when it makes sense to do so. Now, if you do that, it's a low latency, low bandwidth, no cache pollution, and no unwanted data moment. And you can get, essentially, you can reduce the page copy latency by more than an order of magnitude and page copy energy by almost 2 orders of magnitude if you really optimize it. Now, let me give you the key idea. Again, we're going to exploit the analog operational characteristics of DRAM. Assume that source and destination pages are in this array. You don't need to know too much about DRAM for this, but you activate the source row, which brings the data to the sense amplifiers, which is a buffer inside the DRAM to read the data. And then the idea is to activate the destination row next, such that the data that's in the sense amplifiers reliably gets stored in the destination. Basically, by doing 2 consecutive activations with negligible hardware cost, you can get huge benefits in terms of latency and energy. Okay, so there's more in this I'm not going to talk about. Let's talk about computation. How do you do computation? Again, we're going to look at the structure of DRAM. We're going to go a little bit more in detail. If you concurrently activate 3 rows in DRAM, what happens is you connect 3 of these capacitors to a bit line, and the bit line gets perturbed based on the values in these capacitors. This is basic circuit theory. And then the sense amplifier is supposed to amplify the charge. Now, if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells discharge, you get the discharge state at the end. That means you have a bitwise majority function. If you are able to concurrently activate 3 rows, you get the bitwise majority. That's the bitwise majority. And you get bitwise majority, if you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. Basically, you have basic logic functions in DRAM right now. Now, this is very useful. We have shown that you can actually accelerate many applications like databases significantly. I'm not going to go over these results because we have limited time. But I will point out that this is like somewhat theoretical. When we initially wrote the papers, we said that you could do it, and we showed that you could do it in simulation. More recently, we've shown that you can do all of these functions, and even more than we can imagine, in existing DRAM chips. You buy an existing off-the-shelf DRAM chip, you don't modify it, but you modify your memory controller, and your memory controller violates the timing parameters, and by violating the timing parameters, you can actually perform this row copy very reliably. You can perform AND or NOT, NAND, and NOR in real DRAM chips. This is fascinating to me. And we have open sourced our infrastructure. This is PyDRAM. It enables you to actually offload computation in a real program to the memory controller, and the memory controller violates the timing parameters, and you can do the page copy or random number generation. It requires a lot of effort to build this infrastructure, including operating system effort and hardware effort, etc. If you're interested, we're happy to support it. But you get real results on a real processor like this. This is a RISC-V processor that's only at 50 megahertz. That's why the numbers are huge. But that's basically an example. More recently, we've shown that you can actually do the page copy very reliably. Just to summarize, we show that by violating the timing parameters in DRAM, you can copy one row into many other rows with more than 99.98% success rate, almost perfectly. I should remind you that DRAM chips are not designed to support this. We're violating the timing parameters to show that DRAM chips are actually capable of this. You can perform the NOT operation you can perform AND, NAND, OR, and NOR operations, meaning you're functionally complete. You can build any kind of algorithm on top of this if you know how to do it, of course. Okay, I will very quickly go over this, but basically the reason we can have the NOT operation is because you can connect rows and neighboring subarrays through a NOT gate that already exists. This is a sense amplifier. You activate the source row, and then activate the destination row, and the destination row gets the NOT of A. More generally, by manipulating the bitline voltage, you can express a wide variety of functions. This is one subarray in DRAM, 2 cells, another subarray in DRAM, 2 cells. If you concurrently activate all of them, by circuit principles, what you have is sense amplifier compares the voltage, average voltage over here, and average voltage over here. By storing the right values in A and B, manipulating things carefully, which I'm not going to talk about, you can actually get many functions in real DRAM chips. So we tested a bunch of DRAM chips, and we've shown that you can have AND, NAND, OR, and NOR with more than 94% success rate. I believe 94% is actually quite high. I was expecting much lower success rate over here because DRAM chips are not designed for this purpose. There will be no manufacturer that will tell you to do this on their chips. But I think maybe they should investigate this more and more. Okay, there are other things you can do in DRAM. You can actually generate physical unclonable functions. You can generate true random numbers at high throughput, high efficiency. I'm not going to go over that, but you can do this in real DRAM chips today. DRAM chips, again, don't advertise themselves to do this. You can actually do even better true random number generation. We have some works coming up that show that you can do even better true random number generation. These are actually interesting because one of the important things with processing near memory is you don't move the data much, and this is good for security. So if you can securely process your data completely in memory, I believe that will fundamentally improve security as well. Okay. So you can do more. You can do a lot more in flash and other types of memory technologies, which I'm not going to talk about for the rest, but we have a long book chapter where we actually discuss a lot of these, and we're updating it to be much longer right now. Let me quickly talk about adoption. I think adoption is a very important issue. If you want to adopt these ideas, you really need to think across the stack. We need to think about applications, programming, system and security functions, runtime and compilation support, and infrastructures. I believe all can be solved with a change of mindset. I think mindset that we have kind of very processor mindset is limiting us. I believe we can get there step by step. Now let me conclude. I think we want to build fundamentally efficient architectures. That requires us to be data-centric. We also want to build fundamentally high-performance architectures. I believe that also requires us to be data-centric. I believe we want fundamentally robust and secure architectures. That also requires us to be data-centric, in my opinion, but I'm not going to put that on the slide yet. I believe we need to minimize the data movement in our systems. So I think I've said a lot of these over here. We want to enable computation capability inside and close to memory. I've given you some examples in this quick time that this can lead to orders of magnitude improvements in both performance and efficiency at the same time. This can enable application of new computing systems, in my opinion. I think genomic systems, for example, is very interesting. This can enable a better understanding of nature, because I think nature fundamentally is not processor-centric, and who knows what else. So I think the future is bright, but we still need to do a lot of hard work in science and engineering to enable this memory-centric computing paradigm. And it's good to think about this thing over here. I don't think we want to completely imitate it, but it's good to take inspiration from this thing. I think this thing is not processor-centric. I'll just say that, because I don't know enough about it, maybe. Okay, so I'll leave you with some references over here. We actually open source a lot of things. If people are interested in this work in this area, you can get a lot of open source stuff online. This is our GitHub over here. And most importantly, I'll acknowledge people who have funded our research. And even more importantly, I'll acknowledge my research group who've done this research. You can learn more about them in our newsletters. And I'd be happy to take questions.
We have time for 1 or 2 questions, right? So anyone have questions, just raise your hand. We have a microphone for you. Or you still digesting, or you want to grab him privately? Any questions? Yeah.
Maybe I can ask one question. So you mentioned that the adoption is very important. You are talking about architecture right now. So what do you see that the importance of the software stack and the ecosystem for this?
Yeah, I mean, that's a great question. Absolutely, it's critically important. Because in the end, you can design any hardware. Hardware design, I think people can be very innovative. But if the hardware can be useless. So there needs to be a software stack built on the hardware. And a lot of the adoption issues that I showed over there are really about software, building the software stack on top of it.
Thank you. Maybe I missed it. Have you showcased some
benchmark of the performance on the general calculation like matrix production? Sorry,
could you say?
General matrix production. Sorry. Is there some relation of the general calculation like matrix production?
Matrix?
Yeah.
Multiplication? Yeah, sure. I mean, certainly there are a lot of works that show that you can do multiply and add, multiply and accumulate operations, for example, which is really the basis for matrix multiplication. And also there's analog computing that happens in a lot of the memory devices, like emerging memory technologies, where you can do matrix vector multiplication in the analog domain. So there have been a lot of results that have been shown that processing near memory or processing using memory can greatly improve performance and energy efficiency of matrix operations.
So is there significant improvement in the performance?
Yeah, absolutely. I think you can talk to Yuan, for example. He has a work in ISCA 2016 that talks about that, and many other works. But certainly, the improvements are similar, commensurate with whatever I discussed, orders of magnitude improvements in general. The question is, how do you really adopt it in the real life? How do you make it work with the software stack today?
Thank you. All right. Due to the time constraint, let's thank our speaker again.
Okay.
Yeah.
Thank you.
So let me introduce the next speaker, Dr. Gabe Lo, Le Xiu Wei in Chinese. Dr. Lo is an AMD Senior Fellow, and he's leading the effort in the AMD research on many interesting projects. And today he will talk about the delivering compute for AI in the post-Moore's world. Thank you. Let's welcome our speaker.
All right, thank you very much. It's an honor to be here this afternoon here in Hong Kong. So today I'm going to be talking about a combination of both AI topics and how to build future chips for them. And so I'll start a little bit with AI, and some of this will build on some of the comments that Professor Mutlu had just made as well. So, of course, right now it's just an amazing time with respect to AI. We're seeing already, I think we're just in the very early stages of AI use cases, and there's already lots of interesting things happening. Right, right now we see kind of a lot of fun stuff in terms of generative models and kind of the large language models and different applications there. We're seeing stuff in gaming, but looking forward, there's also going to be a lot of very serious applications of AI as well. So this can be useful for modeling climate change and a lot of the sustainability type of questions that Professor Mutlu had brought up earlier. There's all kinds of cloud applications. You can think about how we're going to apply AI to healthcare, as at least I'm feeling older every day, and all manner of scientific research. Right, and so there's many opportunities where AI can have very real impacts on society. And we're going to see a lot of changes in how we do our jobs. AI is going to affect productivity, in pretty much almost every profession. There are some professions maybe more than others. Some areas like legal services, engineering, science. AI is going to be very disruptive in the coming years. It's going to find ways to make us all just, I think, incredibly more productive. There's some areas where maybe it's not as much, but I think even those areas will see some impacts. Even like food service, maybe there'll be AI systems that can help with food safety and quality control. There's a variety of different applications where today we have to spend a lot of specialized human labor, and instead we can actually have AI make people be far more productive. So I think some of this is to be seen. And so the question is, how are we going to enable all of this? Right. So. One of the things is that AI, the trends have been growing quite dramatically over the last few years. So we'll take a look at some of these in detail. And so for a while, there was already a substantial growth in the earlier days using some of the kind of prior generation machine learning techniques, convolutional neural networks, a lot of vision processing. And even then, we're seeing sort of this exponential increase in the sizes of these models, doubling every year, right? And just remember, the traditional Moore's law says that silicon capabilities doubles about every 2 years, right? So it's already growing faster than our traditional silicon capabilities was increasing. And then with the advent of the large language models, things just completely took off, right? And so now we're actually seeing a growth of like 20x per year in the sizes of these large language models, right? So that means like every year, if I want to be able to build and train the largest model, I have to have 20x more specific weights or parameters inside these models, right? Which means I have to store 20x more data. I have to do at least 20x more computation on that data as well. Right, and that reflects in terms of these models, like how long does it actually take to train these, right? And so it used to be that if you had a reasonable cluster and you had a couple of days, you could sit around and train one of these models. Now you need data center scale computation and weeks, if not months, to train the leading edge machine learning technologies. And this is also just societally challenging too, right? Because not everyone has access to those types of resources, right? And so this has become very challenging overall. Right, and it's not just compute, right? As Professor Mutlu mentioned, energy is a huge factor, right? And I guess the hidden subnote in here is that there's a lot of data movement energy represented by this trend line, right? But again, this is an exponential scale on the y-axis, and we're seeing just tons and tons of energy being used. Where if this continues to increase, we're going to be consuming the entire energy budgets of full countries just to train an AI model, which does not seem like the best use of energy for our society necessarily. All right, so there's some very deep implications of these trends. And on top of that, AI is growing not just in scale, but also diversity. Like, what does it mean to use AI in many different use cases? Right, so this is just a quick example of a few cases of whether it's a cloud or like edge, which you could think of perhaps at like 5G base station or endpoint, which is the devices that you're using every day. And it's just a great variety of different requirements, whether it's from the amount of compute required, the energy, the form factor, et cetera. And so we're seeing not only is it becoming difficult to build AI chips just from a raw scale perspective, but we also have to build many, many different types of solutions as well. Right. And so kind of the net of this is that the demand for AI is just completely outstripping the conventional technology, right? Kind of the bottom line kind of shows this Moore's law growth curve, right? Where silicon capability doubles every 24 months, right? And then in terms of the compute requirement that, conservatively projecting, it's just way, way higher than that, right? So how are we going to deliver all of this AI demand to society when the raw silicon is, at best, several orders of magnitude, downhill from there? Right. And that bottom chart there, that bottom line was the ideal case. That's a historical growth for Moore's law. And over the last several years, we've been facing increasing headwinds in terms of trying to scale that technology. Basically, Moore's law is, in some sense, falling apart. Or some people say it's already ended in some ways. All right. This is a graph showing basically how silicon technology has scaled over time. And for a while, the orange line shows the density, right? That you're basically getting this exponential growth. You're getting more devices every generation of silicon. But a couple years ago, we started hitting a little bit of a slowdown there. We see the orange slope falls over a little bit. So we're still getting an exponential increase, but the base of the exponent has reduced, right? So you're not getting as many transistors generation over generation. That's at least partially offset by the blue line in that every generation, the devices, the transistors were still getting more energy efficient. So I was getting more devices, and they're costing me less energy per transistor to operate. But even more recent, in the more recent times, it's happened a little bit before, after the orange curve fell over the knee. We can see that the energy efficiency scaling is also slowing down, and that's very alarming, right? That means in the future we're getting fewer transistors per generation, or fewer additional transistors per generation, and they're also not increasing in efficiency at the same historical rates, right? At the same time, the world wants more AI compute, right? So how are we going to deal with this? And if that wasn't bad enough, there's other challenges. Even though the transistors are getting smaller and smaller, we're getting more and more generation over generation. Not all transistors or not all circuits are created equal. And so, for example, we use those circuits to build analog devices, memory, a lot of the memory, as Professor Liu had highlighted, and then some portion of that is the computational logic. And the SRAM, which is used in a lot of the on-chip storage, the density of that is actually slowing down quite a bit. So even though I'm getting more transistors per chip, if I'm using those transistors to build the storage, I'm not actually getting the same density benefits as I used to get. Logic is still doing pretty well, but even that's falling off a little bit of the traditional curves. At the same time, we're getting fewer transistors per generation. It's costing us more, right? One of the the powers of the original formulation of Moore's law was that we get twice as many transistors per generation, but the secret was that at the same cost, roughly speaking, right? So in the old times, building a chip of a certain size costs about the same no matter what you did. And so if I get twice as many transistors, I'm basically paying half the price per transistor every generation, right? So Moore's law was just as much of an economic statement as it was a technical statement. And that is just falling apart all over the place now, right? So I have to wait longer to get my transistors. When I get them, I don't get the same growth that I used to. And then the chart on the right is showing that I'm paying more and more and more over time, right? So that makes it economically very challenging to build products that can serve these markets in a way where companies can be profitable and not go out of business. At the same time, beyond just building these, I don't have to belabor this too much given the previous talk. The amount of power being spent on memory accesses is just also increasing dramatically, right? And it's one of those things where every joule of energy I spend on moving data is a joule of energy I'm not actually doing computation, right? Moving data doesn't compute anything, right? It doesn't teach you, right? You don't learn anything from moving a bit from point A to point B. It's a computation where the magic happens. And so every amount of energy that we're not doing on compute is in some sense wasted, right? Wasted opportunity. So, where are we going, in terms of trying to address all of this? So there's been several innovations over the past few years. I'll talk about, some of the recent work that's been done to try to address some of these challenges of scaling silicon systems, and then I'll talk a little bit more about the future too. So, just for the audience, if you're not deeply familiar with silicon manufacturing, basically what happens is you start with a big silicon wafer. Today there's 300 millimeters in diameter, and on that you basically photolithographically print a whole bunch of smaller chips. Right? It's at a big wafer. You get a whole bunch of little chips, and what you do is you cut them up or you dice them. That's where the word die comes from for the chips. Right? So you get some number of chips out of this wafer, right? Once you have these chips, you do some testing to figure out which ones work, which ones don't, because the manufacturing process is non-ideal. Defects do happen, unfortunately. The ones that don't pass the test, well, you basically have to throw those out. Whatever's left over, you take those, you package them up, and those are the processors that now you can sell to into the market as as your regular products. So the problem is that if those chips are really big, every time you have a defect, you have to throw away a large amount of silicon. So an alternative to this that we've been using at AMD is this kind of approach that a lot of people call chiplets. Right? Instead of building one giant chip, what you could instead do is build a bunch of smaller chips. Right? And with these smaller chips, we can basically get more of them per wafer. Roughly speaking, you end up with about the same total absolute number of defects, right? But each defect is only going to cause you to throw out a much smaller amount of silicon. And so with whatever is left over that's still functioning, we can reassemble these into proper systems, and now we actually have a larger number of chips that we can manufacture. Right? And so as we move into these new technologies that are costing more and more, it's really important that we maximize how much useful silicon we can get out of each one of these wafers. And chiplets is a technique that allows us to do that. What's also kind of neat is that once you take a system, a computer chip, and you break it in smaller pieces, you can start specializing. Right? So one of the things we did was that we can take our computational cores, the CPU cores, and we build chiplets that have just those cores. That's what we call the CCDs, or the core complex dies. And then for all the other stuff there, your memory controllers, your PCIe, all this analog stuff that doesn't require the latest and most expensive silicon, well, you can manufacture that on an older technology node. And so our I/O die actually uses a cheaper, more mature silicon technology, and we can mix and match them. Right? When you build a single chip, the whole chip has to be using the same technology throughout. Right? But once you break it up, we have a little bit more options here. Another cool thing is that with traditional silicon manufacturing, we use a photolithographic process, right? And that basically, you have to shine light over a certain section of the silicon wafer, and there's just a limit to how big you can do that. It's called the reticle limit, and it's a little bit more than 800 square millimeters. However, once you start breaking things up and reassembling them, I can actually build more than one, reticle's worth of silicon and reintegrate it, right? So normally, if it's the same type of thing. If I want to build a really big cake, and I have, just a cake pan, right? That limits how big of a cake I normally can make, unless I'm willing to make a whole bunch of smaller pieces and put them all together. And once I do that, I can build an arbitrarily large size cake if I want to, right? So we're kind of doing something similar to that, where we can build much bigger systems than the traditional single chip approach would allow you to. And so this actually comes up with a lot of really interesting, cost benefits from it, right? So what we have here is that on the chart, it basically shows, what would it cost if you were to build a 64, core system using our technique. That's the blue bars. Or you can build fewer cores. And what we did was, because each of our chiplets has only 8 cores, you can vary the number of those chiplets, right? If I only have 2 chiplets, I have 16 cores. If I have 3, 4, 5 chiplets. And this is really nice because in the past, if I wanted to build a 16-core server for some customers, a 24-core server for some other customers, et cetera, each one of those had to be entirely separate design with different engineering and different manufacturing, different testing. Now I only have to build 2 chips, and I can just vary how many of one of them is, and I can provide a whole a bunch of different products all at once. And then there's a huge cost benefit. The orange or the red bar shows what the cost of that equivalent chip would have been if I built it as a single chip without using this chiplet approach, right? And you see it's substantially more expensive to try to build it as one big thing, right? And again, it's because if I have a defect, I have to throw out a much larger piece of silicon. And there's no red bar on the 64-core side because that one's so big that you wouldn't be able to manufacture it with the traditional monolithic approach. Right, so kind of a couple key insights to take away here. Taking a big system and breaking it into smaller pieces with chiplets, allows you to build larger systems than you traditionally otherwise could. Doing this allows you to mix and match different technologies, which gives you cost and other benefits. And then by having this kind of modular design approach, we can actually have almost this Lego building block type of approach where we can vary and just change how many of these chiplets. We have more chiplets, fewer chiplets, and really quickly and easily deploy a wide variety of different products. Right, and that was kind of an earlier version of this, but we've been taking this further and further, right? So we've actually, in our latest generation, we have 16 of these CPU chiplets coupled with this big I/O die, and so we can really scale this, and you can build these big, massive systems with what are still fundamentally relatively small and simpler to engineer components, right? If you want to build this as one big traditional chip, it would be just very, very, very expensive, very difficult to do. Okay, so that helps address kind of the scaling of the silicon part of it, but that's only one piece of the equation, right? Memory is still a huge problem. In traditional servers, many of them are still using DDR memory. DDR provides maybe a few hundred gigabytes of bandwidth, but these AI and machine learning problems require terabytes per second of bandwidth, at least using memory systems, maybe with processing and memory and such that'll change the requirements, but until that becomes a wide-scale technology, we're still stuck with kind of more traditional moving bits from point A to point B. One of the key limitations is basically the package interface, right? The processor only has so many pins, right? It's just like this room has only so many doors, right? If you want to get a lot of people in and out of this room, it'd be better if we had more doors, but there's only so much space on the walls to do that. And so one of the approaches that has been advocated and actually been acted on is called in-package memory, right? If the memory is hard to get to because it's outside of your package, Well, one perhaps naive way is you bring it inside a package instead, right? So you bring everything inside. This gets around the limitations of the pins, the limited number of pins you have in the package, right? Same thing, like we have the drinks outside. If we all wanted to go get drinks all of a sudden, we all have to go through the doors. Another approach is just bring all the drinks into this room, and it'd be a lot easier, a lot faster to access. And this is enabled by a variety of different advanced packaging technologies. I'm not going to go into the details here, but there's a lot of just really interesting manufacturing techniques that allow us to mix and match the silicon or different pieces of silicon, processors, and memory all within the same package. One of the problems, though, is just even if I can bring that memory into the package, I still need capacity, right? For example, one of these chips can provide about 2 gigabytes of memory, but the size of these memory, the machine learning models is growing to be much, much larger, so we need as much capacity as possible. And so one of the approaches is to use 3D stacking, right? So instead of having just a single layer of memory, we can actually stack multiple layers on top of each other, right? So now a single stack can give me 16 gigabytes of memory in the same amount of area that original 2 gigabyte took, right? And this should be very natural approach, right, for everyone living here in Hong Kong, right? It's a very limited land mass. When you don't have enough room, you go and you build vertical instead, right? It's kind of similar here. You're kind of boxed in this package. You don't have enough space to put very many of these chips down, so you have to stack them up. Okay, so it's a real estate solution, right? And so one example of how we put this all together is in our MI200 accelerator, right? So this is basically a GPU compute style accelerator that can do a lot of both HPC as well as AI type of computing. And we basically took what would otherwise be one large GPU, we broke it into 2 separate chips, and then we combined that with 8 separate stacks of this 3D stacked HBM, right? And overall, this provides a lot of compute, a lot of memory capacity, and a lot of memory bandwidth, right? Over it's 3 terabytes per second of memory bandwidth, right? Again, perhaps Professor Wen will argue it'd be better to not move that data at all, but at least for now, for the current AI models, this is kind of the approach we have. So, how do we go beyond that, right? So this is already kind of what we're currently have. Well, actually, the MI200 is now about 2 years old, right? So we want to be able to build even larger systems to handle these monstrous large language models, right? And so one of the challenges is the fact that this package here, we've kind of run out of room, right? This is already a big package. You can make it a little bit bigger. The mechanical engineering challenges become quite difficult, but you might make it a little bit bigger, but you're not going to make it 2x bigger, 4x bigger, 10x bigger to get that generation over generation capability that you really want to keep up with the growth of AI. So one of the approaches is, well, we did 3D for memory. We could do 3D for the logic and the computation as well, right? Actually, this is the same picture the owner had earlier, right? So one of the things that the HBM memory, the 3D stacked memory, right? We're already putting 8 layers of silicon on top of each other, and that technology though uses a different approach, or a bonding technology called micro bonding, right? So there's actually these micro solder bumps that provide the electrical connections from one layer of DRAM to the next layer above it. And the spacing of it is roughly in that 40 to 50 microns in terms of the distance from the center of one connection to the next connection, which is enough bandwidth to move the data in and out of that 3D stacked memory. It also has a relatively high thermal resistance, right? Because you have this material that has to fill the gap in between these solder bumps and insulate it and everything else. And so that basically is like having like an extra blanket in between every single layer of your memory, and that becomes potentially thermally challenging if I have something that's consuming a lot of power. Thankfully the DRAM doesn't consume a ton of power, and the power density is not so high, so when the memory manufacturers stack it all up, it stays thermally under control. But if we want to use 3D stacking for our logic, that becomes more challenging. So thankfully there's a new technology called hybrid bonding, which actually provides much denser interconnects. So it's basically instead of having these micro solder bumps in between the layers, the different silicon die are able to basically be placed face-to-face directly against each other, almost at the atomic level, without any kind of interconnects or any other material in between them. And so that allows us to build really, really dense interconnects. The first generation, it's 9 microns, and so that's already about a 5x improvement compared to 40 to 50 microns, and that's in each dimension, right? So 5x in the x dimension, 5x in y dimension, that's a 25x increase in the interconnect density. And then the thermal properties are also much better because we got rid of that underfill, the material that's in between the layers, since the two die are directly bonded face to face, right? So we use this in this V-cache technology for our processors, where we can stack additional cache on top of our processors to build these giant L3 caches. But we can do that for our other logic and such too. All right, so the MI300 accelerator, is basically this. It starts with this kind of this base, level of silicon, right? This piece of silicon has no transistors. It just has some metal interconnect, right? Just to help hold everything together. On top of that, we can stack all of our 3D, in-package memory. So each of these is a 8-layer, 8-tall stack of DRAM. Then on top of that, we also integrate these our I/O die, right? So this is basically has some cache. It has all of the memory controllers to the in-package memory. It has all the I/O interfaces to connect it outside the world. And this is implemented in an older technology generation, like I mentioned earlier, because it's not doing the main compute. And then on top of that, we can actually stack all of our compute chiplets too, right? So this is what does all of the AI compute, all the machine learning, matrix multiplication operations, and all the other compute that you need. And so, by going 3D on the logic, we're now able to, continue scaling and pack more silicon into, roughly the same amount of area, right? Now there's a question of how high can you go? You can stack 3 layers, 4 layers. If you look at the skyscrapers around here, that suggests maybe you can go a lot higher, but that does require a lot more innovation, right? To do heating and cooling and electrical distribution in a 100-story skyscraper is very different than what you do in a 1 or 2-story building. And so it does require new engineering, new innovation to keep scaling these things up. What's also really cool is that with this modular type of approach, where we can have these chiplets and we can stack them on top of each other, is that it's also allowed us to build new products pretty rapidly, right? So one of the products we have, we actually take away 2 of these GPU chiplets. Pressing the wrong button. Right, so we take away 2 of these 2 GPU chiplets, and instead we can put our traditional CPU cores there instead, right? So we actually can mix and match these different parts, right? And what's really, really cool is that we didn't have to design a new CPU chiplet. We're actually using the same ones from our CPU server product line. And by just mixing and matching them, now we actually have this heterogeneous compute architecture that has a mix of both CPU and GPU. Right? This can help some of those data movement type of problems. When I have a CPU working on something and I need to move some of that data to the GPU, instead of having those be in entirely separate packages, I buy a CPU and I have a GPU, now it's just all in one, right? That CPU can communicate directly to the GPU components without having to go long distances. And so there's some really interesting things that you can start doing once you really break down a system into multiple parts, having them have reusable interfaces where I can mix and match things together. So I'm running out of time here, but I think really going in the future, right, that what we're going to see is that as we mix and match all of these silicon components and build these bigger and bigger systems, one of the requirements going forward is that we're going to have to all work together a lot more closely, right? In the past, we can really just build the processor and let the software people do the software stuff, let the manufacturing and platform people do their stuff. But with all these components, there's a lot more interactions, and we're going to see, especially with the evolution of machine learning algorithms, the different data formats, the different algorithms, those are going to drive different architectural requirements. That's going to have different power implications. That's going to have, how we package these things together is going to have thermal cooling, and all of this stuff has to run in a big cycle. And I think that's really going to drive the need for a lot of both our STEM education as well as the research programs that we're driving to really become much more interdisciplinary and a lot broader than they've perhaps had in the past. So I think it's also it's a fantastic time to be in computer science and computer engineering. There's just so many really interesting and deep research problems for us to all tackle, and I think we all need to tackle them if we're going to do this going forward in a sustainable fashion. So with that, thank you very much.
All right, we have time for a few questions. Yeah.
Dr. Lo, thank you for your interesting talk. I'm Shi Liu, a student of Professor Xie's, and I see that you talked a lot about the chiplets and the hybrid bonding and something like that, and they are very hot topics nowadays. And considering that industry has already integrated those technologies into their products, what do you think would be the opportunities for the academia, especially considering that industry has a lot of experienced engineers and will do much better engineering than the students in academia? Thank you.
Well, I think you shouldn't assume that the industry engineers are always going to be better. I think there's always new ideas, new perspectives from the students and from professors. What I would say is a very good question. That my response to that is right now, a lot of what we're doing, we as industry, not just AMD, I think it's still very early days, right? The way we've decomposed the system into chiplets, the particular type of architectures we're doing this is just stage one, right? And I think there's a huge amount of opportunity to be more creative, to come up with, because in industry, our job is to deliver products, not necessarily to come up with the most creative solution, right? And as a result, we're not always going to we're not always going to try to build the craziest thing we can think of, right? Because there's real risks, there's schedules, there's engineering costs. And so in many of the things we do, I think they are very innovative, but at the same time, we don't always push the boundaries anywhere close to what they can be done. And so I think there's a lot of really interesting things to be done, both on the architecture side. What are new architectures that can exploit and really take advantage of these different technologies? And then, really kind of talking about my last slide there, what we're building is still very much architectures for the software ecosystem as it exists today. What changes can we make in the way we, everything from the algorithms down to the software and everything else? If you can change that with the hardware at the same time, what could you do? What additional opportunities would that unlock, right? Because there's everything from the algorithms to the fact that the operating system still uses 4 kilobyte pages or whatever, right? There's so many legacy constraints on how we think about architectures that have to be sold today, right? And I think when you unleash yourself from those constraints, the opportunities are immense.
Any other question? Lady first.
Thank you so much. And I am an undergraduate student from Sun Yat-sen School University, and I have 2 questions to ask. One of this is from the PowerPoint. You mentioned the architecture package co-design that enables flexibility, and well, I was wondering which specific parts that needs to be co-designed in this design, and what advantages can it provide, and what difficulties it may counter, because I think the people that are doing research in computer architecture can have little knowledge of the knowledge of packaging. And that's the first question. And my second question is, I'm curious about what AMD is doing about facing the problem of the heat management, the serious problem in 3D IC. And is the company willing to choose to face with this difficulty of heat management, or they just choose to avoid this kind of challenge and may choose to bigger chips on bigger silicons like Cerebras do?
Okay. Yeah, so for the question in terms of the challenges with packaging co-design, right? I think there's a kind of two sub-questions there. One was, how do you do research when, many computer scientists, don't necessarily know all the details about the packaging, right? And I think that's where, collaboration is incredibly important, right? I'm not a packaging expert either, but I talk to and work with a lot of people who are, and I can give them my problems, or I could give them my ideas, and they can tell me what's wrong, what's broken, and we can work together to figure out if a solution exists, right? And so it's something, and then there's another sub question in terms of like what are some of the problems or opportunities that related to the packaging, right? So some of the challenges are for example in like the power delivery, right? If I have many different chiplets that all have different power requirements, then I have to design a more complex package that can deliver different voltages and whatever is required. I think there's also opportunities where you can perhaps consolidate or amortize some of that stuff, where if there's common needs for some of those chiplets, you may be able to build common infrastructure for them to all share. So the second question was?
Heat management.
The heat management, thank you, Yuan. Yes. Yeah, I should have remembered, it's very warm up here. Yeah, so with the heat management for 3D stacking, it's definitely something that has to be done very carefully. So one of in our products, we've only carefully used 3D in certain specific kind of arrangements where we are able to control the thermals, right? So in the 3D stack cache, what we actually do is we only stack the cache on top of the other cache because the cache has relatively low power density, right? The CPU cores themselves, where all the compute is happening, that has much higher power density. So on top of that, we only stack passive silicon with no actual power consumption, right? And that just basically acts as a heat conduit to get the heat out of the cores, right? In our MI300, we're stacking logic on logic, but all of the compute is on top where it's closest to the heatsink. And the bottom layer is, again, mostly cache, which is lower power density. There's some data movement and some other infrastructure down there. But we're very carefully adjusting and thinking about what goes where, how much power is consumed by each of these things. And it is something that has to be thought about from the very beginning of the architecture. Right? And that goes back to the need for more co-design, more cooperation with the experts of many different types.
All right. One last question. Okay, give you a quick question. Okay.
Yeah, thank you very much for this amazing presentation. My name is Ethan Zhang. I'm working for a Chinese entrepreneur organization, and I used to work for Samsung. So I have some understanding of this field. I'll ask you a question from a geopolitical perspective. So, how large is the gap between US and China in terms of AI computing and the packaging? How wide is the gap right now? And also, how effective is US sanctions on China's, this AI chip, this industry? And do you think China would have a chance to catch up with the US in this term? Thanks.
So, I mean, the short of that is I'm not authorized to speak on those matters, but I think, and I think a lot of the answers to those questions are honestly unknown at this point. How effective is it? I don't know. I'm not sure if anyone really knows yet. I think in terms of, I think there's a lot of discussion that is, I think, not productive in terms of, people talking about, the AI race, right? I don't think it's necessarily a race, right? Because in each, field, in each country, in every, potential application of AI, there's very different, requirements and objectives and needs and opportunities, right? And so everyone is going to be running in a different direction, right? There will be some commonalities, but I think a lot of the really, socially transformative AI use cases are going to be different and tailored for kind of every country, every, industry. And so, I don't have a direct answer for, what you asked. If I knew the answer, I probably wouldn't be allowed to say it anyway. but I think, in some sense, I think, you know, it's not just you. It's like the entire, you know, global discussion, I think in some sense is not focused right? I think it's really about, you know, each of these cases, like, you know, how do we get to the AI that makes, you know, that use case more productive, more valuable to society, to the world, right? And I think when you view it that way, you know, it's not so much of a race. I mean, like, each of us are trying to get to a solution for our problem as fast as possible, but, you know, my problem is not the same as your problem. It's not the same as Professor Xie's problem, right? And so I think there's a lot more, you know, opportunity out there.
All right. Due to time constraint, let's thank our speaker again. The next speaker is Professor Wang Yu. He's from Tsinghua University. He's the department head of the Tsinghua University Electrical Engineering. Let's welcome our speaker.
Thank you very much for the introduction, and I'm honored to be here. And I will talk about, maybe touch a little bit about the last question. Yeah, because I am more on the accelerator design, and also touch a little bit about algorithm and a little bit about the circuit design and a little bit about the system design. So I will be the bridge from Gabriel to Professor Ma Yi. So this is my contents, and first one is talking about the AI. So this is one of my favorite books because everybody has their own definition about the AI, but I find this one is my favorite. So in this book, Thinking Fast and Slow, people are trying to separate two systems, define two systems. One is system one is the brain fast, automatic and intuitive approach. For example, there is a hot water, I touch it, and I bounce my hand back, and this is very fast. So for the system two, that is slower, analytical, and there will be reasoning, right? Because, for example, I'm here because Yuan Xie is my formal advisor. He said, hey, you need to come here. Then I come here. And then I'm thinking about, okay, in this circumstance, how can I speak, especially for the third question, right? So this is from my what I'm thinking. Then I organize my presentation. So this is the system two. You need to think a lot and do it not that fast. So it's thinking fast and slow. So why I'm talking about this is because actually I'm not that not a fully algorithm guy. I'm not doing the theoretical research in the AI era, but I'm more working on the system or the chip design. For the system or chip, there are people are working on how to define the F, right? So every system, including your phone and your PC, and every system is a Y equals Fx, right? In the very, very beginning, that is the AI step one, because in China, we call the PC 电脑, right? Electrical brain, right? So that is the AI very beginning. So at that time, you try to break the F because you can expressively written the F into equations. So then it can be break down to addition, multiplication, and moving the data around all the very basic elements, that is the instructions. Then you build up the CPU. So you build up all the CPU for different F. So then people are trying to make the CPU faster and faster. So that is doing fast computation for every F. So this is the first period. That is about maybe when I doing my PhD, that is in 2002, 2007, that could be people designing the multi-core. That time is AMD and Intel. I think it's 2005, something. AMD and Intel all present their multi-core processor, right? So that time. And for the second step is the perception. There is the system one built up. For example, SenseTime, right, is a Hong Kong company, which is founded by Professor Tang Xiaou, who is very famous for the face recognition, right? So for face recognition, you cannot write an equation for the, or explicitly write a physical equation for the face recognition, but you put X and Y into the system and use a neural nets to fit the f, right? Fit the function. So then you can do the y equals fx. So for this figure, you can see that, okay, we can see that the chess board there. So this is finding the content, right? Finding all the objects. So this is the second step that we define it as AI 1.0. So you use different data for different domains and train different models, right? And at that time, it's about beginning, I think, 2011 and 2012 to boost this face recognition or image recognition by the ImageNet, and also the voice recognition, boosting voice at the very beginning of 2011, 2012. So I try to work with my students working on how to use FPGA to accelerate the convolution neural network and also the deep neural network, and found a company called DeFi Tech. And finally, it was acquired by Xilinx in 2018. So then it becomes AMD, right? Because AMD acquired Lattice. So I have some connections with Lore, right? So we are all from AMD. Yeah. But after that, that is 2018. So after 2018, I talked with my students, just like the first question, talking about, hey, the industry are designing chips. What should the academia do? Then back to the university, my students are thinking that, okay, now we can do the face recognition and all the fittings by label data, right? What is the next? How can we we can recognize every subject or every object in the one figure, but then can you deduct some of the relationship between this object? So then we think about, okay, at that time there's no, or we don't find out that, okay, transformer is good. We don't know that, but we find out that, okay, there is a knowledge graph and deep learning. Putting them together, maybe you can find relationship between the object and do the cognition thinking. So this is the AI step 3, and for my perspective, now becomes LLM, transformer-based LLM dominated. So I'm more focusing on the computing chips, or combining the algorithm and data and the chip together. So we are building up the system. So, and the AI 1.0 and AI 2.0, I've already mentioned. The first one is a point to learning the discriminant task for when you provide some data for one domain, and you train the dedicated small models for that domain. But for now, for transformer-based or the LLM part, you try to give all the models, all the data, and learn the general model for the generative task. Take an example is at very beginning, you are trying to use the law data to train a lawyer, right? Now you try to train a person with all the world data, and use some of the law data to turn a person into the lawyer, right? So it's quite a different way. So I think it's very interesting. So now we move to the AI 2.0 part. But this one requires scaling law, right? So they say, hey, if you try to do more compute and have more data and for more parameters, you will have better performance. So but till now, I think it's still true, but maybe in the next 2 years, it's not true, right? And I think Professor Mai will talk about it. He's thinking from the algorithm view, but for me, I think still having this scaling law. But I'm from mainland China, right? We don't have that much GPU, right? So thinking about if everyone in China use one big model or foundation model in China at the same time, the total requirement of the computing power is not enough. The gap is about 100 times. So this is the current situation. So because we built up a lot of CPU-based data center, but the GPU or the now accelerator-based is not that much. So, and for the future, if AI plus every industry becomes true, then we believe that it will consume a lot of power, right? Maybe at that time, when it's mature, only 20 or 30% is the training cost, and 70 to 80 is the inference cost, because everyone is using the models, right? So this is a weird, but it still demands a lot of energy consumptions. So what I'm doing, we are trying to using the co-optimization to lower the power requirement when you do the same task. That is the boosting the energy efficiency. So the energy efficiency, there is a equation there. So before that, people are trying to design algorithm first, and then design the chips, and then the system. But now, because you need to open the two optimization space, both the algorithm optimization space and the circuit optimization space together, there will be, you will find the best solution. So because AI algorithm is learnable, so you can jointly optimize algorithm and hardware to improve the energy efficiency, maybe a tenth or 100x. So I will try to give a little bit detail about this part, because this one is from my last 10 years, maybe from 2012, when we tried to design the system for the AI 1.0, we use this methodology. The thing is, because for AI algorithm, or the neural nets only have two things. One is the connections, right? The other one is each connection has a number, so you have the quantization. So you can use pruning to cut some connections, or using the quantization to make the workload smaller. So this is the first thing. And then if you have a fixed area, then if you can have 4-bit multiplication, then maybe it will be 10 times smaller than a 16-bit or 32-bit multiplication, right? So you will you will improve the peak performance, right, in a fixed area. And also you can try to optimize the memory usage, or doing the hardware design and compilation optimization to boost the efficiency. That is, you have 1,000 core, then how can you make 800 of them working together, right? So you lower the workload, boosting the peak performance, and boosting the efficiency. Then you can have the best performance for the system. So this is the methodology we provide in 2017. So when I see the LLM, because my students say, hey, there is LLM, should we do it or do something to optimize for LLM? I just ask him, hey, do you see any methodology change from this figure? We find out no. Because still, what you can change is structure, that is the connections, and the data format for each of the connections, right? And you cannot put that large network into a small hardware or into a big hardware, because the algorithm becomes larger, right? So there's a huge gap between them. So we try to think, okay, let's do it again. Then we do it again. We find out that, okay, for each of the steps, we can have some of the improvement of the data usage. For example, you can shrinking the models, and you can pruning the data structure. You can use 3-bit or 3.4-bit to have the same performance, and you can designing a specific architecture to be better performance. And you can also, this is for the FPGA, then you can have 20 to 80x improvement. When you put it into silicon, then you can have another 10x. So that is almost 1,000x, right? So you have a lot of space to lower the cost of the LLM. So then we try to do some experiments. So for example, we try to have different cars working together. So this one is relating to the question you asked that in China, how do we do that? Because in China, we don't have that much NVIDIA or AMD cars, so we have to mix them, right? So some of the mix is trying to use NVIDIA and the Chinese car together. But different cars, right? So how to split the task and put it all on the cars and have the similar performance, just like have all the NVIDIA, right? Yeah. So this is what we do, and we have nearly a pretty good utilization, mixing them together. And also, we are trying also for the serving part. So for serving part, you try to do the batching, scheduling, quantization, and do some algorithm level spec decoding and prefix caching. Then you can also have about 30x, because you need to lower each of the core for one LLM, right? Then people can use LLM whenever they want. Otherwise, you need to pay more. So this is a cloud part, training and the inference. And for the edge part, I think people now are having your own agent soon, maybe this year or next year. Definitely, you will have it on your phone or on your AI PC. And this is a very big market. So phones, AI PC, and the cars, they will all have LLM inside. So should we compute this part on the cloud or on the edge? So this is a very interesting question provided for all the chip makers and the application makers. So what we are trying to do to try to optimize the LLM on the existing AI PC chips, for example, Intel one and AMD one, and we can have about 30% or well, for higher precision, FP16, and also for about 10 to 20% for the Int4. So which seems not that much, but thinking about AMD and Intel have a lot of engineers, right? And we only have students, right? So it's a pretty good result from my perspective. And we try to summarize all the chips published or in the industry, and we can try to predict the requirement for the future ones. So this is a summary paper. So if you are interested, you can read offline. And for example, if we think that for AI PC requirement, it should be larger than 100 tokens per second for a 7B model, and the energy requirement and also the chip should be less than 20 watts. So that squeezed into the small area, or you don't have a very thicker your PC. So in China, we have a lot of different models, right? So I think in US it's the same, right? But in China, we have different GPUs. So this is not the same in US. US only have NVIDIA and AMD, and the others are very small. But these ones are pretty big and quite similar. Huawei is the biggest, and also Capricorn, Huang, and vice versa. So how should we utilize all together? So this is what we are trying to do. So every country has every country's own problem, right? We need to try to utilize our own technology to boost the utilization of all the silicons, right? To have our models trained and all the application or the LLM to do the inference. So what we try, I try to have some of my students back to from Ali and other big companies who say, hey, let's do a small company. And then we try to link the models and the platforms together. So for the last year, we tried to group the people together and founded the small company called Infinigence. And now we have office in Shanghai and Beijing, and also one starting in Hong Kong. So this is for the AI 2.0, the current situation. And I will talk a little bit about the future. I believe Ono has talked a lot about processing memory or near memory computing, but I also agree that this is the biggest problem. Also, the packaging is trying to alleviate the distance of the data and the computing. You can see that the very beginning of the AI 1.0, the moving data also consume most of the power consumption, right? So there are different types of processing near or in memory, right? Analog and digital and near memory computing. So I'm not going to detail. I'll take one example is the analog domain PIM, and that is try to use the voltage as the input, and then you program all the matrix, because the neural nets are matrix, right? So the neural nets have their matrix, and all the every elements of the matrix turn into the memory, the conductance, and then you program all the conductance with the matrix elements, and then the vector input vector is the input voltage, and if you get electricity on, then you will have, because Ohm's law, right? You will have the current out. Then you do the vector and matrix multiplication very fast, right? So it reduces the data movements and improve the energy efficiency. This is about 10 years ago. Yeah, in 2013, when people told me, hey, this is very interesting. We have built up a memorist crossbar. Let's build a system. I say, okay. And then we find out that a lot of things need to be done. For example, the device is not ideal, right? And it's analog computing. So now it's digital, right? So you have digital, the analog. And if you want to have a larger analog system, then you need to cut the system into small crossbars. And at each of the boundary, you will have to memorize the current, then how to memorize the analog value. So it's very difficult. So you need to turn it into digital and then to memorize. Or you will use the inductance or capacitance. So the ADC and DAC, it takes a lot of the energy and power consumption. So from 2013, I put about 10 students and working on the architecture design to show maybe it will have, because they say, hey, you have 1,000 times improvement. But finally, 10x is okay, right? And co-optimization, fault tolerance because it's not ideal, and simulator design because you don't have EDA tools, and AD and DA optimization because you have the interface problem, and you need to build up some of the test chips, so I do some chip design and security and logic. But of course, we do a lot of research, and we have some very good students graduated and get the best students in Tsinghua, blah, blah, blah. But we don't do the entrepreneur based on that because it's too difficult. Yeah, but still we are trying to write papers. Right? This one is the recent paper we write with the Huang, Professor Huang Wu, and the published in Science is still we can do something about that. And we see some PIM industry in China and also in US, but it's still trying to develop. And the other one I think is the robotics. So in 2018, when I saw my first company, I talked to my student, hey, you can see that for this one, because I'm from EE, yeah, I'm not from computer science. So from EE, we try to, we like the embedded system. So if it's embedded system, you have limited battery. So for a limited battery system, you can only do a few things. So one thing is you boost the energy efficiency. And the other way is to make more agents working together. So in 2018, I tried to have some of my students working on this direction, how to have more robots working together, to have more intelligence. But this one, I find out, okay, that is the extension of the equation y equals fx. Then if after you have the decision of output, you need to interaction with the physical world. So then it's the G, right, GY, and you need to execute. So how to do the execute, right? So this is embodied AI and vice versa. And the other one is different agents have different input or different data. So how to have them collaboratively work together. So that is the different acts. So for this part, we found out that, okay, the paradigm shift is still from equations to data-driven, right? Or combining the equation-based control to the data-driven and the equation-based control together, right? So this is a Feifei's talk, TED Talk, which I find very amazing. So I encourage all the young guys to listen to it. And the data-driven promotes the biological intelligence. And now, maybe you can use it for machine intelligence, especially the collaborative intelligence. So we can find out that, okay, for the lower side, the robotics are trying to learn what the environment looks like and where he is. And upside is how to do the decision. But now, after 2023, you can see that it's a sensing, decision, control integrate together. So people have the humanoid-like robots or others. And I think future is putting all these together to be working together. So this is very interesting direction for the system. So this is my last page. So I think what is very interesting is to support the large LLM to move on. So you need to supply efficient computing power or cost-effective computing power to make it happen. And the other one is we need to build up data infrastructure to push forward the hardware of the robots to work together. Yeah, that's my talk. Thank you so much.
Questions from the audience? Yeah. Lady first.
Thank you for your wonderful presentation, and I have a question. We all know that recently large language models and Zoler are the most popular AI application. And my question is, what will be the next popular AI application?
Yeah, actually, I don't think I'm the right person to answer the question, but for what makes me interesting is to having my own assistant. So it's very, very good because the last time I driving back from one place to another place, and I tried to think about a lot of things, and then I cannot write it down. Then I call my secretary on the phone and say, hey, you just get a paper and write down what I told you. And then send me email, right? You just thinking about that, can be done in my car by AI, right? This is very, I do think they will happen this year or next year. Yeah, so I'm very excited by this.
Personal co-pilot.
Yes.
Any other questions?
Okay, thank you, Professor. We have do a lot of work about the LLM inference accelerator these years, and but I'm really confused about the token generated speed has beyond the token we read speed. So where is the destination of the inference accelerate and speed up, and why we should focus on the lightweight model anymore? Thank you.
Yeah, Actually, I think I don't dig that much into the token generation and the decode part. So for technically, I think the preview part is more computation centric, and for the decode part is more memory incentive. So for a larger model, maybe you can split these to two parts, and each one has own architecture from the academia view, right? Because we don't think about cost. And but if you think about future small models and they put together, then you try to reuse all the silicon, then you need to put them together. So I do think for the future, it still should be defined by the application. Yeah, so now AMD, Intel has their own roadmap, but if there is a big change of the application requirement, I think some of the different architecture will have the chance. So this is my point of view, yeah. Thank you.
All right, let's thank our speaker again.
Yeah, thank you.
Now let me introduce the last speaker, Professor Ma Yi. Last week, Hong Kong U just have a new school of compute and data science, and he's the establisher, he's the founder of that school, and he's the dean of that school. Let's welcome our speaker, Professor Ma Yi.
Thanks, Sharon, for the introduction, and also thanks for having me and inviting me for this exciting event. I learned a lot from just the previous talks, and set a very good stage for my talk. So I'm not a chip guy, so this will not be a chip, but I'm going to make two a little bit daring claims, right? So looking forward, what will happen to, a lot of the chips we have been hearing, right? The chips making are making tremendous progress to support AI, to support computing intelligence, okay? So now, I'm going to make two claims, right? First of all, right, memory is computing. Computing is memory. If you truly understand intelligence, there's no separation. There should be no separation in the future, first. Second, I would actually make this claim. I actually made the claim about 3 years ago. I was talking to some of my Berkeley distinguished colleagues who works on chips. They're very busy trying to accelerate the current GPU, CPUs 3 times, 10 times for AI machine learning algorithms. I think that's probably not a topic for faculty at Berkeley, okay? If you look beyond the, in fact, actually, I start to believe that the entire digitalization, digital computer, the universal computing, is a huge detour for, at least for intelligence, okay? So in Chinese, we say it's kind of like, all right, 大炮打蚊子, we're building a universal computing for something very, very small, very, very special, okay? In the future, there's be tremendous change, I believe, right? Probably gazillions of. So we have to understand intelligence, right? So, I mean, in the past few years, we're trying to, there's tremendous advantage, tremendous advances in technology, right? Technology has changed. In Chinese, we call it 术, 技术, right? But in terms of methodology, in terms of 道, 思想, 方法, I think we have to recap, think hard what we're doing, okay? So now, why we have intelligence? Intelligence is life. Life is intelligence, right? The first pre-trained big model is DNA, right? It passes on knowledge we know about the world, generation after generation. In fact, the way we improve our deep networks these days, big models are the same mechanism. Through trial and error, randomly mutate, and with natural selection. Okay? It's improving, but very costly, very expensive. Right? 就是说物竞天择，适者生存. Right? So now, and if you look at the evolution of life science, actually the life and intelligence evolves together, right? For about 3.6 billion years, we evolved that way, okay? By mutation, random mutation, trial and error. Generations of lives passed on, right? And through DNA, we pass on the knowledge about the world and to learn that way. And about 500 million years ago, right, the individual start to develop brain and eye. That comes to the Cambrian age. 寒武纪大爆炸 生命大爆炸 Because why? Something replaced the role of DNA, our own memory. Individual life start to develop its own memories, perceptions, right? That you can adapt to your own environment. You have much greater chance of survival as an individual rather than just entirely rely on what's passed on to you by your parents, right? In fact, if you understand, right, the advance of intelligence are like that. It's not relies more and more on your DNA. It's actually relies on less and less on your DNA. The more advanced the form of intelligence, right? After birth, you stay with your parents longer and longer and longer. My kids, which is 60 years old, still with me, right? And yet, so this is actually, scientists knows this, right? They call this a phylogenetic. It's actually really about evolving by species, right? And the ontogenetic is about individual intelligence, embodied intelligence. And of course, life and intelligence continues to evolve, right? Suddenly human appeared, right? In the early days, we start to be able to develop a language. Language actually start to replace the role of DNA. Because not only will allow us to use language to communicate with each other, to pass on our intelligence, knowledge to each other, also allow us to pass on the knowledge from generation to the next. So our kids don't have to spend much time, right, to learn. And about 3,000 years ago, maybe, something magical happened, right? In the past, we have been very much just learn our empirical knowledge from empirical observations. But about 3,000 years ago, something very amazing happened. We started to be able to abstract, develop mathematics notions, right? Logic, causalities, right? Solving problems that differentiate human away from animals. So therefore, just looking at the evolution of the science, right? So when you talk about the word intelligence, it's a very vague word. We have to be very scientific, right? What stage? How do we define this intelligence at different levels? Right? At least if you look at the life involvement, right? There's already at least 4 levels, right? Early on, we use DNA to pass on knowledge. Then our individuals start to develop knowledge, and then knowledge gets shared by the group, by the communal. And finally, knowledge started to be abstracted. Math, science start to appear, right? So those are the 4 stages. So where are we at? So this is about the 3.6 billion evolution, right, of intelligence and life. It goes together. Now, about just 80 years ago, 1940s, a bunch of scientists are very interested in, can we emulate, using machines to emulate the intelligence, right? Started with actually Nobel winner, right? It's called cybernetics. You know, he's a founder of control theory, system theory, right? And his work, actually, cybernetics actually inspired almost all people in that age, right? You know, the first mathematical model for neural network and information theory, Klaus Shannon, how do we encode knowledge, information, and how do we improve our decision? Game theory von Neumann was under his influence, and even Turing. Right? Turing machine, von Neumann machine are precisely designed to try to compute, to realize, implement cybernetic systems, right? To emulate, making machines intelligent, right? And of course, in the early days of the machine learning, we learn from the animals, learn from the nature. We should continue to do so, right? Right? How the first model of a neural network, even the CNN, right? But it's very much inspired by how neuroscience, how our brains are wired, right? So I believe that in the future, we should also learn, some of even the computing architectures, we should continue to learn from the billions of the structure that the nature has found through billions of years of evolution, right? We don't have to reinvent them from scratch. And this is a sort of recent history of machine learning. Most of people are familiar with, right? And think AI starts in 1956, that's absolutely wrong, okay? The machine intelligence started from 1940s, right? We'll talk about that later, right? And of course, everybody knows the understanding of neural networks actually go up and down. Most of the winters is due to the lack of theory, okay? Understanding, right? Cause all kinds of problems, right? But we also kind of know the recent history a little bit rosy, a little bit optimistic, right? Since 2012, right? And due to the, boosting of data and computation, right? The deep networks can be trained and suddenly applied to language, images, and even all the biological data, right? Proteins and so on. But the evolution, again, look at this evolution, right? I'm not even mentioning early networks, right? Even this evolution, all the networks are designed empirically. Right? In the past 10 years, the architecture evolves very much the same as early days of life, right? Randomly try, something worked, 一将功成万骨枯, right? Out of hundreds of possible networks, one of them survives, right? Gets passed on. Everybody make copies, open source, right? It's like that. It's a black box. We don't understand we don't know how to evolve, right? And also those networks does not have intelligence. We'll see that. So first of all, many people say, what's wrong with this? We don't understand our brain, right? Why do we have to understand what's really going on, right? Not just the scientific curiosity, right? Maybe we understand it, but recently it's getting very, very pressing, right? Because something is very powerful, used everywhere. And history, if it's any lesson, right, tells you, if something's black box, but very, very powerful, influential, people are going to abuse it, are going to manipulate, create fear, right? And to monopoly, to their advantages. That's exactly what's happening. Hence the embargo. If something important, right, I don't want you to have it. So, it's almost a responsibility now in the scientific community. We have to understand what we have done, right? Why do we learn? What is intelligence? What to learn? And how to learn? And how to do it correctly, right? Life spent billions of years to do this. Can we understand the principles behind it? If not, we're just a bunch of blind men to elephants, right? We're going to make outrageous claims, and which are celebrated in the past 10 years. It's very strange, right? If we all are scientific training at all, and we are saying things against common sense, right? A deep network is all you need. Reward is all you need, right? Attention is all you need. Foundation model is all you need, right? If anyone knows a little bit of scientific history, you know this is ridiculous, right? But somehow those things get celebrated, worshipped. And if this goes on further, this is what will happen. In big models that surpass humans, right? They're going to create fears, misleading people, right? Big models are nuclear bombs, virus, wipe people out of the surface. And the people making the same claim are the ones invested most in AI technology, right? Use your common sense. Why they do this? So in this talk, we try to go through this, right? Why do we learn, right? Anyway, in the past years, the technology advanced so fast, we start to ask some very basic questions. Why there's intelligence? Why do we want to learn, right? The fundamental reason why life and intelligence ever existed is because the world is actually not random. It's actually very predictable. We try to use the predictivity to learn, to be able to survive better in the environment, right? Hence, I used to say, right, everybody is Newton, including cats and dogs, but they just don't know it, right? They have exactly the same model. They can predict how things fall down, right? They have exactly the same model. They can predict how object falls down. They have the same sense about gravity. The only difference is that they don't write down the same language. They didn't write down in the differential equations. So everybody is trying to build a model, right? So now then the question is, mathematically, what is common behind? If something is predictable, if the world is predictable, in terms of data, in terms of the mathematical question, we want to learn what's predictable. What is that problem? Turns out that this is very universally common, right? If any data, any phenomena, observation are predictable, hence, when you observe enough of them, they always lies on very low dimensional spaces. Like Newton's law, right? If there's low force, particle travels on a straight line. It doesn't appear randomly everywhere next time, right? So that's actually lies on very low dimensional spaces. So make them very, very predictable. And even images, although each image is millions of dimensions, but it actually all the image on the surface, natural image lies on very low dimensional spaces. That's a common mathematical problem if you actually know that. For example, right? Because the data is low, if the data lies on low dimensional spaces, allow us to do what? Complete, right? We do this naturally. We also do this for images. Right? It's the same idea, same principle. If data lies on low dimensional spaces, low dimensional structure, allow us to do denoising. Hence, we can do this. This is exactly what all the diffusion model is doing. All the generative AI relies on. Right? And also allow us to do correct errors. Because once you know the structure, learn the structure, allows you to do all these things that we do at every second. Our brain is doing that all the time, right? Be able to correct errors, occlusions. Now, therefore, in fact, you can actually summarize mathematically or even scientifically all that is worth learning. The intelligence is trying to learn what is predictable about the world. Mathematics is trying to learn the data, the huge amount, high-dimensional data. What is their low-dimensional structure? Learn that distribution. And then transform them into a very organized way so that I can put in our brain, memorize it, and use it. Right? So this is actually the common problem. Right? Actually, you can formulate this. Now the next question is, how do we do this? Right? If this is objective, then how do we do this? Has anything to do with the deep networks? Has anything to do with this? Right? Turns out that this is a question asked 80 years ago by people like Shannon and Lober Wiener. How do we record, memorize something useful? Once we learn something useful in the world, right, we gain information about the world. Now, how do you measure that, the information? Right? That's actually the, well, I'll bar details, right? That's a technical. It actually worked out pretty nicely, right? So in order to learn, for example, if I don't know anything about the world, anything could happen. Any blue ball could happen next day, right? I have to record, right? In order to prepare what's the weather tomorrow, if I have nothing, have no prediction, anything could happen here. But if I know that weather is, this is summer, this is winter, right? Only those things could happen. If I know the only thing that could happen are those green balls, I gain information about the world. I save the space, right? I don't have to remember all the blue balls. I only have to remember those green balls. I can have much less storage on my computer to record what is truly need to be memorized. This is memory, right? This is compression. In fact, learning is about to learn the structure of the data through compression, so that you want to be very parsimonious about your space, right? Use limited resource to remember what's most useful. Right? And the information actually gave you a code for that, how to record. And it doesn't matter, you use volume, you use the coding length, the storage. This is just a universal measure. How do you gain information? Hence, in fact, all the learning process is trying to learn, although our observation can be noisy, but we try to minimize entropy. To identify the modes in the data, low-dimensional modes, low-dimensional structure in the data. We try to do the denoising, right? So converge on the low-dimensional structures. So for example, my data could be noisy, but I know they come from two modes. I try to find those modes through denoising, through compression. They're all anonymous. Through reducing the entropy, through reducing the coding length. They're all exactly equivalent, right? In fact, all people have done in the past 10 years with all the deep networks, doesn't matter for recognition and generation, are in this very picture. Okay? This very simple picture. What people do with the distribution, except they do this the same idea in millions, thousands of dimensions, not in one dimension. Right? For example, for pictures, Diffusion models, transformers are doing exactly the same thing, right? How do you process your distribution data? To do denoising, compression, and reducing coding length, reducing the entropy. They're all equivalent, right? For example, classification, right? How do we convert those high-dimensional data into very compact code? We don't know how to do it. Let's fit some very daring people says, well, let's just fit some deep networks, right? As a black box, we fit. Make it fast, right? This is one example. You compress your data. And this is exactly the idea behind the diffusion model, right? All this, diffusion AI, Midjourney, all this generative AI, people celebrate. This is the generative AI age, right? It's actually a very tiny thing for us, right? And you have diffusion AI, Sora. They're actually doing the same thing. Compressed data, right? So a random image compressed to the surface of natural images, right? Exactly the same idea. Remember that one-dimensional example, that's what they do, okay? No mystery, nothing, okay? Now, there's one thing we only clarify what people want to do, right? We learn those low-dimensional structure. We even know how to measure it, how good that representation is. How do we do it? Of course, you can say we don't know how to learn that mapping, right? We fit with that neural networks. What are neural networks doing then? Why any particular neural networks? Turns out you don't need neural networks, right? So once you know what you want to do, for example, you want to minimize the entropy of your data, then you just minimize it, right? Any mathematics tells us we just minimize it. So how do I minimize something very complicated, right? This is an object function of the feature could be thousands, 10,000, millions of dimensions. How do we do it? We don't know. But what do? At least we can do gradient descent, right? Computing the gradient, 爬山, 对吧? So once you do that, something interesting happens, right? So I just do one step at a time, right? The next step is just the current state, follow the gradient, going up, down, down, 爬山, 对不对? 可以回吧? Then you do this step by step. Each step is one descent, right? You repeat this step by step, then change the terminology, step to layers, you get deep networks, okay? So that's exactly, neural networks are exactly nature's way to implement optimization algorithm. Remember, our brain, when you are born, you are not preloaded with PyTorch, okay? If your brain wants to optimize something, it has to realize that iterative optimization algorithm. Your networks are precisely doing that. It's realizing the optimization algorithm for you, okay? It's just physical, carbon-based realization of that PyTorch. So this is, then you actually can derive the network completely, instead of black box, it's just purely white box, because every layer, it's doing gradient descent, doing compression, doing denoising, reducing the entropy. The mathematical, statistical, geometrical interpretation of every layer, every operator, are completely transparent, including every parameter. There's no ambiguity, right? And they even actually start to learn. If you train such neural networks, white box, even they start to appear, some even semantic meanings start to appear, because they are statistically meaningful. They're geometrically meaningful. Hence, potentially, semantically meaningful, right? And you can actually scale this up, right? There's a lot of work on it. You can completely scale this out to billions, trillions of images, right? It just behaves like all the empirically based transformers. But yet, they are purely mathematically explainable. There's no mystery, complete white box, right? You know exactly what you did to data, right? And this is not all, right? This is very unifying, as I have said, right? All the things you have seen in the past 10 years, right? All the networks, right? Lelat, Alexa, ResNet, ReduNet, Transformer to create, they're all just doing exactly the same thing. They just attention head, radius reduction, minimal description length, score function, they're exactly doing 爬山法, right? Locally reduce your data to lower dimension, denoising, and reducing the entropy of your data. Everybody is doing exactly the same operation, right? Nothing else. And now you actually can see, at least from both objective and from the architecture, everything are transparent. There's no mystery, right? Instead, in the past, we just have to do a back box input-output fitting. All the architecture are empirically designed with trial and error, evolving in exactly early days, right, of life. And now you actually can design based on mathematical objective. This is purely objective, right? This completely has nothing to do. And also, this is actually architecture is from just iterative optimization. And once you train such network, the representation become purely mathematical transparent. Right? You don't get to decide anything. Right? Now, is this enough? Right? So we know where the network is actually, remember, network help you to layer by layer, iteration by iteration, help you to optimize, right? You will find, maybe you iterate enough, you'll find the optimal solution, right? But is the optimal solution the correct solution? No, in generally not, right? You optimize, you hope you get the right solution, not necessarily guaranteed to be correct, right? So hence your memory maybe gets stuck to local minimum, right? Maybe your data is not enough, you optimize too early, right? And how do you know your memory is enough, right? Your solution is right. This model may not be complete. For example, maybe the family of apple requires 5 dimensions to describe. You only learn 4 of them. There's some app you have never seen, right? You have to change. So hence, you have to use your memory to predict, to regenerate, to predict back to the world. Have I memorized all the apples correctly? The shapes correct, right? When you have an image, you encode, you remember in your brain. The way to memorize, to test if your memory is right or wrong, you'll be able to resample, get it regenerated. So you can see, in fact, if you look at this principle, right, this is actually this is called autoencoding, right? You have data, you encode to your brain internally, you'll be able to reproduce it. This is autoencoding. Does anyone know why Hinton get a Nobel Prize? What's the network? Boltzmann machine, right? Boltzmann machine is actually after the Helmholtz machine. And Helmholtz machine is after the Hopfield machine, right? Neural network. And both Helmholtz machine and also Boltzmann machine are precisely trying to compute autoencoding. By the way, still very heuristic, okay? But that's already groundbreaking enough. He's trying to realize this for handwritten digits. Okay? Now we know how to do this correctly now. Although all the network before was guessed, right? He guessed how many layers, how many nodes. Now everything here should be homework for students. You know exactly what you do. You do compression, forward, and the denoising, diffusion. Both sides are derived from mathematical principles. You don't guess anymore. And you can achieve exactly the same performance as He Kaibing, right? Did the math autoencoding. So you use it to do prediction. If you can learn the low-dimension structure, you can complete your signals. Remember the earlier examples, right? And is this enough? Is autoencoding enough? If I can remember something, be able to reproduce it, is this enough? Not enough for nature. Why? In nature, we never learn this way. We don't have this option to check if our recovered data is correct or not, right? Everybody knows the screen is a rectangle, right? Anybody disagree? Have you measured it? Do you ever come up stage and the measure is 90 degrees? The line is straight. The distance ratio is 3 to 4. You never. You don't have the option. When a tiger approaching you, right? You don't ask her to stop. I want to estimate your speed and the position, right? Before I take the next action. Right? All that animal has gone, right? So everything we learn, everything about the world almost entirely from inside our brain. We don't get to train end to end, okay? Nature doesn't have that option. How did they do it? This is exactly what Nobel winner answered the question 80 years ago. You don't do this open loop end to end. Only NVIDIA try to convince you to do open loop end to end, right? because they want to sell chips to you. Want you to produce also scale AI, want to sell data to you, right? Nature doesn't do that. Nature actually does a closed loop, learn everything in the brain. So if I want to memorize something, this is my brain memory. My memory may not be right, it may be incorrect. I want to reproduce it, get x hat. X hat may not be the same as x, but I cannot measure the distance in the world, in the physical world. What I do, I map that back to my brain. I imagine, I predict, then I imagine that, gets everything reprojected back to your brain. You compare inside your brain. Say if your prediction is right or wrong. This is called a closed loop, right? And it's called cybernetics, by the way. And these days has a very fancy but a vague name called embodied AI, right? So embodied AI is 山寨版的, cybernetics, okay? Read the history. And this is the work we actually did with Yang Kun, right? See, everybody say open loop system, we train a big model, right? But if you retrain it, fine tune it, actually there's a phenomenon called a catastrophic forgetting. Once the system gets trained, including a big model, don't think that big model, once you do fine tuning, doesn't forget, actually forget a lot, okay? Right, that's a problem with the open loop system. Once you ask the network to fit new data, all the previous memory get lost very, very fast, right? It's called a catastrophic forgetting. Closed loop system do not forget that fast. They forget very gradually, just like our brain, right? Hence, in the whole world, this is actually with Yang Kun and work, right? So if you do this, you can learn memory and incrementally, continuously to learn, and you do not forget that easily. Hence, all memory in the world, all life in the world are closed loop system. Yet, there are people trying to convince everybody in this room, let's do end-to-end, train open loop systems, right? Including Elon Musk. It's actually quite idiotic if you know the history of understanding about intelligence, right? In fact, nature has exactly all nature network system, right? All alive AI system at all scale are closed loop systems. They try to simplify things, organize information, and they have closed loop to correct error, right? Last year, right, 2 years ago, Hinton, his latest single author paper, the title called the forward algorithm. He already admitted, right? First time, he admitted nature doesn't do backpropagation. Nature corrects error by closed loop, right? The forward is doing optimization, although he doesn't say optimizing what. Right? So this is actually what we call, right? Just because network gets larger doesn't justify its AI 2.0. Okay? It's the same methodology, same, brute force method, right? Doesn't change. Open-ended system. It's not what actually, at least Yang Kun we believe, the AI 2.0, the A stands for autonomous. The system can autonomously learn, correct its error. And also, now, this is has something to do with today's talk, right? Just understand the principles, the objective and principle of intelligence. Doesn't mean you know how to implement it, right? See, everybody, including Ilya, say big model is doing compression. I completely agree with him. The next sentence, he says, oh, it's optimizing Kolmogorov complexity, which is completely wrong, okay? Because it takes human 80 years to realize how to realize compression, how to do compression properly, efficiently, right? The progress in the past 80 years of computers are precisely how to implement things efficiently and scalably, right? For example, the Kolmogorov complexity is completely incomputable, intractable. That's the contribution of Turing and Shannon. Tell us what is computable, what is achievable, okay? But even computable thing may not be affordable. They may be NP hard. You have to study what is a polynomial, right? And when you have billions of parameters to optimize, you cannot even afford any polynomial algorithm. Who is using Newton's optimization algorithm, Newton's algorithm? Nobody. Everybody is using gradient descent, using backpropagation. Why? That's scalable. Now, why nature doesn't do backpropagation? We cannot afford it. We only have 15 watts. We don't have 10 megawatts, okay? We cannot afford running 10,000 GPUs simultaneously, right? There's still at least 7 to 8 magnitude of efficiency we're looking at. Nature be able to do this much, much more, right? Completely different from global backpropagation, end-to-end optimization. Even though BP is scalable, nature doesn't have that option, right? The evolution of intelligence is not just about understanding the principles, the mechanisms, but it's also how to realize that efficiently through carbon-based, silicon-based, or maybe quantum-based, who knows? Right. So this is actually an idea, right? In the past 10 years, everybody thinks we should accelerate this darn thing, right? End-to-end. More data, bigger model, right? A lot of people get rich, right? And it's not autonomous. It doesn't correct itself, right? It doesn't know it's right or wrong. It's not a full memory, okay? Recognition and generation is still separated. A 2-segment. Don't celebrate the generative AI, okay? It's just 1 segment. It's only part of our function of our brain, right? And even a single loop is not enough. Our brain has 250,000 loops. They're massively parallel, massively efficient, right? They're distributed, parallel, and optimizing in loops. Right? That is where the efficiency and robustness come from. Right? We are way to go, right, in terms of architectures, how nature realized intelligent systems. Right? So then what is intelligence? There's a profound confusion in the past decades, right, despite the technological advance. People confuse two related but fundamentally different things. One is called knowledge, one is called intelligence, right? So intelligence actually is one has a mechanism for self-correcting and self-improving for existing knowledge. Right? Any system, no matter how big, if cannot self-correct itself, does not have intelligence. Okay? Just a memory, right? So if you ask yourself, GPT-4 or new baby, which one has intelligence, which one has knowledge? The answer is obvious. GPT has the knowledge, but not intelligence. Right? To some people, this may sound absurd, right? Think about hard, right? The baby has intelligence. Why? It may not have knowledge yet, but it may grow to be a next Einstein, be able to add to the existing knowledge, discover something new about the world, right? So for people to remember, right? Knowledge is actually the integral of intelligence. Intelligence is the derivative of knowledge. Very simple. Right? So now, here's another thing, right? Just young kids, right? So everybody, a big lesson, 对吧？读历史啊 read history, okay? Don't get your history from 自媒体 Wikipedia, all right? Go to the original text, right? This everybody celebrate, right? There's no doubt. Everybody celebrated the past 10 years artificial intelligence, right? Well, this is a little bit, there's a history 给我们开了一个很有趣的玩笑。Okay. This artificial intelligence is not that artificial intelligence. Everybody quote AI, right? After this talk, I hope everybody in this room don't make this mistake anymore, okay? Read the proposal. Attempt will be made to find out how to make machines use language, form abstraction concepts, solve kinds of problems now reserved for humans and improve themselves. The precisely try to distinguish what is different from the intelligence different from animals and human. Causal, logic, abstraction, symbol. Right? Those are the bunch of young researchers. They try to precisely not to do cybernetics. Right? The 40s program is precisely about animal intelligence, signal processing, memory, prediction, error correction, control and game, reinforcement learning. Right. Sounds familiar? So look at what we are doing in the past 10 years, right? Object recognition, image generation, text generation, compression, reinforcement learning. Is this similar to what the 1956 program, language, abstraction, logical inference, causality, problem solving? No. So past 10 years, we're at here. We are very much here. It's a renaissance not about AI. It's a renaissance of cybernetics. Right? So therefore, if you understand the history a little bit better, right? So machine intelligence has, I think, at least 3 phases, right? Even this coincides with the evolution of life and intelligence, right? Early on, pre-train big models to memorize knowledge. Sounds familiar? DNA is doing that. Even the methodology we evolve is similar, right? We mutate and get selected which one survive. Then open source it. Then everybody copy. Yeah. But there's no intelligence. Individual doesn't have intelligence. Species and the environment together has intelligence. Okay? The closed loop system. Then individuals start to develop brain, memory, and eyes, senses. They start to form their own memory. Learn autonomously, individual, right? That's animal, right? We are very much trying to cross here. In terms of human brain, logic, abstraction, reasoning, we haven't started yet. Okay. So I have 2 PhD students at Berkeley. They don't do anything, they do one thing. Every time there's a big model coming out, they test if the model understands numbers. The simplest abstraction, the simplest symbol. Natural numbers, not even rational, right? Not even 复数, okay? Complex number, forget about it, right? Real number, forget about it. Just natural number. Do they know which one? So after GPT 401, right, came out, 5 seconds later, my student told me 3.911 is still bigger than 3.9, okay? I post on Twitter, everybody yelled at me, right? But Yang Kung retweeted it, everybody yelled at him, right? So, and then I screen captured it, posted it, crowd down a little bit. People start thinking, and in the afternoon, they fixed it, right? If you ask the 9.1, they actually fixed it. But if you ask it in a slightly different way, still, 3.11 is still bigger than 3.9, okay? One of the game, my kids, 13 years old kid, although there's some MIT professor thinks the big model has become sentient, right? Conscious, right? My 13 years old kid, my younger son, his favorite game these days is to trick all the big model to believe 3 plus 3 equal to 5, okay? Try. You have a very high chance to succeed, okay? I can tell you, okay? That's his favorite game. If it does not even pass the Turing test of 13-year-old, what we're celebrating? Okay, yes, everybody, there's a lot of very usefulness, but as a scientist, as a researcher, there's a lot of things we should become more sober about it. Right? So now I think we're at the stage we understand the objective, at least for low-level intelligence, at a memory level, computing level, right? We have good understanding of the objective. We understand the reason, the role of deep networks. We can actually improve them tremendously now. We no longer live in the trial and error age. I'm pretty sure about that. All my students are designing new architecture completely based on guidelines. You don't have to guess, right? You can use optimization principles to improve your architecture design, right? You no longer work in the dark. But also, right? Because we understand how limited we have done in the past 10 years, right? And become even more optimistic how wonderful, right, the future bright will be for younger students. We barely scratch the surface about understanding intelligent systems. And not alone, building efficient system, complete, correct system to realize them. We only build a fraction of our memory systems. Recognition and generation separated. 记忆的碎片. Now it's time to integrate, build a complete system. And the system can self-improve, self-learn, build their own memory, truly has intelligence. Maybe after we've done that, one of the people, genius in this room, start to figure out what happened. The human brain start to abstract, start to form symbols, start to discover logic, start to discover causal relationships, start to do inferences, to solve mathematical problems. Right? That's my talk. Thanks.
Wonderful talk. After Professor Ma's presentation, I felt that we have hope that we don't need that many GPUs anymore, right? Due to time constraint, maybe 2 questions. One from the back.
Dear Professor Ma Yi, thank you for your excellent presentation. I have a question I'd like to ask. Since deep learning frameworks can be mathematically white-boxed, could a learning structure based on mathematics be proposed that is more efficient than deep learning, such as a closed-loop system you proposed?
So there are 2 separate questions, separate answer, right? So yes, even just for open loop, designing the optimal architecture, deep network architecture, now you know what each layer is doing. You know what the objective is trying to optimize. You can actually do a lot of changes, right? For example, there will be at least 2 architecture. See, guys, if you look at in the past, all the architecture were discovered independent by different groups, right? That already says something. There's no principle. There's no design. There's no guideline. Everybody just try. Someone got lucky, right? It's like early days, right? Gets natural selection. Now, second, now you know what he's doing now. Now, actually, at least in just the past year, my group already had the several architectures coming out. You'll see. They're much more efficient. You can actually prove, for example, based on the transformer, turns out you don't need the MLP. Turns out the even computing correlations, the attention can be linear complexity. It doesn't have to be quadratic, right? Because you know what the operation is doing, right? Even the white box architecture right now we derive is based on the most naive basic optimization you can ever imagine, okay? There are 300 years of history about how to design better optimization algorithm. There are 10 different versions at least, right? Even for gradient descent, there's many, many different versions. We have never even tried them yet. So barely started, even design better architecture. Second, once you know the segment, how to put it into a system, a closed loop system, do we solve them, still optimize them end to end, or we can do layer-wise? Nature doesn't definitely not do global, right? Now how our memory optimize our recognition paths and our generation paths, we have no clue. We have some ideas, but in terms of implementation, has not started yet, okay? Including the closed loop system we did with Yang LeCun, still we're doing still a little bit brute force global optimization, but we see the benefits of that already. It becomes more consistent, and also it does not forget, and so on and so forth. It can support continuous incremental learning, but in terms of efficiency, it's far. We have not found the right answer yet. So what are the correct optimization strategy for the closed loop system? We don't know. But at least you can see from this, and once you're understanding the neural network, what it's doing in the forward pass is optimizing. You actually can compute those parameters in the forward pass. You don't have to solve. You don't have to optimize everything from scratch to do backpropagation. So which is already a huge save, right? You can optimize the network both forward and backward pass. The theory already gave you that option. That has never been an option before, right? So about 15 years ago, my group wrote a paper called the PCA network. It's completely computed in forward fashion, right? It actually reached the state of art on face recognition, digital recognition, but nobody believed it. It's only have 2 layers, simplest networks. See, there's a lot of simplification can be done, guys, right? That's why, nature is all about the parsimony. Remember the quote I did in the beginning from Einstein, right? Science, intelligence are following exactly the same principle. Try to make everything as simple as possible, but not any simpler. So your memory just serve you right for the prediction, right? So that's actually, we are still a long way to go to emulating the kind of intelligent mechanism that nature, even at the animal level, we're a long way to go, let alone human, the abstract intelligence, the true artificial intelligence, okay? The word, adjective, artificial, find out what that adjective is trying to define correctly, okay? Don't take that from 自媒体, right? Even from Google or OpenAI's, reports, okay? Intelligence should be now be really truly defined clearly as a scientific and a mathematical or even a computational subject. And yes, it can become a very rigorous, no longer a empirical study or purely technological subject. I think now should become a scientific and a mathematical subject from now on. Yeah.
All right. Let's take. I think that if you have more questions, we can ask offline. I think that's conclude this afternoon section. And thank everyone to attend this section, and also thank our speakers. All right. Thank you.
May I now invite Professor Xie to proceed to the podium to give a summary of this section? Yeah, could you? Yeah, please. May I invite Professor Xie to give us a summary for this section? Thank you.
Yeah. So, all right. So actually, I'm very glad that everyone stayed here for these four wonderful speeches. Actually, from U.S., from Europe, from mainland China, and from Hong Kong, and also from different subjects, from accelerated design, from architecture, and also the last one from Professor Ma Yi on the algorithm itself. And I think Professor Ma Yi's talk is very inspiring. It's actually give us computer architecture guys like there's a different way to do AI. And I think that I checked with the organization group that they said that we have about 200 audience locally and almost 1 million audience online. So it's very impressive. All right. Thank everyone for attending this section. Let's thank the speaker again and also thank all the audience. Thank you.
Thank you so much, and please be seated. Thank you very much. Ladies and gentlemen, it's the finale of today's symposium. Once again, thank you so much for joining 2024 Future Science Prize Week and the Science Symposium. I hope you enjoyed as much as I did. For those who will return to the hotel, please gather in front of the entrance because we have arranged a shuttle bus for you. See you around at the Future Science Prize Week. Thank you very much.